Hello, this is Jason Kendall, and welcome to the next of my introductory astronomy lectures. This time we're going to talk about the appearance and structure of other galaxies. We went through an extended dance remix of exactly what the Milky Way looks like as a galaxy, and we discovered that it is the galaxy, meaning our home galaxy, and we learned from Edwin Hubble that all the other spiral nebulae are extraordinarily distant objects, extremely far away, and that our Milky Way is one of many, quote, island universes. But what we really learned is that there's lots of different types. And so once Edwin Hubble started doing a major photographic survey, he showed us that the cosmos is filled with these extraordinarily large distant objects. So let's go see what they are. Hubble, during his work in 1926 to 36, once he started really going to town with that 100-inch telescope at Mount Palomar, he took numerous photographs of the night sky, made amazing discoveries, and found that the bright galaxies in the sky, we're talking the bright galaxies now, fall into three broad classes according to shape. So he simply took photographic visual surveys of them and determined their classes according to shape. So we're going to follow in Hubble's footsteps in terms of looking at visual representation or optical light representations of the various galaxies. And so Hubble's tuning fork is how he thought they would, that they had some kind of significance. And he thought that they naturally progressed from one to the other. And so he had that 75% of all the bright galaxies were spirals, about 20% seem to be ellipticals, and about 5% are some sort of irregular, which don't fit any pattern. And this is his tuning fork diagram. And he thought that actually progressed from left to right, from elliptical to spiral, thinking that go from a simple looking thing to a more complex looking thing. But we now know that the Hubble tuning fork diagram has no intrinsic meaning. It just looks nice and is very helpful to help you remember the different types. So you can see we have different things. We're beginning with E's, those are the ellipticals, and we have the S's, those are spirals, and then there's the upper tree of spirals, and the lower tree, which are the barred spirals, or the SB's. And the bars have a bar across, and the irregulars, well, they're kind of like train wrecks. So let's go take a look at all of them. From this point on, we're going to do an incredible visual survey because you've probably not seen a lot of different kind of galaxies. So it's my job in this particular lecture to give you a whole bunch of images and show you what the galaxies themselves look like. So here we go. Hubble's classification scheme looks a lot like this with ellipticals and spirals, so let's go take a look. I derived all of the images that you'll see in this particular thing from lots of different sources, from the National Optical Astronomical Observatory, from AAO, the Australian Astronomical Observatory, the Gemini Observatory, European Southern Observatory, the Keck on Mount Mauna Kea, lots of things from Hubble Space Telescope. In fact, I even went to the SEDS group, and then there's a guy that does the NGC project trying to take pictures of all the NGC objects, and then looking at the NED database, which is the NASA Extragalactic Database of Galaxies. So you can look at all of these things to find all these images, and everything I've done here comes from these places. And a lot of these then also appeared in Astronomy Picture of the Day. So if you Google APOD, you'll also see many of these. All right, elliptical galaxies are elliptical in shape. They don't have any internal structure. They don't have disks. They don't have spiral arms. They don't have dust lanes. The brightest stars are big red supergiants, and they're classified only by their appearance and their apparent flatness. So if you see a circular looking one, that's an E0, and if you see one that's really wide compared to its height and it's really flat or smushed or cigar shaped, then that is an E7, where it's up to about 3 times as wide as it is high. Ellipticals come in huge size differences, from some that come from trillions of stars down to tiny little dwarf with only a few million stars, which is smaller than some globular clusters. They also contain no gas or dust and show no evidence of star formation. So they do have lots of hot, but ellipticals do, however, tend to have really large hot clouds of extraordinarily hot gas emitting in X-rays that extend far beyond where you can see. So they may be very well embedded in very, very, very large X-ray cloud emitting gas. So that's interesting. All right, so this is a classic elliptical galaxy. It's a giant elliptical, and it's M87, and it's part of the Virgo cluster of galaxies. And this was taken by the CFH telescope at Mauna Kea. It's an enormously fun look to see, and so when you look out, you see it's got an elliptical shape. It's pretty yellow, and there's a lot of stars, and it's a kind of a glowing cloud. And let's go see more ellipticals. This is the elliptical galaxy 1132. It seems to be in the middle of a whole number of tiny little galaxies. It's a giant elliptical, and you can see a number of little galaxies all around it. Here's another giant elliptical galaxy. All right, we keep going through it. And another elliptical with some spirals that are much more distant in the background. And again, I believe this is M87 that we saw before in Virgo. And you can see a number of other ellipticals, at least 4 others that are there, maybe 5 or 6. Actually, Google, if your eye wanders around, you see a lot of them, plus a lot of other fuzzy objects in the background too. If it's got basically spikes, like those starry spikes, that's a Milky Way star. That's a star in our Milky Way. We're mostly and completely concerned with all the fuzzy objects that are in our field of view. Those things are much more distant. M87 in the Virgo cluster of galaxies is over 65 million light years away, and so it's truly distant compared to the stars in the field, which are only tens of light years to thousands of light years away, and maybe up to 10,000 light years away. But stars are on the order of hundreds to thousands of light years away in pictures like these, but galaxies are on the order of millions or tens of millions, if not hundreds of millions of light years away. And this particular one in the center, that is in the Virgo cluster, which is about 65 million light years away. Incidentally, the light from this galaxy started traveling to us at about the same time that the dinosaurs were wiped out on Earth. So that's what it looked like back then. We see it now. Here's another image of an elliptical galaxy, and another one is a very, very elongated elliptical, and now a more centrally looking elliptical. Lots of ellipticals. Oh my goodness, ellipticals. There's an E0 type, definitively, and other ellipticals, and so on, and so on. The Virgo cluster has a lot of elliptical galaxies in it. We see 4 examples here, ranging from E0 and ranging from a dwarf in the lower left to a very large E7 type elliptical in the upper left. All right, so ellipticals, can be looked at as kind of boring to put up, and you're not going to make a really big poster of an elliptical galaxy and put up on your wall, because people go, why you got that big white dot on your wall? But we're going to get to the more pretty looking galaxies very soon. The next intermediate type in the Hubble scheme is the S0 types, and they are the lenticular galaxy. And lenticular means lens-shaped. And there's also barred lenticular, SB0. They do exist. So they're distinguished by having a bar type of shape in them, but they're rarer. So now a lenticular does have a disc-like structure. It does have a central bulge, but there aren't any spiral arms, and there's no interstellar gas. So you don't see any hydrogen gas clouds or anything like that. A lenticular galaxy is seemingly intermediate between ellipticals and spirals just because of the appearance. And they do have dust in their disks. So an elliptical can have dust lanes, even though there's almost no star formation going on. So that means the hydrogen gas is gone, but there's still dust left over, which is interesting. But because if they have very ill-defined arms, and if they're face on, meaning you see most of them from the side, you won't necessarily see that dust, and a lenticular can easily be mistaken for an elliptical if they're not seen edge on. All right, so here's a classic lenticular, meaning that you see just a fuzzy cloud, and that fuzzy cloud is very much like an elliptical galaxy, but yet it has a dusty lane going through it. But there's no pink clouds in that indicate star formation. So this is a standard sort of typical lenticular. Here's another lenticular. I believe it's actually the same one. No, it's a different one, but they look very similar, don't they? Here's another lenticular with a seen edge on, and you can see there's dusty lanes in them, but there's no pink star formation, so it's all older stars. Here's another lenticular, and you can see that they can have spiral arms to them, but the spiral arms there's no star formation. There's no pretty little Orion nebulas or Trifid nebulas or anything, or Tarantula nebulas or anything like that. There's nothing like that, but there are dusty lanes inside of them. So these are kind of reddish sorts of galaxies. Here's another lenticular. We see it's kind of wispy, and there's some dusty lanes in the middle, but it mostly looks like a lot of older stars. Another lenticular, dust lane again. There's a standard appearance, and here's this. They tend to be kind of small. This is about only on the order of a few thousand light years across, and it's about 25 million light years away. So it's closer than the Virgo cluster of galaxies, but yet what we see is there's a dusty lane and then some appearance by some of the cloudiness for it, but that cloudiness is obscuring some of the dust lanes. So it's kind of in between an elliptical and a lenticular. All right, let's get to the really pretty stuff. The ordinary spiral galaxies. So spiral galaxies come in a few flavors, and we will call them S, A, B, C, and D. Now, Hubble did basically S, A, B, and C, and there's been some extensions and slightly different things, but let's add the SDs because they do exist. So an SA will have an enormously large bulge and very, very, very tight, indistinct arms. So they look a little like a lenticular, except there's star forming going on. An SB are an intermediate type. They don't have as large a bulge, but the arms are much more distinct. And SC are of a tiny bulge and loose, very well-defined arms. And SD has absolutely no bulge, but lots of big spiral arms. So these tend to be really pretty, so here we go. This is the classic SA type galaxy, the Sombrero. It's about just under 30 million light years from Earth. It's about half the size of the Milky Way at 50,000 light years across. And inside of here, there is some star forming going on. Not a lot, but you can see that if you squint and look carefully, you can see there's some pink clouds in there. So this seems to be like a extremely dusty lenticular type galaxy. But that's where we think of that's why Hubble merged into this tuning fork diagram, because they seem to, by appearance, merge smoothly one to the other. But that doesn't mean they evolve this way. They just have this certain appearance. And so there's only certain ways that galaxies certainly appear. Well, inside of those dusty bands, there's some pink glows, and those pink glows show star formation. All right, another one is the classic spiral called M81, and M81 lies about 12 or so million light years away, and it's an incredibly beautiful spiral galaxy, and it's one of those intermediate SB types. We can see definitive spiral arms. There are bright pockets of star formation indicated by the blue glows, and there's some pink glows as well, indicating ongoing star formation. And this is another view of it. And then we see with the Whirlpool Galaxy, extraordinarily vigorous star formation happening. That's what all the pink glows are. Those pink glows indicate Orion nebulas and hot H2 regions, meaning ionized hydrogen. That's where the pink glow comes from. And inside of the pink glow, what we see are that's where bright stars form in clusters and groups. And as the galaxy itself rotates, or more specifically, everything rotates through it, gas passes into these spiral arms, these overdense regions, gets compressed, as we saw with the formation of the Milky Way spiral arms, and then stars are formed and keep traveling on and explode as supernovae. So basically, you see dust on one side of the spiral arm, and inside of the spiral arm, vigorous star formation and pink clouds, and on the other side of the spiral arm, as they travel through the density wave, are the bright stars that were formed by the gas only a few million years before. So you can think of it as that. Look at it from one side of the arm to the other, and the extent of the blue stars doesn't get very far from the spiral arm. So they'll only go about 10 or so million years. So that span is just how far they go in 10 million years. All right, so let's get deeper in close to the center of the Whirlpool Galaxy, M51. You can see more of what I was talking about, meaning the spiral arms are places where star formation is vigorously occurring. And this is the Pinwheel Galaxy, M101, which is also an SC type galaxy, a very small bulge but large and loose spiral arms. And if you look really closely, there's a wonderful detail of it. You can see the flow of the gas. You also see how the stars themselves are grouped in large groups. There's not as much pink star formation going on. And what's neat is about this particular image is way off to the right, we see another galaxy. And that galaxy is extraordinarily distant compared to M101. So we're looking through the galaxy to an extremely distant galaxy, maybe 100 times further away. That's an amazing image right there. But what we can see, remember we talked about the nature of how spiral arms are basically the gas and dust is on these streams of elliptical orbits. So look at the shape of the gas. It looks like it's in waves. But now think instead of them being in waves, think of them as lines. And so the lines are orbiting the center. And so you have like this nested set of ellipses, and when they run into each other, they get denser and darker. All right, here's the Triangulum Galaxy. This is a local little neighbor within a couple million light years, and it's a favorite target for amateur astronomers and for amateur photographers because lots of really great star formations going on. See, that's that pink glow. It's also an SC-type galaxy with a very, very, very tiny core, bulge, galactic bulge, and very well-defined arms. And another one is a starburst galaxy called NGC 3310, where there's huge amounts of star formation going on. That's why it's got really, really bright all over the place. It's about half the size of the Milky Way, and it's about 50 million light years away. And to cause that, it probably was a collision with another galaxy, maybe 100 million years ago. And these stars are now the brightest of stars. And we can estimate that there would be 100 million years ago, because the types of stars are roughly A-type stars. O-type stars live a few million years, B-type stars live tens of millions of years, but if the spectra of the stars is roughly A-type, then they'll live about 100 million years before dying, and that is the kind of stellar spectra that we would see inside of this galaxy. All right, here's another great spiral, Messier object number 74, with numerous star formation regions and quite distinct things, distinct images. And these Hubble heritage images are fantastic, so go definitely Google these around. And if we look closely, we have M81 and M82 close together in the sky. These are an interacting pair at about 12 million light years away. And this is the Leo triplet, a triple of spiral galaxies in the constellation Leo. And you can actually, and this image is about 1 degree across. So if you have a large enough telescope and the eyepiece lets you see about 1 degree across, for a standard, for something that's an f2, f4 type telescope, if you have a 17 millimeter eyepiece, this would all fit inside the same eyepiece, which is I've done. So it's kind of pretty. So we see three different spiral galaxies, and yes, they're an interacting group. The spiral galaxy NGC 1309 has another little distant spiral up and to the left, and a much more distant spiral off to the right at 3 o'clock. And then you can see huge numbers of spiral galaxies way off in the distance. And so clearly we were looking not along the plane of our Milky Way, which blocks the light of these stars, but above or below the Milky Way in order to see this object. So look at all the little tiny smudges in the background. Those are even more distant galaxies, far, far, far in the distance. And there's another one, another beautiful grand spiral. We can see little tiny smudges. Each of those are much more distant galaxies. Here it is again, and the spiral galaxy NGC 3370 is chosen because it has some beautiful imagery galaxies in the same field of view. An edge-on lenticular on the lower right, lower center, and it looked in a tiny barred spiral in the upper right, as well as numerous little galaxies. Those aren't little because they're little compared to NGC 3370. They're little because they're really far away. So the universe is filled with these things. So here's another one, NGC 3949. I love showing these off because they're really pretty. And there's another one, and you can see the spiral arm structure, and there's another beautiful one. And you can see that now the two elliptical, there's actually a number of elliptical galaxies that kind of surround the spiral. And yeah, they seem to come in groups like this. And here's another classic spiral, which has huge amounts of dust. And there's the starburst galaxy again, just because. And now we can see what a spiral galaxy looks like edge-on. I believe this is NGC 891, and it's a classic edge-on spiral galaxy. How do we know it's a spiral galaxy? because of the huge amounts of dust and gas, and the spectrum shows star formation and hydrogen gas cloud emissions. And there's another edge on spiral galaxy, and we know it's a spiral because of the star formation that's happening in it. And that star formation can be seen by the glow of hydrogen and the prevalent blue glow of stars in the disk. Remember again that the dots that we see in front of the spiral galaxy are part of our Milky Way, and so therefore very close. And there are little tiny smudgy galaxy-like objects in the very far background which are much more distant than the foreground galaxy. And this galaxy is on the order of tens of millions of light years away anyway, so that's pretty far. The stars are near at tens to hundreds of light years. Then the galaxy is millions of light years, and the much more distant little background galaxies are probably 100 million light years or more. There's a lenticular and a distorted spiral galaxy, and sometimes you see one galaxy in front of another galaxy, and this would be along the plane of the Milky Way. That's why we see so many stars in this field of view. So we're looking away from the center of the Milky Way out along the edge, and so we can definitely see the spiral structure of this galaxy. But all the stars in the Milky Way are trying to get in the way of our view. There's another pair that seems to be one in front of the other. And here's what we call a compact group. And so all four of these little galaxies are in a group, gravitationally interacting with each other. So that gives us some information about the nature of normal spirals. And then parallel to them are the barred spirals, which really are interesting because they have this enormous bar-like structure, where the bar appears to rotate as a solid body. Now remember, galaxy bars are not solid structures like a rod or something. No, they're composed of stars and gas and dust, but they rotate as one. So the stars so that means the ones that are farther out are rotating faster in their orbit so that they maintain the bar than the ones closer in. Just in the same way, if you look at a marching band, so yeah, the best example is a marching band. The marching band has to keep its lines together in order to stay as a line as they turn a corner or do their thing on the football field. So the guy that's in the interior of the turn, he takes little tiny baby steps, but the people on the outside of the turn, they have to take huge steps, so they have to go faster or practically run in order to keep the line the same. So in terms of marching band styles, you can think of the bar of a barred spiral as a big marching band of stars. All right, so here's the barred spiral, NGC 1300. So they have very similar characteristics to spiral galaxies, except for the huge bar in the structure. There's another one, the NGC 1365. We can see the various types, SA, SB, and SC. This is an SBA, so it's a large bulge and tight arms. And this is an SBB, meaning intermediate bulge but looser arms. And then we can go to SBC, which are really tiny bulge, very, very well-defined arms, and the bulge is there in the center. Now this also highlights the incredible star formation that is occurring in M83, Messier Object 83. And that's where all the pink glow is, and that's where stars are being born even now. And it's wonderful to take a zoom in to see the effect of that. So those are incredibly turbulent regions, but if you were nearby, you'd have something, if you were in that galaxy close to that, you'd have such a beautiful view in your night sky. All right, here's another view of a barred spiral. More barred spirals. You can see the pink glows of star formation. So these have lots of gas, lots of dust, star formation is going on, young stars and old stars. Okay. Another barred spiral showing star formation in young stars. There's one I use for a lab that I've used frequently. It's a very pretty barred spiral. Here's another beautiful barred spiral that kind of has a ring around the bar, which is interesting. And another barred, and another wonderful barred spiral. There we go. Let's keep going through. And now we get to the second to last of our classifications, the irregular types. And basically, they look like train wrecks. An irregular is not an elliptical, it's not a spiral, has no spiral structure, but they tend to have a lot of star formation going on in them, the irregulars. They look like messes, and these are the two large and small Magellanic Clouds. Now, they're together in the sky, and this is a ground-based photographic view, but then when we take these amazing views of the Large Magellanic Cloud, we see that there's lots of gas and dust, that there's star formation going on, and there's a lot of activity. So there's a huge amount of interaction going on inside of this thing. It's a turbulent place where stars are being born everywhere. The Large Magellanic Cloud is about 200,000 light years away. And so we see everything we see in there, the light has been traveling for about 200,000 years to get to us. Same with the Small Magellanic Cloud. This was taken by Stefan Guissard. And I've just got to mention that. I'll find the link for his work and put it on the YouTube channel. But again, this is Stefan Guissard's image, and we see the Small Magellanic Cloud is here, but just to the left of it is a globular cluster that's part of the Milky Way, and below it is another globular cluster, part of the Milky Way. So the globular clusters are, comparatively speaking, on the order of tens of thousands of light years away, but the LMC and SMC Small Magellanic Cloud are about 200,000 light years away. So that means for it to be that big, it must be really huge compared to something that's 10 times closer. So if the Small Magellanic Cloud were at the same distance as the larger globular cluster, it would be 10 times bigger in the sky. So those are big, 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 big things. And that's also a place where star formation is going on. An interesting irregular, which is the active galaxy M82, and I showed you M81 and its neighbor M82. It has some strange structure. You could think that maybe it was once a spiral galaxy, but it has this it has a dark dust cloud going across it, and then if you take a deep image, and this is a deep Hubble Space Telescope image, that pink glow is ionized hydrogen gas, and the outflow is going at tens of thousands of miles per hour, miles per second actually. It's going extremely fast. These winds have been driven, and it's being driven out to tens of thousands of light years, up to over 10,000 light years long, some of these filaments. And M82 is the brightest galaxy in infrared in the entire sky. And what has happened is that there's an enormous amount of star formation happening inside of this galaxy, and the combined winds of all those super bright O and B type stars creates enormous winds, and those enormous winds drive the gas, and so the gas is being driven out of the galaxy by the formation of the stars. And this is an interesting combination of X-ray, of optical and infrared imagery of the same galaxy, and it just looks kind of like a crazy, crazy, crazy thing. So, all right, the center, and this is a more standard sort of appearance, NOAO ground-based image, and then using the Wide Field Planetary Camera 2 from the Hubble Space Telescope, we get the interior of a dusty, dusty area where lots of star formation is happening at M82. And there it is once again in the sky. A few years back, M82 had a prominent supernova that went off that we'll talk about in the future. It's a very, very nearby one, but it was a distinct kind of supernova that's called a Type 1a supernova, and it was very important to help us even more land down the nature of the distance to M82. But you can see in this full color image that the hydrogen gas clouds are there. And yes, M81 on the left and M82 on the right are distinctly interacting. M81 on the left is much more massive than M82, and the interaction has caused M82 to go into a massive amount of star formation as M81 buzzes by. They interacted probably about 10 million years ago or so, and they're at roughly the same distance from us, at about 12 million light years away. So their relative distance between each other is actually quite small. So that's interesting. The interaction that they had, very deep images, show that they're still interacting, and that there's a line of hydrogen gas binding between them that can be seen in the radio wavelengths. And here's another disrupted, sort of irregular, gosh, they look all crazy. Oh, here's another irregular, they just look like train wrecks, like something's really went wrong, like mistakes were made. And here's a dwarf irregular, and here's another flavor of irregulars that kind of looks like a barred spiral galaxy, but in the center we see active star formation in a ring-like structure. And here's another strange-looking irregular called Hoag's object, which is a Hubble image, and so star formation in a ring. There's another one, the center of NGC 1512, which is a ring-like structure. This galaxy has a bar, and then that bar has a ring, and so it's kind of a double-ringed galaxy, so we'll call this an irregular. another irregular ring structure. And then you get the really strange ones, which are the dwarf irregulars, which are just complete little tiny train wrecks. And they're almost impossible to image because they're compact, dim, small, and difficult to observe. As you can see from these things, they're practically not even there. And the Sagittarius Dwarf Irregular Galaxy orbits our Milky Way, and it's so gossamer that it basically you can see through the galaxy to the other side. So what exactly holds this galaxy together, and what exactly is the lowest boundary for a galaxy? This is an incredibly important topic for, say, the study of dark matter. How does dark matter cluster? And so there must be an enormous amount of dark matter there to keep the Sagittarius dwarf around. And here's a couple of other dwarf irregulars, and you can see active star formation occurring in them. And they're also sites where they're basically train wrecks of interaction. And here's another dwarf irregular galaxy. These are very tiny objects. They tend to have only a million, on the order of millions to tens of millions of stars on their sizes. And they're typically distorted in shape like these are, and they typically have a lot of hot young blue stars in them. All right, so here's some statistics on the nature of the ranges of galaxies. So we look at spirals in blue, and they tend to be on the order of 1 billion or so solar masses up to 1 trillion or so, just over 1 trillion solar masses, or 100, or just under 1 trillion solar masses. The largest, but ellipticals have an enormous range, down to about 100,000 stars, 100,000 masses of the sun. That's what the M sub sun means. It means mass. That little target is a symbol meaning the sun, and M means mass. So we're doing this all with respect to the mass of the sun, and that means that ellipticals span from 100,000 times the mass of the sun up to 10 trillion times the mass of the sun for the giant ellipticals. And irregulars are kind of an in-between group that go from about 1 million times the mass of the sun to some of them can be as large as other spiral galaxies and larger than many spirals. So irregulars kind of span the gamut between them. Now, if we think about the luminosity of them, the luminosity is in different range altogether. Spirals go from about just over 10 million times the luminosity of the sun up to just under 100 million times the luminosity of the sun. Whereas ellipticals range from 1 million times, which is much dimmer because they can be smaller ones, all the way up to 1 trillion times the luminosity of the sun. And irregulars are down there in the tiny ones, so irregulars tend to be much smaller. So that's because ellipticals range in size and mass. And now we think about the diameters of these things, and this is where it gets really dramatic, is that spiral galaxies are on the order of 5 kiloparsecs, or about 15,000 light years, up to about 150,000 light years across, with the Milky Way being about 100,000 light years across. So the Milky Way is on the larger end of the spiral galaxy size. Irregulars are all tiny little things that range from that are almost like 10 times smaller than the Milky Way, up to down to 1% of the size of the Milky Way. But ellipticals can range from being really tiny things to catastrophically large things that can be up to 10 times the size of the Milky Way. And the largest galaxies known are all giant elliptical galaxies, which make the spiral galaxy Milky Way look like a tiny, tiny, tiny little brother. So the structure and nature of galaxies are that spirals have a disk, they have a spheroidal component, they have rapid rotation, and the spheroid is puffed up because of the random motions down inside the bulge. Elliptical galaxies, though, are only spheroid, they're only old stars, there's no gas or dust, and spirals do have lots of gas and dust, which we see with the rotation. And all of the rotation of ellipticals is just mostly random, and there might be some slow overall rotation, but the random rotation of the stars dominates the appearance of the Doppler side. So basically, if you look at one side of an elliptical compared to the other, you're just not going to see that there's one side is approaching you and one side's going away. Spirals, on the other, however, if you can get an edge on, one side's coming towards you, one side's going away. And irregulars, they're just a mix. They're chaotic in structure. They have tons of blue stars and some rotation maybe, but there are lots of chaotic motion, so they're stirred. All right, and spirals, in terms of how many stars and gas there are, spirals are about 10 to 20% gas, a huge amount of hydrogen gas. Lots of star formation is going on in the disks, and there's a mix of the, I remember Walter Baada's combination of population 1 and population 2. There's a mix of population 1 and 2 stars, meaning some old stars, some really ancient stars, and some really new stars. Ellipticals, there ain't no gas nor no dust. And star formation ended a very long time ago, and there's only population 1 stars. Meaning, even if you take a spectrum of it, you find that even their chemical composition is ancient. Irregular galaxies can be almost all gas, and so there's huge amounts of star formation going on because tons of gas means tons of things that you can make stars out of. So they're pretty much, you see only population 1 young stars, meaning O and B and A type stars, or F and Gs, sure, but dominated by the bright ones. And dwarf ellipticals, they're very, very, very metal poor, and so they may very well be, because of their low mass and small size, are just finally getting to the point where star formation can begin since their formation over 12 billion years ago. So that's really interesting. Dwarf galaxies are most common in the universe by number, but not by mass. They're all, and all of these are either small ellipticals or tiny irregulars. There's no spiral dwarfs, meaning little tiny dwarf galaxies. So remember all those images I showed you with there's little tiny spirals? They're far away, that's what we mean. And the dwarf galaxies might be just smaller versions of the larger ones, or they're a completely different population of objects, and they seem to be the same, but yet the dwarf galaxies might just have the similar appearance to them, just scaled down, but their exact nature is an area of active study. The most important element, though, and the takeaway of this is, though, that we're going to take in the future, is that galaxies are the basic units of luminous matter in the universe. They are, by basic, what we mean is that they're the things that when we say we're looking at a supercluster of galaxies or a galaxy cluster, now we're not looking at individual stars, we're looking at groups of galaxy clusters, which then also group into groups of groups called superclusters, or just a really big group of galaxies. And so where you find star formation in the universe is in galaxies. Star formation doesn't occur outside of galaxies. Star formation only occurs in galaxies. So therefore, galaxies are the place where heavy elements other than hydrogen and helium are formed in the entire universe. And so we've got to find that the different kinds of galaxies mean that there's something different by how they formed and how they evolved and where they live. And that's what we're going to talk about when we talk about the structure of the universe. This time we're going to be talking about colliding and interacting galaxies. Last time we were looking at the Hubble classification of galaxies and saw that many of them look distorted or messed up in some way, and those are the peculiar galaxies. We also indicated that possibly galaxies are forming by collisions and mergers. So now we're going to see how that actually works. All right, so the first step to think about is that galaxies fill the space around them. Unlike stars inside of galaxies, because remember, galaxies are made up of stars, hundreds of billions of stars, such as these two examples that we see here. The examples that we see below have a huge number of stars in them. Though the fuzziness of a galaxy isn't because it is gassy, well, it is very gassy, but it's because of the collected illuminated light of all the hundreds of billions of stars within them. But the stars themselves don't touch. They're separated by roughly 10 million times their sizes. So stars are incredibly far apart compared to their sizes. However, galaxies, which are assemblages of stars, are actually separated by roughly only about 20 times their diameter. The Milky Way and Andromeda galaxies are roughly about 100,000 light years across and are separated by 2 or 3 million light years. So therefore, their distance between is only about 20 times their diameter. So that means galaxies are very likely to encounter each other and collide, unlike the stars that make them up. All right, so The way we will indicate that we understand how things are going are by tidal interactions. And so all interactions that galaxies do, it's not the electromagnetic force or the weak nuclear force or the strong nuclear force or I don't know, Sailor Moon force or something. You can make it up. But they interact via their gravitational pull between each other. They're extraordinarily large, and because of that, the near side gets pulled on by more than the far side, and so they get stretched out. So the tides distort the shape of the galaxy. When we say tides, what we really mean is the differential gravitational pull, or the difference in gravity pull between one object and another compared to their center of mass. So peculiar galaxies occur in interacting pairs. That's very frequently what we see. And so here's that image again. We see the two spiral galaxies interacting, and there's another pair of spirals from the Hercules cluster of galaxies. And this is what we might think of as a high tide. Notice that the whirlpool galaxy seems to be elongated towards the elliptical with which it's having an encounter. So it's getting squished along the line of sight and switched towards the line between them and stretched along the line between them. And in so doing, when there are interactions, you should expect to see massive amounts of star formation, which is what you do. See all those pink glows? That's because the gravitational pull between the shocks that are occurring because of the tidal interactions are causing the gas clouds to merge and collide and form stars rapidly. So you get tidal stretching along the line between the two of them. And that's what we see with the ARP-87 interacting galaxies. And when they're called, this group is called ARP because after Halton ARP, who is an amazing observer, and he found a whole bunch of very, very strange things. So if you look for the ARP catalog of galaxies, you're going to see all sorts of really interesting, peculiar galaxies. All right, so here's another peculiar galaxy called the Tadpole, which has an enormous tidal tail. And then we see the Mice, which also has an enormous tidal pair of tails as they're interacting. And notice you have a huge number of blue stars, and then you have these yellowish cores, which are in the process of merging. And here's another beautiful interacting pair as they swing around each other. These interactions take quite a long time. They'll take up to 1 billion years or so to fully complete. And it's important to remember that we see stars also. The stars have spikes, and the starry spikiness that we're going to see here, those are all foreground Milky Way stars. They are not distant. They are distant in the sense that they're tens to thousands of light years away. But the fuzzy clouds that look like the galaxies, those are millions of light years away, or tens of millions of light years away. And if you look very carefully at these images that I'm showing you, you'll find that there's actually little tiny galaxies far, far, far in the distance that are extraordinarily small, and they are much more distant galaxies, maybe 100 million light years away or greater. All right, here we go. So computer simulations show that they take about 1 billion years to conduct this dance of collision. So this is not a fast thing, even though they're traveling at hundreds of kilometers per second or up to thousands of kilometers per second. The sizes are so enormous at hundreds of thousands of light years across that it really does take billions of years for the interaction to occur. And so you take the simple rules of Newton's laws of motion, you take his law of gravity, you plug it into a computer, you then try to take into account other things, say dark matter, which we talked about with the Milky Way in the previous lecture. But if you take all those things into account, then you see the shapes occurring. So if you have taken into account all of the mass, all the underlying mass, and then look at tracking the individual particles, and you might call clusters of stars particles or big clouds of gas particles, and then if the models match the observations, then we know we're on the right track. Some number of them that occur that people have done, Dr. Dubinsky over at Canadian Institute of Theoretical Astrophysics has created a wonderful series of videos that you can go check out. There's his website. And there's others that occur as well, and direct galaxy collisions are really, really, really pronounced. When they occur, and when you have very, very tight collisions where the cores come very close to each other, there's a huge amount of what we call starburst activity. And starburst activity means the clouds of gas and dust collide and get overdense and form stars very, very, very rapidly. All right. So what they did with the whole group is that this set of images was used to kind of help guide that group of that simulation that we saw. So Summers took these images and rotated around, and basically this is what you get when you take a couple of spiral galaxies that are similarly sized and just slam them into each other from various angles. The disks of the galaxies get distorted, tidally disrupted, and all depends on the orientation that they come in at. So this is what they look like when you have two radically interacting galaxies. And we see that now that we have a good computer simulation that seems to be doing exactly what we see in nature, we think we're on the right track. So there's a good close-up of one of them showing the starburst activity in the ring formation, and another one that shows more star formation in both of the galaxies. And here's one that's showing incredible tidal disruption. Again, look at the tiny, tiny, tiny distant galaxies far, far away in the background. We can see that the blue stars are actually being stripped away from the center and actually sent out, way out and away from the tidal interaction. So the gas clouds had formed, and the blue stars were essentially just left behind as they are forming. So we can see that the interaction is happening on the order of hundreds of millions or tens of millions of years, because those blue stars trace out a time frame about 10 to 100 million years. Okay. Here's another one we see where the intense star formation actually happening right in the center. And then finally, here's another gorgeous pair that show interaction and star formation all throughout it, with the hydrogen gas clouds going pink, the blue star clusters appearing all over the place. And we can tell that this is extremely distant because they're out of focus. Or more specifically, they're not resolved. And since they're not resolved into individual stars, those blue dots aren't individual stars, but huge groups of stars, many thousands or tens of thousands of blue-type stars being formed all at once. And here's ARP 273, sometimes called the Rose, which is an enormous, beautiful looking interacting pair, and we can see that the Hubble Space Telescope image can certainly bring out the more interesting aspects to it. And this is the Stephan's Quintet, which is actually four interacting galaxies, and the bluish one is in the foreground. But the four interacting galaxies are certainly having an extreme interaction with respect to each other. And if we rotate around and look at this image from a slightly different angle, this is the Hubble Space Telescope image merged with the Chandra X-ray image. And if we go back and forth between the Chandra X-ray image and the optical plus X-ray image, we see that the hot X-ray gas is being created in that area where the stars are forming extraordinarily rapidly. So X-ray emitting gas is being heated to tens of millions of degrees as black holes and neutron stars are being formed in great rapidity there. So you can have ring-like encounters as well, and if a small galaxy goes smack through the middle of it and hits a bullseye, then you can create a circular wave of star formation, such as we see here. And this is a Hubble Space Telescope image that shows a very, very, very violent interaction between a little galaxy that literally went smack through the center. The little galaxy got completely disrupted, but it sent shock waves through the rest of it, which then filter out through the rest of the galaxy and form a ring, sort of splash-like ring of star formation. And we see ring-type galaxies all over the place. There are many examples of ring galaxies that must have had very, very close encounters with smaller galaxies that are then disrupted. And there's another one, ARP 147, that shows a ring-like structure, as well as another ring, a double ring type structure going through. Starburst galaxies are another classification that we have, and that's what we really are calling these things. And starburst galaxies can be seen by their spectra as well as by their images. And starburst galaxies create huge, huge, huge output, and that enormous, enormous output. What it'll do is it'll create very, very short-lived O and B type stars, which are incredibly hot and luminous, and they make the galaxy extraordinarily bright. And what happens is, though, that these O and B stars make shock waves that cascade through and burn up all of the gas in the galaxy within a few million years, leaving it with some blue patches, but then a bunch of red stars. So effectively, they wipe out all of all of the gas that's left in there, and the supernovae that are triggered by these O and B stars within a few million years create enormous winds that blow the gas and dust out of the galaxies. And so intense star formation also comes with enormous winds. And this is the antennae, which are a very fast interacting galaxy group. And the core of the antennae shows a vigorous star formation. We can zoom in on this Hubble image and see huge scads of blue-type stars, red regions of star formation, where H2 regions, these pink glowing clouds, where H2 regions indicate hot ionized gas, and then we have extremely turbulent areas where lots of gas and dust are forming many stars extremely rapidly. And they will form shock waves and supernovae, which will blow the gas out of the entire galaxy very soon. And here we see a region that is coming out of a density wave and forming huge numbers of O and B type stars. And the pink glows, of course, hydrogen. The dark areas are dust, and the glows of the stars are actually tens of thousands of hot O and B type stars, all seen in one galaxy group called the antennae, the core of a pair of interacting galaxies. And here it is also in the ALMA array, which is in microwaves, which will show where a lot more gas and dust are. All right, so another great interacting pair is M81 and M82, and they are a classic interacting pair of galaxies. Sorry about that. They're a classic interacting pair of galaxies, M81 and M82. They're about 12 million light years away. The one on the left is M81, the one on the right is M82, and the one on the left is sometimes called Bode's Nebula. And what we see is that they have recently interacted, and deep imagery also shows that the two of them have a gas streamer between them. But we can see in pink hydrogen off to the right some huge super winds coming off of M82. And now we're going to focus in on that, and the active galaxy M82 that we just saw in the other image, we just rotated around and zoomed in, and the Hubble Space Telescope took a series of interesting images of it. And that pink glow shows enormous winds coming off of M82, and that is all hydrogen gas. It's being blown out by the star formation and shock waves from previous supernovae in huge numbers, maybe thousands upon thousands of supernovae that are happening all within the last few million years. There was a Type 1a supernova that just occurred a couple of years ago in M82, but that's probably part of the residual of the formation of such things. So keep watching M82. It's actually something you can see with a small telescope in your backyard. It's not that dim. It's actually something you can see very easily with not necessarily binoculars, but definitely an 8-inch scope can definitely pick it out of the sky. So when do galaxies merge? If they collide and there's enough dissipation of the orbital energy, meaning they don't get flung apart, they don't swing around each other, not going so fast that they just swing by, then eventually the angular momentum gets distributed throughout the entire system and distributed out, and it can lose that orbital energy by dispersing the stars that make up the components. That then makes the gas clouds collide, that forms new stars, and then the entire thing merges into one thing, one big galaxy. So mergers appear to play an incredibly important role in galaxy formation and evolution. In fact, we think that the Milky Way was formed by a construction or a collision of many small little galaxies over its 10 billion year lifespan. And if we think about it, we even now know today that the Milky Way has stellar streams that we talked about in the formation evolution lecture previously, and that is, we would call it galactic cannibalism. So if you have a slow encounter between a large and small galaxy, the smaller one gets torn apart and slowly merges in. So it's not like you get this ring effect, but the little one comes in nice and slow and just gets shredded apart as it comes in slow. So giant ellipticals also may grow by the fact that if you take very large galaxies at very slow motions, then they will actually come together relatively slowly and their cores will stay intact, and that will create a giant elliptical galaxy. So here are some other processes of galaxies that are in the process or the final stages of merging over the next 100 million, 200, 300, 500, 700 million years. There's another one where we're showing two tidal tails that are coming out and the cores are almost completely merged. And here's one that was showing two spiral galaxies in the process of merging. They're just begun that. I think we showed that one earlier. And here's one from the Swift telescope. And the Swift telescope sees things in ultraviolet. So what we're seeing is when we see, this is a Higgs compact group, one of them, I forget which one, but this particular compact group shows enormous numbers of blue hot stars being formed in the ultraviolet. So we can see that ultraviolet is emitted by O and B type stars, and that's what this mostly picks out. So we're looking at extraordinarily vigorous star formation of young stars. And there's another one, kind of a fuzzy one, I don't know why I threw that in. And we have a ring-type galaxy, a polar ring-type galaxy, where you have some sort of a pair of rings pulled together, and this is another Hubble image of a pair of interacting galaxies. And this is a really beautiful one that kind of looks like a pair of owl eyes as they are interacting together, and as they collide together, they're going to distort each other over the next billion years and form one big galaxy. There's another one with a ring-type structure that happened as these two galaxies collided and formed enormous star formation in the ring. There's another one we see off to the side, and some other tiny galaxies all around it. There's a good one that's another ARP interacting galaxy, and so on, and so on, and so on. Part of the reason I'm showing you all of these things is because there's a visual vocabulary that comes with astronomy. And the visual vocabulary is so exotic. These pictures could be hung in museums. And in fact, look at this one. This is absolutely gorgeous. Most of the stars, the points, are actually stars of the Milky Way. But we're seeing a pair of interacting galaxies far, far, far in the distance, millions of them, 10s or 12, 20, many tens of millions of light years away. But the stars in the Milky Way are in front of it, and they're only hundreds to thousands of light years away. There's another one, and they're very fascinating things, but also look at the distant ones in the background. When we said that galaxies make up most of the universe, we really do mean that. And so we see that these objects, they're not little galaxies, they're far galaxies that look little. And that's what's interesting about these clear sky ones that are looking up away from the plane of the Milky Way. You see interactions no matter where you look. In fact, peculiar bright galaxies are happening all over the place. This visual vocabulary serves to show you how many things are in the sky and what we can see, and that galaxy collisions are extraordinarily common. And as they occur throughout the history of the cosmos, they build up larger and larger and larger galaxies until we get to things like Milky Ways and so forth. And this is an enormous, enormous study that can be done of many, many, many galaxies. There are hundreds of millions of galaxies in the cosmos. And as we look out in that, we see huge numbers of them floating around. And wow! But we talked originally about the collision between Milky Way and Andromeda. Right now we know the Milky Way is approaching us at about 120 kilometers per second. And so in about 3 or 4 billion years, the Milky Way and Andromeda are going to collide. And they're going to tidally distort and merge after about 1 billion or so years. And the giant elliptical that should remain will be called Milkomeda. John Dubinsky has a really great metamorphosis that shows this, and it's a wonderful, wonderful image. I invite you to go check out his website. But I'm going to actually go with the Hubble Space Telescope group that showed exactly how we know this. And we look at the Andromeda Galaxy, and if you look at the edge of the Andromeda, way away from the distant, from the bright core, but way out in the outer reaches, many of the stars that are in the tiny area have a significant amount of proper motion. There's proper motion to them. There's a Doppler shift to these stars that are in this field. So many of the stars in the highlighted area are actually part of the Andromeda Galaxy, not part of our Milky Way. So if we zoom in and look, we can see there's some background objects too, but inside of this study, there are about 10,000 stars from the Andromeda Galaxy. And inside that one little field, this one field, there are over 200 distant background galaxies. So if you go hunting, you can find them literally everywhere. And that target field, by comparison, is just about the same size as one of the large mare on the moon. So the moon itself would cover up hundreds of thousands of galaxies every night as it passes through across the sky. All right, so how do they do this? Well, over time, they took a series of observations to see how these things had moved. And so there was some motion of them with Doppler shift, as well as a proper motion, meaning a motion across the sky. And all you have to do is and if it's a fast enough motion, meaning, well, if you're coming 120 kilometers per second, you should see something. And so it's just separated by about a decade or so, 5 to 10 years. You should see some motion of the Andromeda stars relative to the 200 distant background galaxies, because they're going to be fixed. They're not moving anywhere. Or they are moving, but they're so far away that their motions are incredibly tiny compared to the stars in front of them. And the stars in front of them should have some uniform motion. And we're just trying to measure that uniform motion. And as a result of that measurement, it was discovered that the Andromeda Galaxy was moving approximately 120 kilometers per second towards us, and we will have an encounter with it in about 3 billion years. And so the group made an interesting video to kind of show you the encounter as it will occur in the distant future. The Triangulum Galaxy is a satellite galaxy to the Milky Way and Andromeda, and eventually will end up being a satellite galaxy to Milkomeda. And what's fascinating is there is the encounter that we saw that's very similar to the encounters that we saw in many, many other things. So Milky Way and Andromeda will take over 1 billion years. Look at the time frame that's occurring. It's already a 500 million years to go through after the first encounter. And now it's 1 billion years later where the two cores get close, another 500 million years just for them to merge completely. And notice they went from kind of blue to now yellow, as all the stars were burned out that were young and hot, and were left with only the red dwarf type stars in copious amounts. And so after about 7 billion years, well after the sun has died out and become a white dwarf, Milky Way and Andromeda will have collided together and formed one huge giant elliptical galaxy. And so this is some of the things that if Earth were to have survived, this might be the view that we would see. Here is the view from the present day with the Andromeda Galaxy very far in the distance, with our Milky Way in the foreground. And then in about 2 billion years, the Andromeda Galaxy will be enormous. It'll be much larger than the moon in the sky. It will be quite a picture in 2 billion years. In about 4 billion years, it will span most of the night sky. And when the Andromeda rises in the sky, it will be an astonishing view. And very soon thereafter, the tidal distortion will be occurring. There will be huge amounts of star formation as the Milky Way itself gets distorted. Orion nebulas will blossom in the sky, and there will be numerous supernovae to keep everybody distracted. And then when we look at in about 4 billion years, there will be so much star formation that people will be able to read by the numerous supernovae that are occurring in the sky, whose light will last for months. And so there will be a strange element of lack of night due to all of the bright stars in the sky. After about 4 billion years, the Andromeda Galaxy will have passed by, and we'll see an enormous, a tidally distorted Milky Way, all messed up, with Andromeda not looking half as beautiful as it did. That gray just looks kind of old. And then finally, about 5 billion years ago, 5 billion years from today, the cores will get closer and closer together, and eventually, in about 8 billion years, or 7 or 8 billion years, there will be a giant elliptical galaxy. There will be no more Orion nebulas. They will be gone. There will be no more Tarantula nebulas. They will be gone. They will all be gone in a huge burst of star formation with no gas or dust, but just this yellow glow of billions upon billions of stars in the sky. And that's the future for the view of the Andromeda Galaxy. And this came from NASA and the Hubble Space Telescope, and the group with LeVay and Vandermeer and Hallis and Mellinger over at NASA at Space Telescope. So just go take a look at those wonderful videos that are on that. I provided a link there at the bottom. And here's some interesting review questions for you to go over. We just looked at the Milky Way and the types of galaxies in the cosmos, and then we looked at the interacting galaxies, and we mentioned that galaxies are really big compared to their sizes, but we also saw that galaxies in the distance are really, really far. And I asserted in the previous lecture that in the interacting galaxy images that we saw, that huge number, we saw lots of little galaxies at extraordinary distances, and I gave numbers like hundreds of millions of light years or billions of light years distant. So really, nobody's ever been there. So how do we know those distances? And basically, now we're getting close to the beginning of the study of cosmology. Cosmology is the study of the entire universe. And we're going to be looking at the physics of the whole universe, how things are distributed on big scales, how things move on big scales, how the universe has changed from the beginning of time to the future, and what the age of the universe is, how it began, and what ultimately it will become. So cosmology is broken up into four big pieces. There's four pieces, but I call zero homogeneity isotropy because it's kind of a zero thing as its underlying assumption. And we're going to look at mostly number four, and getting to know number one. Number one is redshift, which is the key way that we know of distances in the Big Bang. And again, we always must remember the cosmological principle says that there's really nothing special about our location. It's just our home. That makes it really special because you can't quite live on a white dwarf and you can't quite live on Mars yet. I mean, maybe someday Elon Musk will take us there. And we don't live on Pluto yet. We can't travel between the stars yet. So our place is our home right now, and that makes it special. But we apply the idea that really the laws of physics must be the same everywhere that they are here. So with that idea, and we look around on the cosmos, the cosmological principle says there's nothing special, meaning we're in no other different place. But yet you notice that when we look in the sky, we see that basically everything in the sky is roughly the same thing in every direction. It's called isotropy. And if you combine it with the cosmological principle, it says that nothing's really special, then isotropy isn't really that special. So therefore, everything is pretty much homogeneous everywhere. And so that means anybody on any galaxy ever seen by anyone, if they have people out there on those distant stars, then they would see the sky roughly the same way we do. Maybe there'll be more galaxies, maybe less. Maybe there'll be more supernova, maybe more gas, maybe less. But they're going to see galaxies, they're going to see supernovae, they're going to see stars and planets like we do. So it's going to be the same stuff. So now we're going to look at how we know the distances to the galaxies. And so we start from the idea of Hubble's law. And Hubble's law is something very interesting that said, wow, we're going to get to it next time, really the detail about Hubble's law. But basically, Hubble's law relates the distance, d, to the recession speed of the galaxy, how fast its redshift indicates it's rushing away from us. And so it's proportional to, the distance is proportional to the speed v, the speed that's rushing away from us, which is inversely proportional to the Hubble constant, which is h naught. And that is for nearby galaxies. And for nearby galaxies, we can simply measure what's called the redshift. And the redshift is z. And z is the shift in the wavelength of light from its rest wavelength times the speed of light c, divided by h naught. So the trick is we've got to figure out how to get this h naught number, because how do we know what the heck it is? All right. Our goal is to find this magic number that gives us the distances to the far, far galaxies. And we'll just describe its origin next time. But there's no real way you can get it universally. I mean, it begins with extraordinary expansion, as we'll see next time. So we're going to look at the way we get up to redshift. And the idea of redshift was known for a long time, since the 1920s. That's how Edwin Hubble determined how far things are. But we're going to look at that more carefully soon. But there's no one single distance method that gets you everywhere across the entire universe. Some things are good for close things. Some things are good for far things. Some things are good for really far things that aren't really too far. And so we call this a bootstrap process. You pull yourself up by your bootstraps, and you get yourself out the door. So we find distances to near objects, and then you find something like that near object at a farther object that encompasses it or is next to it, and then you calibrate that you find some new way of seeing something that's farther and presumably brighter and easier to see than the thing that was closer, that was relatively dim and can't be seen from so far away. The trick is, though, and this makes it really problem, is that errors get made. Mistakes are made. So let's look at the nearby thing. Way back, we talked about Henrietta Leavitt's luminosity period relationship for Cepheids that she discovered. And that is one of the most important relationships, but it can only get you about 100,000 or so light years, or 150 million light years or so. And that's if you use the Hubble Space Telescope. But that's hard to do with the Hubble Space Telescope because you need lots and lots of time, hundreds of Hubble orbits, and that means you have to have one of the best reasons ever to actually go hunting for Cepheids in some really distant location, because the Hubble Space Telescope is an extremely expensive thing to run, and people don't give up their orbits very well, and you have to put in a decent proposal so that you can push people away, because there's only so many times that the Hubble Space Telescope can orbit the Earth in its lifespan. So use it wisely. Finally, Cepheid relationships only really work for spiral and irregular galaxies because that's where the star formation is going on. You got to have young, hot stars in order to make Cepheids. And so the farthest you can really get with Cepheids, since you can actually try to identify individual Cepheids, is about the Virgo cluster of galaxies, which is about 60 million light years away or so, 65 million light years away. That, at 65 million light years away, is very nearby in terms of the universe. All of the galaxies that we looked at in those interacting things are within 10 to 20 to up to 50 or 70 or less than 100 million light years away. And the things in the background were much further. So really we're trying to get to the grandest size scales, how we can know things that are billions of light years away, not just millions. So here is what we call the cosmic distance ladder, where we start with parallaxes, and use proper motions and main sequence fitting or cluster diagrams. Hyades is critical. Cepheids and Lyrae get you out to the Large Magellanic Cloud and out to Virgo cluster with the Hubble. And then you have something called the Tully-Fisher relationship and type 1a supernovae and other bright objects, which get you out to the Coma cluster, which is about 10 to the 8th parsecs. And then finally, you can really start calibrating the redshifts out there. All right, so our first step is measuring the astronomical unit, and we talked about this many times in the past. The AU is the average or mean Earth-Sun distance. It's about 150 million kilometers, and you measure by geometric triangulation. You bounce some radar off of Venus when it is at quarter phase, meaning you see Venus as half illuminated in the sky, and that means it's at a right triangle with respect to the Sun, and so you get an angle between the Sun and Venus, and that's not 90 degrees, but the angle between the Sun and your Earth make with respect to Venus is 90 degrees. Bounce some radar off of Venus because it's very reflective. Get you a distance to Venus. You can use high school trigonometry in order to get the distance to Venus. Now, Copernicus and many others have determined that the orbits of the planets have relative sizes, and you can look at the size of the orbits and their relative things and get all their relative distances. So the main thing to measure is the astronomical unit, because once you get that, then you can get the relative distances to all the planets. And if you determine the astronomical unit, you can get the trigonometric parallax to stars. And once again, way back, we talked about trigonometric parallax. You got to know the astronomical unit, which is the radius of the Earth's orbit around the Sun, and that allows you to calculate those little tiny angles that stars seem to make as the Earth goes around the Sun in a year. Remember that the typical parallax is always less than 1 arcsecond, and an arcsecond is about the same size as a regulation NFL football held 37 miles away. So that's a really small angular size. So the nice thing is that stellar parallaxes recently got a huge burst at 2016 with the first release of the Gaia dataset by the European Space Agency. And they've released their second data set recently, so there's lots and lots of data. Up until then, it was just ground-based stuff that got you out to about 100 parsecs, and Hipparcos satellite, which only got to about 1,000 parsecs. And now, with this data, you can get the absolute distances to things. If you can get absolute distances, you can use the inverse square law for brightness to get their luminosities. And so we can use that to get spectroscopic parallax. So what we do is we find typical clusters of stars, and the prototypical cluster is the Hyades cluster. And we make an HR diagram based on the difference in brightness in two colors, the B minus V, and two different filters, and compare it to the brightness seen in the V, that's a standard color magnitude diagram, or HR diagram. And the shape that it makes is the Hyades has a distinct main sequence, and we figure that all stars are the same in the cosmos. So if a main sequence is below another main sequence, that's because it's farther, not because it's a different kind of main sequence. No, it's just that it's farther. Maybe it's made up of a slightly different population, but that population would only but that doesn't account for huge differences in the HR diagrams. The major differences between the brightnesses of a full HR diagram between two clusters is because of the relative distance. And so diffraction limited viewing gets you out to see star clusters out to the Large Magellanic Cloud, which is about 100 kiloparsecs away, or thereabouts, and you can get to, and you can make out, and that allows you to be able to make out individual stars. You have to be able to make out individual stars in clusters to create an HR diagram. And roughly the distance of the Large Magellanic Cloud is the length. Now, it's good that the Large Magellanic Cloud is there because it has a huge amount of star formation going on. And because it's got a lot of star formation going on, it's got a lot of young clusters. If it's got a lot of young clusters, it's got a lot of Cepheids. If it's got a lot of Cepheids, then you can calibrate the Cepheids from that. So this is really good. So now we can look at the Cepheid variables, which are the next step up. And the Hyades gives us the basis for all star clusters, because now you can get the physics of the star clusters and you get the absolute brightness, because you can get because the Hyades are only about 150 light years away, and then you can use the Hyades to get other young clusters. Remember that Cepheids are supergiant stars in young clusters. They're about to die, and there are tons of these clusters, as I said, in the Large Magellanic Cloud. And since the LMC, once you're 200,000 light years away, 1 or 2 light years back or forth doesn't really matter. So what you do is you look at all the star clusters that you can find in the Large Magellanic Cloud, make a generic HR diagram out of them, and then fit that HR diagram to what you see for the Hyades. And if you can do that thing, then you can get the relative distance to the Large Magellanic Cloud. And if you can get that, then you can find specific Cepheid variables, which are much brighter than most of the stars in any of the clusters, and that allows you to match it up. So then you can get a calibration for the Cepheid variables. So these are so bright that they can get you out even farther than is possible with main sequence fitting. And so, but the thing is that you can only really get out to about the Virgo cluster of galaxies with Cepheid variables. That's about 60 million light years away. And you have to look in spiral galaxies because, there's got to be star clusters and there's got to be formation going on. Ellipticals don't have star formation, so you ain't going to find Cepheids. Funny thing is, though, is that spirals aren't as bright as the brightest ellipticals, and ellipticals are far more numerous. Okay, so there's our standard thing. The Large Magellanic Cloud is littered with them, and we've got to find more. Finally, next we keep going up in scale, and we're starting to get a little desperate now because, things that are really bright that can be seen for 70 or 80 or 100 million light years away, those things are pretty rare. They're by definition rare, but you got to take what you can get. And so maybe you can find type 1a supernovae, which are standard candles of some sense, because they happen in a very specific way as the star explodes, because the white dwarf explodes because it just gets 10 extra atoms of hydrogen on it and explodes exactly the same way each time. So therefore it's a type of standard candle. Now you can also get a relationship for planetary nebulae, which are the shells of dying stars. So the brightest planetary nebulae are probably at roughly the same brightness because they all come from roughly the same kinds of stars. So if you find bright planetary nebulae, you can make a relationship for their rough luminosities and get something out of that. Also, you can say, what are the distribution and sizes of globular clusters in the Milky Way? And by studying globular clusters in the Milky Way, you can determine roughly how globular clusters go in terms of their luminosities. And so hopefully you can make out something with that. That's all some tricks though, but the real thing is we got to find Cepheid variables to get to spirals and hope you can find something in there in that spiral that helps you. So these things mix and match and max and mitch, and basically Cepheids are the most important thing. But the good thing about getting out to the Virgo cluster is it starts to the very beginnings of getting us a local estimate of the expansion rate of the cosmos. Now the Virgo cluster is approaching, the local group is approaching the Virgo cluster, so it's a little tricky and you got to take into a lot of motions and things like that, but we're getting close. Now then we can do a new thing, is once we have a distance to the Virgo cluster, we can assume that galaxies are similar objects to nearby ones. Remember when the Herschels did star counts? Well, people do that with galaxies too. And we assume that certain kinds of galaxies are certain kinds of luminosities, and it gets kind of dicey. But if you look at enough of them, you can find correlations between luminosity and some distance-independent property. And large samples also help you remove the Doppler effect due to redshift of the motions of intrinsic galaxies during their space. And that's called their peculiar motion. Finally, there's two major things that are looked at, and they're called, one of them is called the Tully-Fisher relationship for spiral galaxies, and it's found that spiral galaxies have a luminosity that's related to their rotation speed. And you can use 21 centimeter radio emission in order to determine the rotation rate. And that's a very specific wavelength, and it's not littered with a bunch of other stuff, and 21 centimeter is pretty bright and can be seen for a very great distance. Also, there is a relationship in elliptical galaxies between the absolute luminosity of a galaxy and the line widths of the absorption features inside of the elliptical galaxy. So you can measure the absorption line widths of the spectra, and the absorption line widths are a measurement of the random motions of the stars in the elliptical galaxy, and the more random motions there are, the broader the lines. The broader their lines there means more motions, which means that there's more gravity. If there's more gravity, there's more mass, so you can determine a relationship between, if there's more mass, then there'll be more luminosity. And if you get an HR diagrammy of a kind of a population 2 sort of thing with all these ancient galaxies, then maybe you can make a relationship between the width of the absorption lines of an elliptical galaxy to its absolute luminosity. And that's also how we get the large mass differentials between them as well, is by looking at this particular relationship. So let's go back to pretty pictures, because pretty pictures are always fun. This is a wonderful image of the Virgo cluster of galaxies, which is in the constellation, of course, of Virgo. It's about 70 million light years away. But let's zoom in on the center of it. And if we zoom in on the center of it, we find we have a couple of ellipticals, but we have a few spiral galaxies. And those spiral galaxies, we can measure their rotation speeds. And why do we measure their rotation speeds? The faster they spin, the more massive they are. The more massive they are, the more stars they have. The more stars they have, the brighter they are. This particular thing only works with spirals, and the Virgo cluster has a number of spiral galaxies. So the Tully-Fisher relationship, which is a distinct relationship between the rotation rate of a spiral galaxy seen edge on and its luminosity, therefore its mass, is actually something that is very important in looking for distances to clusters of galaxies and individual galaxies too. So the Tully-Fisher relationship works for spirals, and all of these spirals can have their distances measured in this similar way. And we have, of course, our face model from whatever magazine, finding that in 21 centimeter radiation, exactly what happens, how do we measure this thing, is that the spiral galaxy, the hydrogen gas, is emitting at a specific wavelength of light. And each of the three little graphs shows the wavelength that it's emitting in a narrow band. However, if it's approaching us, if it's in a gas cloud that's approaching us, the frequency of the 21 centimeter radiation will be blue shifted towards a shorter wavelength. Maybe it's 19 centimeters. And if it's in the center, it will be unshifted, so it stays at 21. And if it's redshifted, maybe it's 25 centimeters or 23 centimeters or something like that. And so when you add up the entire thing, you can't necessarily make out the entire galaxy unless it's very nearby, say in the Virgo cluster. Then you can say, oh, this is a spiral galaxy. It's got a really broad emission line. If it's got a broad emission line, because you add up all this stuff together, then you see that it must be rotating fast. And the faster it's rotating, the brighter it is, because the brighter it is, the more massive it is. The more massive it is, the more stars it has. And for spirals, that means bright stars and O and B type stars. All right, so the Tully-Fisher relationship is probably one of the most important relationships that is used for cosmic distance studies, because they're very, very bright. You don't have to wait for serendipitous things like supernovae, and you can't try to hunt out and scour out a whole bunch of tiny little point sources like planetary nebulae or bright supergiants or something like that. No, you just say, find me some galaxies. I'll take their rotation rates, and I'll try to get a relationship between them. And so Tully and Fisher made a lot of hay out of this thing. And so all you have to do is calibrate it with a whole bunch of different relationships, and utilizing the distance to the Virgo cluster and calibrating the Tully-Fisher relationship using that. And then all you do is say, okay, what's the rotation rate? And determine that the faster it's rotating, the more massive it is. The more massive it is, the more luminous it is. And so we can get the luminosity in terms of comparison to the sun. All right, once you've calibrated the Tully-Fisher relationship, you may keep going further to find things that are even brighter than spiral galaxies, because maybe that 21 centimeter line is dim or fuzzy or hard to find. And those things are like a type 1a supernovae. And with all of that, then we can finally get out probably to redshift, and all these things get you about 1 billion parsecs, or a gigaparsec. And the last thing you're hunting for is redshift distances. Redshift is the thing that comes after everything else. So remember, each one of these steps was calibrated on the feet of the one before it. Each step depended on accurate measurements of the one before it. And so you're trying to measure that finally, if you can get accurate distances to far galaxies, then if you can measure their redshifts, we find that the farther away the galaxy is, the greater the redshift it is. So we can then estimate, like we had that equation right back at the beginning, where we said, what's the distance? It depends on the speed with which it's rushing away from us. And in nearby galaxies, out to a few 100 million light years, maybe half a billion light years, it's pretty much a linear relationship like we saw. So the Hubble relationship is a measurement of the expansion rate of the universe. And so all we have to think now is that the redshift is a good distance indicator, because the farther away they are, the faster they're rushing away from each other. And now once we've calibrated the Hubble relationship, we can then measure things, the distances to very far galaxies, simply by taking a spectra and seeing what the redshift is. So all of these things are critical measurements, and of course the most critical distance is to the Large Magellanic Cloud, which calibrates the Cepheids, and the Cepheids then get tweaked because maybe we find a type 1a supernovae floating around, and that's really important because those are extraordinarily bright beacons that can be seen up to billions of light years. And since it's about not Doppler shifts, we have to actually understand how galaxies are moving in space, because we need to study, because they're not just standing still, they are moving. Like the Andromeda Galaxy and Milky Way are going to collide in 4 billion years, in about 4 billion years, so galaxies are on the move, and that can add to the Doppler shift. So the nice thing to know is that lots of different measurements and lots of different ways to calibrate the redshift relation give almost all the same results between 60 and 67, 69 kilometers per second per megaparsec. Therefore, what this means is every megaparsec, every 300 million light years, 3 million light years, every 3 million light years, a galaxy is rushing away maybe 70 kilometers per second faster. 6 million light years, it's rushing 140 kilometers per second away. At 10 million light years, it's rushing, 30 million light years, it's rushing 700 kilometers per second away from us. So the faster it's rushing, the farther it is. And what's nice is, there's many ways to measure this, and they're really close to each other. So here's some recent stuff, the most recent major work that's been done. The first was in 2012 by the WMAP probe, the Wilkinson Microwave Anisotropy probe, and they quoted the expansion rate at about 69 or so, plus or minus 0.8. So you can see what the error bars are. It just demonstrates how well they know their data. And so that's about 69-ish or so, and it's pretty good, and these are incredible measurements. We're in the era of precision cosmology. David Spergel would get mad at me for calling it pretty good. This is an astonishing achievement with the WMAP. And then European Space Agency's Planck mission came along and did some revisions and made some tension with that by quoting something in 2015 of about 67.8 or so, and that's really close to the WMAP, but there's some tension there. And then finally, the Sloan Digital Sky Survey looks at various things. It looks at galaxy clustering, and that helps how galaxies cluster is also affected by the expansion rate. It came out in 2016, and they give something that's very, very close to the Planck mission. And finally, there was a really good measurement that was done by looking at gravitationally lensed objects. And that's gravitationally lensed objects show how light has moved through space as the universe has expanded underneath it on lines of sight. So the Holy Cow group, and yes, that is the exact name of the group, it's called Holy Cow. You can go look it up, it's really wonderful. In November 2016, gave a rather large number that was well outside the error bars of everybody else. And that provided a little bit of a tweaky problem for many people. And at the January 2017 meeting of the American Astronomical Society, this was a major source of concern for a lot of people. But the thing is that they're all in really close agreement. We're no longer in the time where I was when I was in college, where people didn't know if it was 50 or if it was 100, and it was off by a factor of 2. Now people are getting really, really close with these measurements, and numerous teams are getting numbers that are very close to each other. But this means that we're in the era of precision cosmology, where we'll actually discover the expansion rate. And maybe it's dependent on direction, maybe not. But these measurements are very good and show that the expansion is robust and can be measured in many different ways. So we have really big questions that we're going to be asking in the future. And exactly what is the Hubble parameter? What's the expansion rate of the universe? What's the age of the universe? How did it expand in the past, and what will it go to in the future? And next time we're going to be talking about what is this redshift Hubble parameter thing anyway to begin with? Today we're going to be talking about the Big Bang. Last time we looked at Edwin Hubble's amazing discoveries and we're going to extend that into the idea of the cosmological redshift. The cosmological redshift is one of the key pillars of the Big Bang and cosmology itself. It demonstrates, just to let the cat out of the bag, that the universe is expanding. So we're going to look at the evidence for that and why we think that we treat that evidence as though it's expanding. Once again, cosmology is the study of the entire universe and everything in it, what it's going to do, how it moves, its origin, and its fate. And next, we're going to utilize an incredibly important principle called the cosmological principle, in that there's nothing special about our location in the universe, other than that's where it's home. And if we see that everything's roughly the same in every direction, maybe not the exact same galaxies, but yet the same kinds of things distributed in the same kinds of ways in any direction, that's isotropy, about any point in the universe, particularly us. And if you combine it with the idea that the laws of physics are the same, meaning there's nothing special about where we're at, then isotropy means isotropy everywhere. If you have isotropy everywhere, then you have homogeneity everywhere and looks the same everywhere and made of the same stuff. That means no matter where you are, you're going to see exactly the same thing, and that will become really important. Okay, so when we look off last time on the great distance debate that was in the early part of the 20th century, it was solved by Hubble in 1929, was the distance between the Milky Way and Andromeda, and trying to find the distances to the spiral nebulae, which puzzled people for a long time. So let's do a quick review about that. A couple of galaxies like M81 and M82 nobody really knew how far away these nebulae were, and they were thought, like especially the one on the left, M81, was thought to be a star-forming region or a planetary forming region or something like that before people knew that it was 12 or 14 million light years away, and that thing is composed of hundreds of billions of stars. Same with the other one on the right. These are interacting galaxies that are pretty nearby us at about 12 million or so light years away. And the distance, the detection of that distance was a major story about the size of our cosmos. So how do we know how far away they really are? And what we're really going to talk about is the expansion. And in 1912, prior to Hubble's discovery, Vesto Slipher at Lowell Observatory and a few others, mostly Slipher, was able to measure over the course of a few years using getting radial velocities for the spectra of about 25 of these galaxies, which he called spiral nebulae at the time. And he found, of those 25 galaxies, 21 of them show a redshift, and some with very, very, very high speeds, up to 2,000 kilometers per second away. And he said he found that galaxies are rapidly receding, but he didn't have distances. So he knew he was onto something very important, and the discovery and knowing that the significance of the spectra were really, really, really important. He just didn't have distance in order to actually make the connection. But in 1929, Edwin Hubble finally actually measures the distances to a few galaxies, including M31, M33, and some other local group galaxies, and he compared the distances with the recession velocities. He found that the recession velocity gets larger as you get farther. And this was taken to mean that he had found the systematic expansion of the universe. And this is a really, really, really big discovery. In fact, it's probably one of the most important discoveries of 20th century science, without any exception, because it changed the nature, it turned the study of the universe away from stories told in ancient books to being a precision science. And that's where we're at today, almost 100 years later. So how far is the Andromeda from the Milky Way? And that was the question of the 1920s. And what Edwin Hubble did is he knew about Cepheid variables because of Henrietta Leavitt's work, and then refinements by others on that work to actually discover Cepheid variables in, say, the Large Magellanic Cloud, which are a particular kind of variable star. And the variables, Cepheid variables, have a particular light curve that if you find a star with that variability, you've found a Cepheid variable. But they also tend to be much, much more luminous than the others. And Cepheid variables are extraordinarily luminous variable stars. So if you can create a good relationship or calibrate the period luminosity relationship, meaning then you can get their distances. Well, that's a good thing. And that's exactly what Hubble did in his work in the 1920s. So he started taking pictures of M31 and M33 and others in order to try to find Cepheid variables, and he did. He found a number of them starting in 1923. And here's another one of his plates from 1926 from the Astrophysical Journal, and you can see he marked up a series of variable stars that he found in there. And so he looked specifically for them and found their periods, and therefore he could derive their luminosities based upon the work of previous people, starting with Leavitt. And what he then did is he followed it up by noting what Vesto Slipher had found, that there are radial velocities. And so he did additional radial velocity measurements with the 100-inch telescope at Mount Wilson, and his work was with Milton Humason. And Humason was actually one of the mule drivers that actually brought the 100-inch mirror all the way up to Mount Wilson in California in order to do that. And he stayed on after his work as a mule driver. I stayed on as a janitor at the place, so he never had any really formal education. But he ended up having a fantastic way with things, and he became one of the greatest observational astronomers of the time. So what he would do is he would work and taking the spectra, and some of these spectra would last between 30 and 50 hours of exposure in order to collect enough light to find a spectrum. And that meant that the same spectrum had to be, because it's photographic, had to be taken out of the telescope every day, put back into the telescope every night, and then done over many, many, many nights, where the object would have to be centered in the telescope and tracked not just by the telescope itself, but by Humason at the observatory. And so this took an extraordinarily long time in order to assemble the light that created the data that you see on the right-hand side. And so they used as to get their velocity data the fact that elliptical galaxies, or at least elliptical galaxies, could be used to this effort, is that the particular kinds of galaxies had certain absorption features, and those certain absorption features were seen to be redshifted. So look at a galaxy, look at a greater and greater and greater distance, it looks physically smaller, it has a greater radial velocity away from us, and that's a very interesting thing. All right, so we see a particular pair of lines, and there's a reference point called H and K, and the H and K lines are the things that they're actually measuring, and we find that they're actually displaced from their laboratory rest wavelength, and that is called redshift. And so when we look at what we really mean by redshift, it's on the top, it's the rest wavelength, meaning if you were right next to the object and took a spectrum of it, the top spectrum is what you would see. However, if the object is receding away from us at some speed, then the entire set of spectral absorption features will be shifted to the right by the same amount, and that is what we call the redshift. So when he did this, he found that there was a relationship between the speed with which it's rushing away, which is a measurement of the redshift, and how far away it is he derived from, that Hubble derived from Cepheid variables. So this is from his 1929 Proceedings for the National Academy of Sciences, and this is his 1929 data that show that the farther away something is, that's the bottom, the faster it's rushing away. And that's the y-axis, or up and down. And he then further went on a couple years later to publish in Astrophysical Journal even more. And his original data is in the lower left, but he found some other ones that are much further off, up and to the right. And that linear relationship that showed the farther away something is, the faster it's rushing away from us, became a universal thing. And that's one of the great discoveries of the cosmos. And this was it didn't have to be this way. We have to remember that it didn't have to be this way. The universe didn't have to be expanding. It could have done whatever it wanted to do. But it just so happened that this was the discovery. And we assume there's a lot of things that it tells us about the nature of the entire universe to have that the farther a galaxy is from our location, the faster it's rushing away from us. And that's very interesting. So here's Hubble at his desk with the 100-inch telescope inset there, and we looked at, and here's some of his data showing how he measured the redshift of a particular galaxy, and this is the data that he obtained for his first paper that changed the world. So let's look carefully at Hubble's law. Hubble's law shows that there's a relationship between the recession velocity of a galaxy in kilometers per second and its distance in megaparsecs, or millions of parsecs. And it's related by the Hubble parameter, or the expansion rate. So basically that's a way of saying the velocity equals some number times the distance. So the Hubble parameter is essentially a rate of change of the distance. So the more distant a galaxy, the faster its recession velocity. And it's very hard to measure that, this H0, but currently best accepted things are H0 is roughly about 68 kilometers per second for every million parsecs. So you got to go very, very, very far and see something extraordinarily far so that you can actually start to see this effect. Now we measure what we measure today is roughly between 67 and 69. There was a lot of projects, and one of the most important reasons for the launch of the Hubble Space Telescope was to actually measure, to discover Cepheids and measure the Hubble relationship to great extent. And that's what the Hubble Key project did, and they have a number of things. I provide the link down there at the bottom. And they discovered, I believe their measurement was somewhere around 75. But H naught is extremely hard to measure. It's really hard to measure. Recession speeds are pretty much easy to get because, you just take a spectrum and see how far they get shifted. But the distances are much harder to measure. So making an accurate distance measurement is very difficult. So that's where most of the errors came into account. When I was in grad school in the 90s, the thing about the redshift or the entire Hubble relation is nobody could decide between whether it was 50 or 100. Now it's well known to be about 68. So this is very interesting that it's kind of gone right smack in the middle of the extremes. So let's look at what it means to have a redshift. The important thing is it's like a Doppler shift, and what they did is they assumed that the rest wavelength, which is the lambda sub O, or that's the observed wavelength, lambda sub O, and then compare that to the emitted wavelength, lambda sub E. If you do a ratio of that and subtract 1 from it, that's equal to the speed with which it's traveling away or towards us compared to the speed of light. So essentially, you're saying is how much different is it from how much different is the observed wavelength from the emitted? If it's not different, then the speed with which it's rushing away will be 0. If it's really different, it can be twice or 3 times or what have you. It can have a very, very, very large redshift. So that's the analogy for it. So what we have now is that we can define redshift, and redshift cosmologically is defined this way. It doesn't have units like meters or seconds or anything like that because the definition is embedded in it. So I just basically took that previous equation and got rid and combined c divided by v and turned that into z. And so z is the standard way we talk about redshift, and it's simply the difference from the observed to the emitted wavelength divided by what it was when it was emitted. So you can see that if the redshift is 0, then the observed equals the emitted, and that's basically right next to you. But if it's rushing away from you so quickly that the observed wavelength is twice the emitted wavelength, then that would be a redshift of 2. All right, so here we can see a summary of all those things. The speed of the redshift, v redshift, is equal to the speed of light, c times that redshift value. That's in the middle. And at the top, we see the relationship that I kind of described and put it all together. And where that square rooty sort of thing comes at the top right, is because if you are looking at it relativistically. Now, relativistically means that the recession velocity is nearly the speed of light. And you have to use that equation. But if the speed of light, but if the recession speed is small compared to the speed of light, then it approximates. That's what that double tilde sort of equation, that bendy equation means. Then the previous thing with the square roots and the -1 to that gets really, really, really close to v over c. If the v over c, the speed with which it's receding compared to the speed of light, is pretty small. So that equation approximates that. That's what that double tilde means, that double wavy equation. Now what's funny is that we look at the bottom, is the redshift is approximately, and this is really important, it's approximately related to the time that we observe it in the age of the universe compared to the time that the light was emitted in the age of the universe, times what the Hubble parameter for the current value of the Hubble parameter is today. So that means that the redshift is equal to the distance divided by the speed of light times the Hubble parameter today. That's what T sub naught means, is the time today, today's time. And T observed could be just today's time, right? But T emit is when it was observed, when the light was emitted from that galaxy. And when we say a galaxy is like 100 million light years away, T emit is 100 million years ago, and T observed is now. So that gives you a big difference of time to go back in time, and so the redshift can be a large number. All right. For nearby galaxies, therefore, the redshift is proportional to the distance. It does not work for really distant galaxies. The equation changes. But for nearby galaxies, the distance d is approximately, that's what that waggy equation means again, is approximately to the speed of light times the redshift that you measure by looking at the observed and emitted observed wavelengths, and when you know what the emitted should have been, divided by the Hubble constant. Well, measuring the Hubble constant is a real trick, and that is really the trick, and that was what Hubble did in 1929. He actually, that slope of that curve, that line, is the measurement. Now you can see there's a lot of spread around that, and that makes it tricky to measure, and you've seen other things like that too. So, but our most important element that we're going to take away is that all galaxies, only with a tiny number of exceptions, like tiny means a handful, like 5 or 10, are receding away from us. The recession is what we call the cosmological redshift because of the cosmological redshift, it's not a Doppler shift. Why isn't it a Doppler shift? Okay, a Doppler shift means that the galaxy is simply rushing away from us, right? So if you hear a Doppler shift, like a siren going off and there's an ambulance is driving down the street, then that Doppler shift happens because of the relative motion of the ambulance with respect to where you're standing. And okay, that's fine. So then if it's not, but then why can't it be a Doppler shift? Because the cosmological principle says that there's nothing special about where we are in the universe. And if there's nothing special about where we are in the universe, then what's this deal with everything rushing away from us faster and faster and faster as it goes out? It makes us look like we're at the absolute center of something, of everything. But that's not the case. If the cosmological principle is true and everything looks the same in every direction, and everything we know that the laws of physics, or we can at least posit that the laws of physics are the same everywhere, then it makes no sense for us to see, and we don't look really special. Our galaxy looks pretty much like other galaxies as we've seen. So if our galaxy looks like other galaxies and we're not special, then that redshift measurement is not special. And if the redshift measurement is not special, then it can't be a Doppler shift, meaning that stuff is flying away from us because it's moving, it's got rockets, something else must be doing it. And that something else is the stretching of space-time as the universe itself expands. But the universe drags on the light. And so galaxies don't get stretched by the universe's expansion because gravity holds them together. Protons and electrons don't get stretched because they're little particles of mass. However, light has a definitive wavelength. So as it travels, the universe expands, and that actually extends and makes the light grow because there's nothing, quote, keeping the light from being stretched. So the light gets stretched as it goes through the cosmos. That's where the origin of the redshift is. So the redshift distances have limitations. You can only know the red H0 to a few percent, but that's getting better and better and better with more and more observations of various kinds. So random galaxies, so you can't use redshift for close-in things because then the cosmological expansion is dependent. It can be overwhelmed by, say, the random motions of the galaxies. So if you look at the Virgo cluster of galaxies, you've got random motions of those things that are comparable to the cosmological redshift. So really you need to look at things that are extraordinarily far in order to start really saying, oh, now the dominant motion is the redshift. So you got to get there, you got to get out to the far stuff before you can use it. But as soon as you get out there, then you might as well just call things by their redshift, because now we say that the redshift is there. So we might not, since H0 is not well known, the best way to actually discuss what the distance is actually simply to declare about what the redshift of the object is. All right, so the lower left-hand corner here is Hubble's data, and we can see a Hubble diagram for a different kind of thing, the distance as a function of velocity, recession velocity as a function of distance, and this is for a bunch of type 1a type supernovae that was published in 2004. And we can see that this particular data set shows that the farther you go, the faster it's rushing away from us. That's really what we're talking about. And this is from another group, from Mold et al., who has actually compared various and sundry methods, and they averaged them out to show that it's about 72 kilometers per second per megaparsec. But we see that there's 5 different methods by which people were measuring this number of H0, and they all give pretty good agreement. with the brightest objects being the type 1a supernovae, and we have all sorts of different ways of measuring distance, and somehow they all come up with roughly the same answer, which is fantastic. But the most widely accepted value comes from measurements of from the cosmic microwave background due to the European Space Agency's Planck mission, where h0 is approximately 68 or 67.7 kilometers per second per megaparsec, which is a really accurate measurement compared to what we're seeing in this graph. This graph has a spread between 65 and 79, but the Planck mission has narrowed it down to 67. So this is really interesting. So how do we interpret, and why do we interpret this redshift as the expansion of the cosmos? It's really important to get at that, so let's kind of dig away at it a bit. We do recognize in the world today that yes, there is a cosmological expansion, so exactly what does this come from? Well, first, remember Hubble's law is empirical. It came from observations. He simply fit a line to the observations and found some empirical data, meaning he took data and found a relationship between them. Vesto-Slipher knew that these things had redshifts, but it was until Hubble was able to get the Cepheid distances to these galaxies in order to make this relationship. And every other empirical data point that's ever been found has shown that this is also the case. So it has been found by numerous researchers doing lots of different things from different cultures, different places, different methods, different times, so this is a real thing. So let's see what we mean by the expansion. It is not motion through space. It is not about the galaxies are moving through space. We must think instead that space-time itself is expanding and getting larger. That thing that we call space and time, or space-time, or space, is getting larger. And as it gets larger, galaxies just get kind of carried along. Now, when the universe gets twice as big, the distances between the galaxies are twice as far. And so therefore, the sizes of the galaxies don't change because they're bound together by gravity, and that, remember, overcomes the expansion because the expansion is very small compared to the rest of it. So the space in your room is expanding, but you know what? You have to look at megaparsec size scale, so it really doesn't do too much inside of a room. And in fact, the space between the atoms inside a table or a chair or just inside your head or whatever you like, the electrostatic force overcomes that expansion, so they don't get spread apart. So this is a general expansion, so everybody sees everything. So we can say with confidence that there is no center and all observers seem to be at the center. That's what we mean by this kind of funny thing. So take like kind of a balloon sort of thing and stick a whole bunch of things on the surface of the balloon. And why do we use the balloon analogy? Maybe you've seen this a bunch of times. Why do we use this balloon analogy? Because we take the three-dimensional, or the up, down, backwards, forwards, left, right version of space, and just for visualization purposes, we eliminate, say, up and down. So we only care about left and right. So how would we make left and right work? So you can either take a sheet or a balloon, but people know about balloons. So paint a bunch of dots on the surface of a balloon and imagine that all you can do is go left and right on the surface of the balloon. You can't go into the balloon. You can't go below the balloon. You can't go up above the balloon. You can't go inside the balloon. You can only stay on the surface of the balloon. So if you're only on the surface of the balloon and you start puffing it up, then the things on the surface of the balloon will stay the same size, unless if you paint them, then they'll stretch. But let's say you stick on some stickies, so like a couple of little icon-y sort of stickers. The stickers will simply, on the surface of the balloon, will expand away from each other, but they won't change in size because the stickers don't participate. Now the sticky tape will drag them away from each other. So in this case, it looks like the robot in the center is seeing everybody expand, but if you look carefully, you'll see that everybody else would also see everybody expanding. And the farther away somebody looks, the greater the distance appears to be. And so everybody would see it. And the nice thing about thinking about the surface of a balloon is just rotate the balloon and look at a different set of stickies. And that sticky then looks like it's in the center as you expand. And then you look at another set of stickies on the same balloon, and you rotate the balloon around and then keep expanding. And that sticky stays in the center. So it doesn't matter which sticky you focus on, it will seem to stay put while the other stickies seem to move away as you inflate the balloon. So this image does not mean that these things are inside the surface. It means they're on the surface of this balloon. And so what we mean by space is that for this example, as we reduce the 3 dimensions, up, down, backwards, forwards, left, right, to just backwards, forwards, left, right. And we've ignored the third one because, well, that's kind of hard to do. And so let's make an analogy that'll help understand. All right. Now the universe grows, and so the size scales of objects that are not bound together is like something like light. So light is not gravitationally bound to itself. So as the universe expands, it gets stretched too. So the wavelength of light gets stretched as time goes and as light travels through the cosmos. So what's kind of deceptive about this particular image is that waves of light are not standing waves on the surface of the balloon, but you'd have to think that the wave is moving from, say, left to right. And as it moves, the ground, the surface across which it is going is stretched, and because it has a wavelength and it's not pulling back on itself, that wave gets stretched. So that's what explains the cosmological redshift. So we can look at the bottom little graph. We got 2 little galaxies, and on the right-hand side, the galaxy emits some blue wavelength of light. And that's the distance that they were apart when the light was emitted. So that's what de-emit means. And then there's lambda sub-emit, which shows that it was blue wavelengths of light when the light was emitted and the galaxies were close. Now, as the universe expands, the galaxies spread apart, and the light travels from the place it left towards us, and then we receive it at a new wavelength, which is a longer wavelength. So the universe has stretched by, say, twice or 2.5 times. This looks like 2.5 times. So the wavelength will be 2.5 times greater, and the galaxy will be 2.5 times farther. And that is the distance now and the wavelength now. So the wavelength now compared to the wavelength that was emitted is proportional to, in fact, is exactly equal to the distance now compared to the distance that it was when it was emitted. So the cosmological redshift is simply the fact that the universe is dragging on the light and stretching it as it travels. So the galaxies don't stretch because they're bound together, but light does stretch because it is not bound together. Here's another little graphic that kind of shows that. And another way we can think about it that's really kind of interesting is to think about light travel time. How distant was it, and how much time it took. So the emission distance is on the bottom, and it starts as blue, and when it arrives, the distance now is there. So when we think of something of saying, and then there's like 2 paths. And the path that's way on the right is the path that the galaxy took after it emits the light. Remember, light does not travel instantaneously, so when you look at something, you don't see it as it is now, you see it as it was when the light was emitted, because it took time for the signal or the light to get here from there. Now, we're just here, so we stay put in time, so time goes from the bottom of this diagram to the top. Now, the light itself, the photon, travels through time, and as it travels, it gets stretched, and as it gets stretched, its wavelength gets longer, and if its wavelength gets longer, it gets redder. And so that what we call that travel time is the light travel distance, or the distance in, say, light years. That's what the vertical scale is, and that is what we would call the distance in light years, meaning how far did the thing travel if we presume that we say light speed times the time that it took to travel. So the up-down time, blue arrow, shows the light travel distance. The emission distance is also a valid distance. It says, well, what was the distance when the light was emitted? And The real distance, or the distance now, or called the proper distance, or is if we stop the expansion, just could halt it for a bit, and then walked a whole bunch of meter sticks to the right from our current, from where everything is at the top, and walk all the way out, and we would see exactly how far it is. But remember, the universe is expanding, so it's kind of tough to do. So you have this thing called light travel time distance. And so you have a light travel time distance, which, remember, photons don't have clocks, but they do get redshifted. All right, how does redshift measure expansion? Let's really get to the nitty-gritty. Distance measurements are always some length. So it doesn't matter how that length is measured. But what you can do is you can make, say, paint a big triangle in the universe. And I'm going to color that triangle purple. It's got 3 points and the triangles are there and here. And then we can say, let's start with the triangle when the universe is, say, small or a go. So I'm going to call it having a scale factor of A, and A is the value of the scale factor of how big the triangle is in general. And that's what it is then. So now what I'm going to do is I'm going to expand the triangle. So I expanded the triangle to a scale factor of now. And now its size is twice as big. Every side of the triangle, I just made twice as long. And as I made it twice as long, the scale factor is twice as big. So the purple, every side of the triangle, is exactly half the size of the side of the green triangle. I invite you to try this at home. So the green triangle is double the side on each side. So the length of each side is twice the side that it appeared from. So the triangle has been scaled up by a factor of 2, and that's what those A sub now and A sub then indicate. It shows you the relative scale sizes. And I've left that funny thing on the left-hand side, that 1 plus z, which is the redshift. So how do they relate? That's a real big question. So remember, redshift is the wavelength observed times minus the wavelength emitted divided by the wavelength emitted. Remember we said the distance now is compared to the distance then? If you set these two equations together, you get that the size now, which is observed, is equal to the size of the universe now compared to the size of the universe then, the A sub now and A sub then, is exactly equal to the wavelength of light observed divided by the wavelength of light when it was emitted. So this is the measurement of this. The light gets stretched by this expansion, and all we know, we don't care how it got stretched. Maybe it went faster and slower and slower and faster. But for this particular object, when we get that thing, we know what the size scale of the universe is compared to today. So maybe when the light was emitted, the universe was 10 times smaller, or 100 times smaller, or 1,000 times smaller than it is today. So as the universe expands, it was smaller then. So now we simply just say, oh, what is the universe size scale now? Let's just call it 1. How about then? Well, it might have been 10 times smaller. So if the universe is 10 times smaller, then the A then is a tinier number. So A now must be 10 times bigger. So A then might be 0.1, and maybe A then is a million, 1/1,000,000th or something. So light gets stretched because these two equations are linked. They are the same thing. So remember, each length gets doubled, so the wavelength gets doubled, and if the purple lines are the wavelength of light on the sides of the triangle, if one wavelength of light was the length of one of the sides of the triangle, then each wavelength got doubled. And notice the length of the triangles are different. The length of the sides of the triangles themselves are different. So you can have different wavelengths of light. And so you can have these different wavelengths of light, which then get stretched by exactly the same amount. So all redshifts get stretched by exactly the same amount. So let's look more carefully at it numerically, because let's just do this and see, because we want to relate this to the Hubble constant, the Hubble relationship. So what I've done is I've said, think of each of the points of the triangle as either number 1, number 2, or number 3, and R is the length, R sub 1, 2 is the length of one of the sides of the triangle where we're going from point 1 to point 2 as a function of time. That's what the parenthesis t means. It means it's a function of time. And that's equal to the scale factor and how its changing with time, a sub a as a function of time. That's what the parentheses mean again. And then we say, well, what was the side of the triangle at some time ago? T sub naught. So you begin it at some time, like the blue side, and then you grow it by some scale factor, a sub t, maybe twice as big, and you end up with r sub 1, 2 of the time. So you take length of 1 and 2, r sub 1, 2 at the initial time, t sub 0, and you call that length 1. And let's say you make the scale factor twice as big, just like the triangle below. That's a sub t. After a few seconds, a sub t is now twice as big, or maybe a few hours, or maybe a few years, or maybe a few milliseconds. That's interesting. How fast does a go with time? And then you get to the size scale. So notice what I just did there. I said that a varies with time, but how does a vary with time? That's important. And that's our next step, is that we say the velocity of the speed of the growth of the triangle, v sub, I'm just going to focus on one of the sides, say the hypotenuse. So so let's call the hypotenuse v1 is the longest side of the triangle, away from the right the right angle. So now the speed with which the v1, 2, or the longest side of the triangle is growing as a function of time is, well, that d by dt, dr1, 2 dt means is the derivative of the speed, the rate of change of the size with time. That's what that equation means. That dr dt thing simply means how does the length of that side of that triangle change with time. Now, but remember the initial side is a constant. So that means that from the previous equation, we just take the derivative of the scale factor, and that's what that dot means, because I don't want to write out that ddt stuff. So I'm using a shorthand notation. And so a dot of t means the rate of change of a, the scale factor, as a function of time, meaning how fast does it change? We know that it changes, maybe it gets twice as big. But how fast over what time period does it change? Does it get twice as big in 1 hour, twice as big in 1 year, twice as big in a millisecond? So we can then say, oh, but wait a second, we remember that old thing because r12 is equal to the reciprocal of the scale factor times the function of the radius with respect to time. But wait a second, that's our Hubble relationship. If we look at the left-hand side of the equation, v1, it's just speed, is equal to some crazy number, a dot over a, which is the rate of change of the scale factor compared to the scale factor times a distance, r12. So the velocity with which that speed is changing over time is equal to the speed at the velocity at a given time is equal to some ratio times the size of the thing at a certain time. So if we go forward, we find that that's exactly what the Hubble relationship is. Now I'm just going to take that equation, what I just said before, and put it together. The speed with which one of the sides of the triangle is growing, v12 as a function of time, is equal to some ratio. How the scale factor is changing with time compared to the scale factor times the size, r12, as at a given time. And that's just the Hubble relationship. That is exactly the Hubble relationship because it is a velocity is equal to the Hubble parameter times the time. And so we could drop the parenthesis t if we really want to, and we get the original equation, which is the Hubble equation, which is the velocity that is receding away from us is equal to the Hubble parameter times the distance at which it's going. But notice what we've done with this. We've said that now the Hubble parameter can be a function of time. And we know that the velocity with which, or this recession speed, must be a function of time, and the distance that it's going also must be a function of time. So we're allowing for the Hubble constant to not be a constant. Right now, if you look very close, it looks like a linear relationship that's constant. But the farther back in time you look, that number will change. And so we call h as a function of time is the Hubble parameter. And now we see that the velocity is related to the redshift. And the redshift is some measurable that we get. So all we have to do is get some distance measurement. We can get the speed or the redshift speed, the v, from the redshift. And then we can, in theory, measure the Hubble parameter. And that's what those other graphs were talking about. And this is why we say that the Hubble parameter is a measure of the rate of change of the universe's expansion. That's what we mean by it. This is all these bunch of linked equations, and these are the 4 equations that are used to link things together that show that the universe's size scale is expanding. On the bottom, we have the definition of redshift, which shows how the wavelength of light changes from its time of emission to its time of observation. And that's related to the size scale of an object as it's growing. But the middle equation, v redshift, shows how the speed is related to the redshift, the speed of recession is related to the redshift, and the scale factor definition of the redshift falls in so that we can actually relate the Hubble parameter directly to the redshift. All right. What this all means is that the cosmological redshift is exactly the stretching of space-time itself. We do not have to say that the galaxy is flying away from us because it's got rockets on it or something, because that would be weird, because all those things would have had to have been given rockets here, and the farther away they get, the faster those rockets would have to be pushing so that they would get away even further. Now, that would mean that we would be in a really, really, really special place. The place where everybody started. That is not true. We are not at the center of the expansion. So therefore, the cosmological redshift means that the space-time itself must be stretching. What's fun about this is that it also gives us an age, gives us a rough age, because the Hubble relationship shows a relationship between a speed and a distance, so that means it's roughly a time. And if the h-naught is about 70 kilometers per megaparsec, we can simply take the reciprocal of that, multiply all the conversion factors out. There's so many astronomical units in a megaparsec, and so many kilometers in an astronomical unit, and so many seconds in a year. And so multiplying all these numbers out and dividing up and down gives us that the age of the universe is approximately 14 billion years. Just by discovering what the inverse of the Hubble constant is today, we get a good guess as to what the age of the universe is. That's really interesting, isn't it? Well, what is the exact age? Of course, we talked about this last time, but the WMAP probe in 2012 said it's about 69 plus or minus 32 kilometers per second per megaparsec. The Planck team gave 67.7, and Sloan Digital Sky Survey gives about 67.6. The Holy Cow group, looking at gravitational lensed objects, found a higher value, and they're extremely good data. But that's an interesting thing that there's some tension there that people really think will get worked out. In any event, when you measure the distances, all those distances show that the farther away you are, the faster things are rushing back, and you're also looking farther and farther and farther back in time. But it doesn't mean that as the recession velocity gets faster and faster and faster, that it gets closer and closer and closer to the speed of, well, you can get it so that the recession speed apparently it gets closer and closer to the speed of light, then that the distance actually kind of peaks out. And that peaking out means that's our cosmic horizon. So you can't see anything farther away, more specifically farther back in time, than there has been time for that light to get here from there. And so the farthest thing back in time that we can see is approximately 13.7 billion years. And its current present distance would be much greater because, well, remember, present distance is what we call proper distance, and proper distance is stop the expansion, pretend you can stop the expansion, just pretend for a second you could stop it, put down a whole bunch of yardsticks all the way out to that far thing, and you'd find it's really, 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 really far. However, if you had some way of just saying, oh, we know how far the light's been traveling, and that looks like it's 13 billion light years away. So that's kind of a misnomer. Something that is seen to be at 13 billion light years away is really a bad way of talking about it. What we mean is that the light has been traveling for 13 billion years. That doesn't mean that it's 13 billion light years away. Remember, there's expansion in the cosmos. So if the light's been traveling for 13 billion years, that's just how long the light's been traveling. Right now, that thing is much, 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 much further away. And according to this little graph, it's about 30 billion light years away. So there are things that we see now that are currently so far away that any light that is being emitted by them will never reach us, because the expansion of the universe makes it so that that will expand the light away before it can actually get to us. Interesting. So our universe then is expanding, and we measure its distance. We measure the distance of the objects by looking at their expansion rate. And so from Stefan's quintet, we can see that there are 4 galaxies here, and well, 5 actually, but we see that 4 of the galaxies, according to this Hubble image, are approximately 6,000 or 6,500 or 6,600 kilometers per second recession velocity. But then the little spiral in the upper left has only a recession velocity of 800 kilometers per second. Because of the expansion rate of the cosmos, we now know that the 4 yellowish distant galaxies are maybe 10 times more distant than the little spiral galaxy, which looks blue. So all 5 of these are not interacting. NGC 7320 is close compared to the other 4 in the background. So that's interesting that that one just happens to be in the same direction as the others. And you also don't see any tidal interactions between the 4 yellow ones and the one and the spiral galaxy, which looks, relatively speaking, undistorted. Why? It's 10 times closer than the 4 behind it, which means the ones that are 10 times closer, that means it's a small galaxy compared to the ones behind it, because they look about the same size, but yet the ones behind it are much, much, much further. Fascinating. Now, another interesting factoid is that as you look back in time, then if there's an interesting bit that since the universe was smaller ago and everything was closer together, the light the objects, if you look farther and farther and farther back in time, meaning greater and greater and greater redshift, you'll be seeing it when things were closer and closer and closer together. Now, if every galaxy was 30,000 light years across, just presume it for a second, so it's a standard ruler, then as you look back, as you look further and further out in space, things look smaller because they're farther. But at some point, because of the expansion rate, the universe catches up with that look back. We're actually seeing the galaxy be bigger in the sky. So the greater and greater and greater redshift objects would actually look larger and larger and larger, and would look about the same size as something that has a redshift of maybe even a much smaller redshift, a redshift of less than 2. So if we can find a galaxy at redshift of 10, say, and it may very well have the same angular size, and they're both 30,000 light year galaxies, one at redshift 10 and one at redshift 0.5, then, or redshift 1/4, then we know that the one at redshift 1/4 is very near, and we know the one at redshift 10 is very far, but yet they'll have the same appearance in a photographic picture. They will look the same size, if they're the same size. If they're the same size, meaning they're both 30,000 light years across. The fact that we don't see that means that galaxies in the deep, deep, deep past at extraordinarily high redshifts are actually much smaller. That's interesting. All right, the universe is expanding. We look like we're at the center, but that's what every other observer sees too. That's the cosmological principle. So if that's what we see, and the laws of the universe are the same for everyone, and our galaxy is no different from any other galaxy, I mean, we're not at the center of some grand explosion, we're not sending all these galaxies off into space and things are spinning off. If that's not the case, then every other galaxy will see the same property. Therefore, it's a universal property. The only way for everyone to see the expansion in the universe is for it to be homogeneous and isotropic around the entire cosmos, and so therefore the universe itself is expanding. And that is the discovery of the expansion, right there. So the universe today is pretty low density, it's dark and rather cool, and it's still expanding. If you go back in time, 13.772 billion years ago, the universe was very small, very dense, and very hot. The universe was filled with light, and how far back can we possibly go? But when we go back and back and back, we get to the point where it must be hotter. Why? Things are closer together. Higher density. Higher density, according to the ideal gas law, means hotter. Higher density, higher pressure, higher temperature, everything. So that's why it's called a Big Bang or a primeval fireball. But where did this happen? There was no special place. There's no shock wave. There's no expansion front to the explosion. So there was no real explosion. But remember, everyone sees the same thing no matter where you are in the cosmos. Therefore, it happened everywhere all at once. So the Big Bang is an event in time over all of space, not an event in one place in space at a point in time. No, it is a thing that happened to all of space at the same time. That's what we mean by the Big Bang. It wasn't this little place in space did this thing. No, the thing that we call space, all of that thing, all of those things participated in this Big Bang at that time. And now we measure the rate of expansion of the cosmos by measuring the Hubble parameter. That's why Hubble's discovery was so incredible in 1929, because it leads to this amazing conclusion that once upon a time, 13.7 billion years ago, that the universe was tiny, hot, small, condensed, and we have evidence for that because the universe is expanding now, which is really quite amazing. This time we're getting way out into the cosmos. We defined the nature of redshift last time, and so redshift allows us to get distances to galaxies, and with those distances to galaxies we can figure out how things are arranged in space. And that's the structure of what we're talking about this time is groups and clusters of galaxies, because once we know where they are in the sky, we can see that they're actually grouped. All right, so the first most obvious group that we know about is called the local group, and the local group is about 54 or so galaxies comprised the Milky Way and Andromeda. It's our little local neighborhood in the universe. Now the Milky Way and Andromeda are of course falling towards each other, so they're all bound by gravity, and the diameter of the local group is about 3 or 4 megaparsecs, and it contains about 5 or so bright galaxies, and 3 spirals, and 1 some big elliptical orbiting M31, which is M32. There are a few dwarf ellipticals, and lots of little dwarf spheroidals, dwarf irregulars, and all sorts of little bitty things. Now the total mass of the local group is about 5 trillion solar masses. That's about 5 times 10 to the 12th solar masses, because each of the Milky Way and Andromeda is a few hundred billion stars, with a lot of dark matter in between. And so when you add up all the stuff and all the dark matter, you got a lot of mass there. All right, so the local group is our little neighborhood, and there's what it kind of looks like. There's a lot of space between galaxies, because remember, galaxies are where the stars are, but we also know that in between the Milky Way and Andromeda, there's an enormous amount of dark matter. So if we could possibly see all the dark matter, it would fill this space. It would be like this big glow around the Milky Way and around Andromeda, and in fact it would probably be about 5 to 10 times the size of it. So this whole bucket would be filled almost to the brim, almost completely smoothly with dark matter if we could see it. So the local group has a certain kind of orientation, so let's take a little tour. There's what the Milky Way is. We always center ourselves in the Milky Way. Lots of little dwarf galaxies, large and small Magellanic Cloud around us. And if we go up to the M31, we see it's over here. The Triangular Galaxy, M33, M110, and M32 are also there, some elliptical galaxies. And we can see their arrangement in space. And here's a beautiful image of the Andromeda Galaxy taken that was shown in an astronomy picture of the day. Another wonderful astronomy picture of the day picture comes here of the Triangular Galaxy, and the large and small Magellanic Clouds are part of the Milky Way of the local group as well. So the Milky Way is the local group is kind of a thing called a group, and so there's different kinds of ways that galaxies come. They come in groups and clusters. Groups have about 3 to 30 or a few bright galaxies, and clusters have at least 30 to a couple hundred bright galaxies. And groups and clusters typically range from about a megaparsec across to about 10 or 15 megaparsecs across. That's millions of parsecs, which means about 30 million light years to about 50 million light years. And they're filled with many, many, many more dwarf galaxies than bright galaxies by their counts. Now, there's groups and clusters of galaxies. They range in mass between 1,000,000,000,000 and 1,000,000,000,000,000 solar masses. So there's a lot of mass that tends to be in groups. And thousands upon thousands of galaxy clusters have been known and cataloged. So here's some dwarf galaxies in the Perseus cluster. Here's one of them is called a Hickson compact group. So you see 3 spirals, 2 interacting, and one elliptical, and possibly a very, very distant spiral in the lower left. Here's Hickson compact group 31, and that's another group of galaxies. Here's its appearance. So you can see this is not very big. So the Hickson compact groups are kind of an exception to this, where they're very small volumes of space with smaller galaxies that are interacting as groups. Here is Seyfert Sextet, which is another small group of galaxies all interacting. And the Hickson compact groups themselves were studied by Hickson, and he created a series of groups that were between 50,000 and 200,000 light years in diameter, and always contained maybe 1 or 2 spirals and a few ellipticals, but they tend to be centered on spirals. And we can see a couple of groups in here with the lower left, which is the Stephan's quintet, of which only the 4 on the lower left is Stephan's quintet, and the upper right we just have an apparent group. The big one in the foreground is actually a foreground galaxy, but the ones that are above it and beyond, that's actually a group. So groups get to larger groups that we call clusters, and clusters of galaxies are much larger and can contain thousands of galaxies. The Virgo cluster is the nearest large galaxy cluster to the local group. It's a relatively loose cluster, meaning it's not really tightened in and everything together, but there are 2 bright ellipticals, M87 and M84, that comprise it, and it lives at a distance of about 18 megaparsecs. That's about 60 million light years, and that spans about 2 or 3 megaparsecs in diameter. Composed of about 3,000 or 4,000 galaxies, and most of them are dwarfs, of course. And the total mass is really huge, 100 trillion suns. But the Virgo cluster has a large composition. As you can see, the spread out nature of all the fuzzy objects, that's what we mean by not compact and loose. And so there are much tighter clusters of galaxies, which we'll see shortly. And here's some of the outskirts of the Virgo cluster. We kind of rotate it around, and here's the core of it, highlighting M84 and M86, which are 2 giant elliptical galaxies. You can see that there's some spirals inside, but lots and lots and lots of objects that are identified as galaxies inside here. Here's an extended mosaic of the Virgo cluster, and here's wonderful thing from Astronomy Picture of the Day to go hunt around yourself. Here it is again. So we can then go jump and look at rich galaxy clusters, and rich galaxy clusters contain thousands of galaxies, and they can span up to about 10 or so megaparsecs, and they have about 1,000 trillion solar masses. So remember that the Milky Way is about 100 billion solar masses, which is about 10 to the 11th. So this would be a 10,000 Milky Ways in terms of mass. They always at least have 1 giant elliptical deep in the center, and rich galaxy clusters have many ellipticals swarming around the center, and the gravitational pull from them usually makes these galaxies spin up to 1,000 kilometers per second as they whip around inside of them. Now that 1,000 kilometers per second inside galaxy clusters has a lot of implications. And here is the Coma cluster, which is a more compactified galaxy cluster, and there it is, the center of the Coma, which is, you can see lots of elliptical galaxies in here and a couple giant ellipticals, but we don't see a lot of spiral galaxies inside a dense cluster like Coma. And we can see 2 kind of groups over here. There's 2 centralized groups of galaxies with all the fuzzy patches are distant galaxies. And another rich, dense cluster, Abell 02345, where a couple of giant ellipticals surrounded by a swarm of elliptical galaxies. And here's Abell 02439, which is a long sort of string of galaxies. and another one, 2350, which is kind of an extremely distant galaxy cluster that seems to have a number of ellipticals in it. And Abell 2351, which kind of looks like a star field, but actually is a group of fuzzy little galaxies far in the distance. Just to give you an idea of what galaxy clusters look like in the Digital Sky Survey, that's what this is all doing, is that we can see that there's these little tiny fuzzy things that are deep in the distance that were seen photographically originally, and so counts were done. And here's Abell 2353, another one that's a nearby galaxy cluster. And the Hercules cluster is a more loose one, and it is spread out further and has more spirals in it. Abell 98 is a much more rich cluster with a dense group of ellipticals around a giant elliptical at the center. And again, Abell 98, I believe that was the same thing, Abell 98, different orientation. Now, the fun thing about galaxy clusters is they're held together by gravity. Now, gravity is keeping them together, even though the relative speeds of them are whizzing around at 1,000 kilometers per second. Now, when you have something that's 100 billion solar masses and another thing that's 100 billion solar masses, or thereabouts, and they're going 1,000 kilometers per second, that's too fast for them to stay together. And since that's too fast for them to stay together, their average motions, as we learned with the nature of dark matter when we talked about that when we looked at the Milky Way, there has to be something there that keeps them together. So the total amount of mass that must be there such that these clusters actually exist, given the fact that they are composed of these large galaxies, the mass must be enormous. So people looked for the amount of mass that was there, and they hunted in all sorts of wavelength bands, from radio to infrared to optical to X-ray. And when X-ray views were taken, it was found that a huge amount of X-ray gas existed. But it wasn't enough in order to make up the mass that held the entire cluster together. But most of the matter in all galaxy clusters is in the form of dark matter and can make up to 90% of the mass. And that's what keeps them together from flying apart, even though they're moving very fast. In X-rays, we see that of the remaining normal matter of the entire galaxy cluster, which is 10%, of like normal matter. We assume dark matter is not normal matter, but the remaining normal matter, most of it's an extraordinarily hot 10 million to 100 million Kelvin gas, which can only be seen in X-ray wavelengths, and it's typically superheated material that is emitting light through what's called thermal Bremsstrahlung, and that Bremsstrahlung action means that there is as one atom moves at nearly the speed of light, relativistic thermal Bremsstrahlung, or even just Bremsstrahlung itself. If they're moving extraordinarily fast, then as they pass by each other, their directions change and they lose energy. But they don't lose a huge amount of energy, but it's just enough and when they turn around and get pulled by an atom pulls on an ion or pushes on an ion, that Bremsstrahlung, or braking energy, makes X-ray light. And so that can be done in the presence of a magnetic field or just simply in the presence of other charged particles. And when it does that, well, if it's in the magnetic field, it would be called synchrotron, it would be rotating, it would get radio light. But thermal Bremsstrahlung is a hot gas where the way it's emitting light, because it's not dense, it is not a dense hot gas, it is an extraordinarily diffuse hot gas with only 100 or 1,000 particles within a cubic meter. So they're incredibly, incredibly underdense areas. So the fact that it's glowing so intensely in X-rays means that there's a huge amount of it. So we see that in the optical image here from Abell 2199, we see a bunch of galaxies, but in the X-ray image, we only see the hot, hot, hot gas, which is centered on the X-ray, which is centered on the giant elliptical at the center. So this X-ray gas comprises most of the mass of the cluster that's normal matter, and that normal matter interacts with light. But even that is not enough to keep it together. So the studies for X-rays emitting gas in galaxies has been done for a very long time, and when Chandra X-ray Observatory went up, what was one of the major studies is to map out X-ray distributions in the sky, and here's some Chandra maps of X-ray emission in the sky of various galaxy clusters. And we can see that the X-ray emitting gas greatly extends and encompasses and envelops the normal luminous matter. The vast majority of all the gas, of the matter, of the normal matter in a galaxy cluster, is about 90% of it is this hot X-ray emitting gas. So if 90% of a galaxy cluster is dark matter, and 90% of the normal matter is this hot X-ray gas, then we're only seeing 1% of all the normal matter when we take a picture with a photograph in optical light, where we just see stars. So stars and gas and dust make up only 1% of all the mass of galaxy clusters. Most of the rest is in this hot X-ray emitting gas. All of the rest is in dark matter and this hot X-ray gas. So here's another image of the Chandrasekhar Observatory looking at the hot X-ray emitting gas of a massive galaxy cluster, a rich galaxy cluster deep in the distance. And we can see that there's an enormous amount of X-ray emitting gas. This X-ray gas is probably being created by the formation of this galaxy cluster, as well as enormous star formation and possibly active galactic nuclei, which we will talk about in the future, where active galaxies spew out huge amounts of material into the intercluster medium, thus probably heating up this gas. And so the gas is at millions of degrees. So it's probably been that way for a very long time, but it needs to be reheating because as it emits light, it cools down. If it cools down, it's falling towards the center because gravity pulls things towards the center, as you can certainly see from this image. So something's got to reheat the gas in order for it to have this great extent, so it can stay at tens of millions or 100 million Kelvin. And that's probably due to active galactic nuclei as the galaxies then collide and the supermassive black holes in their centers merge and then form quasar-like activity, which we'll talk about soon. All right, so the largest known structures, are what are called superclusters. And superclusters are enormous clusters of galaxies, or just huge, vast, amorphous, lumpy groups. And they can range up to sizes to 150 million light years, or 50 million parsecs. And their masses range from 1,000 trillion masses to up to, quite a bit. 10,000 trillion masses, which is an enormous amount of mass. And they tend to be long filamentary structures and separated by enormous voids that span the sizes that are as big as they are. Now, superclusters are dominated by, inside of the clusters themselves, mostly empty space because that is filled with dark matter and X-ray emitting gas, right? So, but it's amazing to look at such an image like this from Courtois, Herein et al. In their Cosmography of the Local Universe. It was published in 2013 Astronomical Journal, and I get the link there for you from Archive if you want to go take a peek, because this is worth taking a peek at, is that you see that there's these enormous voids. And these huge voids make part of what we're looking at around here. And the local group is right down in the center there, just off to the side, to the left of what's indicated by Centaurus. So the local group is part of the local Virgo supercluster. So what's that? The Virgo supercluster is what is now on this image that you see here. This is a map of all the galaxies in the neighborhood. And so this was made, of course, with using positions in the sky and their redshifts, and then using the Hubble relation in order to map. Because you can't get Cepheid variables for all of these things, but you can very easily get redshifts. So redshifts are fast, Cepheid variables difficult. So now that we're talking about individual galaxies, if we know their distance, it's because we're correlating it using a well-calibrated Hubble diagram that relates the redshift to the distance. So now this is how we know their distribution in space away from us. So the Virgo cluster of galaxies is off to one side, and we've got these little minor clusters, the Virgo Libra, Centaurus, Hydra, and Ursa Major. This is called the Virgo supercluster. It has an enormous amount of mass, and it's centered on roughly the Virgo cluster of galaxies. And as the local group falls towards the Virgo cluster, the others are kind of grouped together, and this is a roughly gravitationally bound object. Now but in 2014, Tully and a number of other astronomers redefined the nature of the local superclusters and redefined the Laniakea Supercluster. The Laniakea Supercluster it spans many hundreds of, about 100,000 galaxies, goes over 40 million light years, up to 500 million light years, almost a half a billion light years across, and has a mass of at least 10 to the 16th and the 15th of solar masses. I think I've made a typo there, so they have an enormous thing. There are 4 major subparts, and the subparts are the Centaurus cluster, the Virgo cluster, the Hydra cluster, and I think there's another one in there. I think of the Dorado group or Fornax group or the Pegasus cluster. Those were used to be separate superclusters, but in 2014, the astronomical community adopted Tullian team's definition of the nature of a supercluster, because now the ability to actually resolve the relative speeds of things could be deduced and removed from the cosmological measurements of the redshift. So now you could get a position in the sky and base the nature of superclusters off of how things apparently are moving in the sky. And so utilizing the apparent cosmic flow of galaxies, you can redefine clusters of galaxies. So the Laniakea Supercluster was defined in such a way, and it's known this is too big to actually be gravitationally bound and will probably be shredded by the expansion of the universe at some point within the next few billion years by the push of dark energy. So the Laniakea Supercluster is the redefinition of the local supercluster. So let's kind of zoom back into a closer thing. So let's look at what we mean by the Virgo supercluster. This is again from Herein and Courtois' paper, the cosmography paper that we talked about later, and I'll give a reference for that soon. And we see that the Milky Way is off to kind of the outskirts of some side. There's the M81, M82 group over there to the right, and the Virgo cluster is 60 million light years away, and the Ursa Major loose cluster off to the side. We see that M81 and M82, which we highlighted many times off to the side, is pretty close by. And the Centaurus A is a bright radio galaxy that's seen in the southern sky, and the Sombrero galaxy M101 is up there, is up in the sky, up over there too. So we notice from this image that there are lots of empty spaces. So the universe is kind of foamy on the largest size scales. The largest structures, such as the Laniakea supercluster, are about 100 to 200 megaparsecs in extent. That's enormous, up to about a half a billion light years across. And those structures are only kind of semi-temporary because they're not gravitationally bound, so on the largest size scales. But they still do have some sort of coherent appearance. And so the actual definition of where clusters end and superclusters begin is kind of up to taste and current researchers, whoever working on it, and then people just saying, well, that makes sense or not. So it's actually kind of an open-ended current area because Laniakea was only defined, of course, in 2014, so people are really working on it. So clusters and superclusters are arranged in these kind of filamentary or sheet-like structures and sheet-like structures, and their actual volume occupies only about 10% of the space. So the rest is huge voids, and they're big, big, big empty bubbles, and these bubbles of voids can be, up to 100 million light years, up to 150 million light years across, or 25 to 50 megaparsecs across, and they have vastly fewer numbers of galaxies than superclusters, up to 20 to 50 times fewer galaxies, and in fact they might have none. So the exact number of galaxies inside of voids is not well known. So here is there's an important, credible one called the Great Wall, the Sloan Great Wall, and you can see they come in these kind of lumpy sorts of structures. And notice we're looking now at surveys. So a survey shows we're looking at velocity space, and so we can assign distance, which is distance in megaparsecs, but it's much easier just to call what the distance is. We know that the distance is related to the Hubble flow, so we don't really need the distance. We just say how fast it's rushing away. So we have a kind of a pizza pie diagram, and this I believe is a 2DF survey or a Sloan Digital Sky survey, and I forget which it is exactly, but we see that there's this would be Sloan because of the orange mark or marks out the Sloan Great Wall, but we see that there's these lumpy structures and they're foamy. But if you look, that they're foamier, actually lumpier as you get closer and closer to us, meaning velocity goes to zero. So the Milky Way and we are observing from the vertex of these pizza pie slices, and as we look out towards the edge of the pizza slice, we're looking farther and farther and farther away and further back, and they're much more distant galaxies. So we're at the center of the observation, looking either north or south. All right, so here's a better view of that. And once again, you can see that if you look at the distance of things that are approximately 700 megaparsecs or so, we see that it kind of, things get more spread out, and or velocities or up to 50,000 kilometers per second or so, and greater. We see that it's harder to find galaxies because they're fainter, and you have to have deeper surveys in order to find them. But we see that there's greater structure nearby, or stronger, more larger structures nearby. And that's a result of gravity. So the Sloan Digital Sky Survey endeavored and continues to endeavor to map the galaxies in the cosmos, and they've released many data sets over the decades that they've been working. In fact, I started my graduate career in the early 90s by beginning some of the very rudimentary networking to connect Apache Point Observatory down to New Mexico State. In the lab area, so that we could see that. So it was an early use of early networking. So that was kind of a nice way to begin a career. Anyway, the Sloan Great Wall is an enormous discovery. It's about 450 million light years long, about 60 megaparsecs high, and about 5 megaparsecs thick, and has a mass of over 20,000 trillion solar masses. That's enormous. So, I mean, it's almost getting silly to even talk these big numbers. But for the 10 to the 16th means that's how many suns there are. So we really should start to have a new unit in terms of Milky Ways. And a Milky Way unit would be 100 billion solar mass. So if we just use 100 billion, which would be 10 to the 11th solar masses. So this would be 200,000 Milky Ways would be about the size of that structure and how many things are in there. So 200,000 Milky Ways comprise the mass of that thing. And there's not many things that are bigger in structure than about 300 megaparsecs. If you do Google around, you will find some odd things such as very large groups or large quasar groups that seem to be much larger than that. But they seem to be actually larger than this kind of structure. But notice that we don't really find structures larger in great numbers than 300 megaparsecs in size. And here's another view of the Sloan Great Wall, and there's another wall group that was seen by CFA, the Center for Astrophysics survey, and all of them were looking in velocity space. Notice in these pizza diagrams, we always look out towards the edge, and these things are given in terms of right ascension, which is left and right in the sky across a pizza wedge, and we're at the vertex looking outwards. And here's another great galaxy survey called the 2DF survey. And so we see lots of filamentary structure, and wall-like structures and voids. And each of the points is now not a star, but a galaxy that is up to billions of light years away. And we can see the relationship between the distance in billions of light years and redshift. And redshift is out to about 0.2. Remember, redshift, we defined it in the previous lecture as being the change in wavelength compared to the rest wavelength. And it's about 20% is the redshift. So it's been changed by a factor of, the redshift has been altered by a significant fraction. Not doubled in terms of wavelength, but extended by 20%. Whatever it is. So if it's a wavelength of 1,000 nanometers, then it is now 1,200 nanometers long. So it's been extended by 20%. And that happens when something's about almost 2 billion light years away. So you really have to get very far out to get significant redshift. And there's another view of the 2DF survey. And it leads to a very incredible question. How did galaxies form? The existence of this large-scale structure, meaning all these voids and filaments and groups and clusters, galaxies have to form in these structures. So the structures themselves are created and shaped by gravity, and dominantly by dark matter, because we've learned that clusters themselves would fly apart if they weren't composed of dark matter. So they're moving really fast. They're composed of mostly dark matter. The structures are shaped by the gravity of the dark matter and the hot intracluster gas that permeates them. So there has to be huge amounts of concentrations of matter where the galaxies form. So we should expect that the dark matter web should look very similar to the web-like structure that we see here. And that will come up when we talk about large-scale structure formation as part of the Big Bang. So let's go back to Courtois and Herein et al., who are looking at the map of the local universe, and this just predates Tully's definition of Laniakea. And it looks at things in terms of the local speeds. And in fact, this set of data is what helped to define the nature of Laniakea. So we see that, let's start with the local group, and the local group in Milky Way and Andromeda and M101 and M81 group and all that stuff. Remember M81, M82, way over there? There's lots of little dwarf galaxies next to them. But you can also see that there's an enormous void off to above and below the plane of the Milky Way, which is really fascinating. And if we look down from that local void on top of it, we see that there's a tiny little grouplet over by M81, which is its own group of galaxies, right? And we see M83 has its own group, and Centaurus A, which is a bright radio galaxy. When we talk about active galaxies, it'll be in there. And we see these things are composed of little groups. And if we then zoom out a bit bigger, we see again the location of the Virgo cluster of galaxies, which has a few thousand galaxies inside it, and we see all the little tiny mini groups that are close by. And then we can kind of look even a larger size scale and notice that the Coma cluster is much more distant, and we get the beginnings of the Great Wall, and the zone of avoidance is there because of the existence because the Milky Way itself, the dust and gas of the Milky Way blocks that view. So there is a huge gap that it can't be seen and never shall be seen because of the Milky Way blocking it. But on this size scale, when we're looking at velocity space of up to 5,000 kilometers per second of recession velocity, that gets us out to some rather large galaxy clusters such as Coma and Abell 1367. But you see that Virgo cluster is about 65 million light years away, so that we would go 5 times that distance. So we go out to about 300 million light years away to get us to the Coma cluster, as well as Abell 1367. We take and we rotate the view because that was an X and Y view. Now we look at it from above, from the z-axis looking down, and we see the zone of avoidance from there, and we see the Virgo cluster off to the side, and we can see slightly different versions of the filamentary and group-like structure of the local universe. And we can rotate it again to see the pancakey sort of structure of the entire environment. So it is kind of flat, actually. It's a very pancakey structure to the entire local universe. So now we can kind of group it and see how things look in sort of a density sort of format. So we have red where it's most dense, and blue where it's least dense, and nothing where it isn't dense. And we see there's big groups by the Hercules cluster. The Great Wall is intruding in. It's just poking into the view. And from a different angle, we see the Great Wall poking through again. And this is where it gets interesting and how we begin to start to define the nature of Laniakea. So notice all these little dots, and this is what Courtois, Herein et al. Did in order to try to begin the mapping. And this is a major achievement of actually being able to take the actual velocity data out of the flow and show you how things move in the sky because of the local flow that they must have. So we zoom back and forth between the two images and go back and forth between the velocity space and others. And we find that we're in part of a large group that's falling towards the Great Attractor. So the Virgo cluster, in which we are in the kind of center right, is flowing towards this red area, and the blue is where things are flowing out of. The red is where things are flowing into, and the blue is flowing out. So these things are traveling on the order of thousands of kilometers per second, and we're looking at things that are millions upon millions of light years in size. So the great attractor is not visible due to the zone of avoidance because the Milky Way is blocking it, so we can't see it. But we can measure the flow or the apparent flow by seeing the residual speed away from the Hubble diagram, away from the Hubble flow. And so then we can look at a slightly different view that shows us the Virgo cluster flowing towards the great attractor and leaving behind an enormous, enormous void. The blue is where the voids are, the great attractors are the red are. And this shows how things apparently are flowing in the local rivers of the universe. And again, here's another amazing view of it that shows how the flow is going towards there's the local void, and how everything is kind of flowing towards both the Fornax cluster, the Virgo cluster, and then that's all going towards the great attractor. And so what we have is, that's the flow diagram, and then if we take that flow diagram and say really what's actually grouped together, we can name those groups, and we find that there are all these superclusters in and around our area, and we find that the superclusters are the local billion light years in area. The Laniakea group supercluster is in yellow in here, but we see all these other superclusters that are around us. And superclusters make up the largest size scale objects in the cosmos and are composed of enormous numbers of galaxies with vast, vast, vast distances between them. And the Laniakea group is not necessarily a gravitationally bound group. Most of these large stringy superclusters are not, but the clusters within them are. So there's a bit about our local cosmos just within the nearest billion light years and how we found it using redshift surveys and groups and clusters. We're continuing down the path towards understanding the Big Bang and some of the more important elements to it. We're not going to get into huge details like we're taking a graduate level course or something, but I'm giving you a taste of all the things that go into Big Bang cosmology. One of the most important things that we have then is that we found last time that galaxies come in clusters and groups, and that there's been some big surveys. So now we're going to look at galactic evolution and how things change. So again, cosmology is the physics and distribution and age of the universe. And the cosmological principle says there's nothing special about our location other than it's our place and our home. And as a result, the laws of physics are the same everywhere in the universe. All right, so what is out there way out past 10 to the 8th parsecs, 100 million parsecs in the billions of light years? What do we see out there? Well, what we can do is we can actually look far back in time and use very specific kinds of surveys to see how galaxies have evolved with time. And that's really what we're going to be talking about now. So it's thought that galaxies go from small, misshapen, extraordinarily blue objects and go by mergers and mergers and mergers to forming spirals and giant ellipticals. So it's thought that galaxies start in very tiny things and grow through gravity. And that's what we think it is. Now, given that's the concept, we should look for that in the observational evidence to see if this general sketch is true. So we can also think that there's definitely evidence for collisions because, as we saw, starburst galaxies have massive star formation. We could actually model the appearance of starburst galaxies by colliding. And the collision models and numerical models that show collisions between spirals can actually accurately map objects that we see deep in the sky. And in fact, we see some places that look like they have multiple cores, like some galaxies are supermassive giant elliptical galaxies and appear to have multiple galactic cores, and so they must be in the process of merging. Also, we know about stellar streams. There are stellar streams around other galaxies, and there's also stellar streams orbiting our Milky Way. And stellar streams are tiny little galaxies that are very low mass that get spread apart along the line, their orbital path, and as they orbit, they get stretched and pulled, and their stars get pulled into different orbits, and they no longer look like a galaxy, but now look like a stream because of the tidal pull between the near and far side of the little galaxy. So we should expect that larger interactions actually will create maybe some spiral interactions, maybe a small galaxy turn a large one to a spiral if it still has gas and dust, if it spins it up. So we can then say, well, do these evolutionary characteristics actually appear in the data? And so if we look at massive surveys, such as the 2DF Galaxy Redshift surveys, looked at about 250,000 galaxies, and they showed that, yeah, they're distributed in sheets and filaments and voids, and what's been looked at by this specific survey goes out to about almost 2 billion light years. And there we'd have a better view of it. And we see the redshift is about 0.25, or about a quarter. And that's a really good way of measuring. Instead of billions of light years, redshift is the big thing that we're going to be talking about. So the other one that's actually been a significant contributor to the universe, our understanding of the universe, is the Sloan Digital Sky Survey, which was a large 2.5 meter scope in Cloudcroft, New Mexico, and I actually went to grad school in New Mexico State, and I started off the very, very, very beginnings of the elements of the computer technology that went into the stuff. And so back since that's the early 1990s, we're talking this is like the beginning of the internet. So nowadays it would look, what I did was kind of minor, but yet it was groundbreaking in its time. And that's how it helped me to do other things in my life too, which is kind of neat. So this particular telescope, though, the Sloan Digital Sky Survey, which is shown here, its goal and its major survey ran from 2000 to 2008, and it cataloged millions upon millions of objects with hundreds of thousands of quasar redshifts and lots of galaxy redshifts. And it got photometry for billions of stars, galaxies, and quasars. And the goal with this thing was to make an accurate map of the sky and specifically hunt for galaxies on their redshifts. And there it is over the Sacramento Mountains, and in the distance you can see the White Sands National Monument. So this is a beautiful place, and if you ever get a chance to go to New Mexico and get up to Cloudcroft and say hello, do it. Anyway, this is one of their data sets. This comes out from the Sloan Digital Sky Survey. Comes from what they call their classic legacy archive, and it shows out to a redshift about 0.15, which is not as deep in this particular image as the 2DF survey. But over time, the Sloan Digital Sky Survey went much deeper and had much larger data set than 2DF. Well, what can we find that takes a little bit? So let's go back a little bit further and see why the Sloan Digital Sky Survey was even done, and why 2DF was done, and what motivated people to make these massive surveys. Well, the Hubble Space Telescope was launched a while back, and one of its major goals was to actually study the evolution of the universe. And what this was the longest at the time. It was released in January of '96. It was the deepest survey yet done by any telescope ever. And so this is what we call a pencil beam survey. And the Hubble Deep Field allowed us to see galaxies back to about almost 13 billion light years in distance. But we see that there's all sorts of arrangements and appearances to galaxies. There are about 1,500 galaxies in this image alone. But remember that the size of this image is very tiny. It looks kind of big here, but if you take a dime and put it 75 feet away, that is the size of this image in the sky. So it's a very, 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 very tiny image of the sky. And if 1,500 galaxies are in this direction of the sky, then they're everywhere. And this is not the deepest of the surveys, but this was the first one. And here's some elements from it, and it was the details was pretty controversial when it first was done, because nobody actually thought that this would actually use Hubble time wisely. But it ended up being an amazing, amazing set of discoveries, and we see most of the objects in here are galaxies. There are some faint red dwarfs, that are Milky Way objects. Those would be the stellar objects that are in the foreground, but most of the tiny, tiny, tiny objects in the background are galaxies. Again, here are some more details from the Hubble Deep Field, and there were 342 frames taken over the course of 10 days. So this is a huge, huge undertaking, and the size of the area this was one of the longest exposures ever done to date in 1997. All right, so but that wasn't the first then. Considering that was something that actually yielded results, then people said, well, let's keep going and get more. So the Hubble Ultra Deep Field, based in part on that, surrounding that area. And so what you see is the purple circle here shows what the Hubble Ultra Deep Field looked at, and that the circle illustrates the size of the moon. And then there's the green outline, which is the GOODS survey, and this is the GOODS North group. And so there's a very large image that was created out of that. And the advanced camera for surveys on Hubble Space Telescope is a tiny little blue block in the center, and the near-infrared camera and multi-object spectrometer, or NICMOS, also on the Hubble Space Telescope, was used to do deep imaging. So a series of images were given in this whole area in order to discover exactly how deep, what kind of depth we have. And the Hubble Ultra Deep Field then was released in 2003, about 6 years later. And this holds this also contains the Hubble Deep Field, but there's now 10,000 galaxies in this visible light image, and so they used so now the visible light band was used, and there are some very, very, very red galaxies, and the dimmest objects and tiniest galaxies were when the universe was only about 800 million years old. And so as you see when close-ups of this image show that when you look at deep, deep, deep into this image and look at the highest redshift objects, then those are small blue misshapen galaxies. And you only get fine structures like spiral galaxies in the local universe, meaning today. And there's something really interesting about this that we'll get to. But this again was an enormous undertaking with 800 exposures, taken over 400 orbits of the Hubble Space Telescope around the Earth, about 11 days of exposures. And this utilized the advanced camera for surveys. And then they utilized with the NICMOS experiment, looking at the near infrared, to actually look at objects who would be strongly redshifted. And this gives an important element to see what are the deepest objects in this field, and that allows you to see further back in the past, because if something is getting greatly redshifted, it will probably appear in the infrared rather than visible. And so you can actually see farther back in time using this, and that's why the caption of this shows that it's about 400 million years after the Big Bang would be the deepest and faintest objects inside of this. So the Hubble Ultra Deep Field is actually in the northern constellations. Actually, no, this is the Hubble Ultra Deep Field south. It looks in the exact opposite direction, and we're looking in the area of Eridanus in the constellation Fornax. So there are many details in the Hubble Ultra Deep Field that show the evolution and state of galaxies. You can see some extraordinarily misshapen objects, and only the larger objects, meaning the closer objects, meaning objects that are in the local universe, are actually things that are grandly structured, such as spiral galaxies. But if you look in, say, the lower right image of these six, you see in the kind of the left-hand side of the lower right object, you see a really distorted and misshapen thing. In fact, all the objects in there are distorted and misshapen, and only recent objects, meaning very nearby and at low redshift, have the appearance. And what we're actually beginning to see is that something that looks like the Milky Way only appears now. If the universe was infinitely old, then we should expect to see things just like the Milky Way, but extraordinarily far away. We do not see that. What we do see, though, is the Milky Way is only a recent thing. And if we look farther out into space, and therefore farther back in time, we see that there is an evolution of galaxies from then to now, and we do not see anything in the deep, deep, deep past that looks like anything like the Milky Way. So this is again a prediction of the Big Bang, that there would be a baby picture of the universe and an adult picture. And baby pictures predict that if the universe had a beginning, then if you look farther out into space, you're looking farther back into time. And therefore you should see things as they were ago. And if the universe was infinitely old and didn't have a birthday, then you should see Milky Ways and things mixed in with baby galaxies. But we do not see that. We only see baby galaxies long ago and far away. So the Goods Field South that we described a bit, this was presented at the AAS conference, American Astronomical Society conference in January 2010. I had an interesting time seeing this. They printed this out and put it on a wall at high resolution. It was about 30 feet long, I think, and about 15 feet high. It was an enormous poster that they printed out. But the goal with this thing was, again, to show that the images of that galaxies could be seen when we look perpendicular to the plane of the Milky Way, and as we look very far deep out, we get to see how galaxies have evolved with time. And here are some details from that image set. As we zoom in, we see many galaxies, but the deepest, tiniest, even the tiny little flecks, those are galaxies. Those are, because they're misshapen and they don't look like point sources such as stars. Now there are a few Milky Way stars in this image, quite a few, but most of them are, but there's more galaxies than stars. So the fuzzy objects are galaxies. And on the left-hand side, we see a number of tiny galaxies or globular clusters or dwarf kinds that are interacting with the two near spirals that we see. And we see kind of a little spiral off to the upper left that is much further away. And here's some details inside of that as well. We see a kind of a cluster and some gravitational lensing effects. On the upper left there, we see a gravitationally lensed galaxy. And we see the ranges of redshifts in here. So if you can go, I will post the actual images and the location where you can find this on NASA's website, so you can go take a peruse, so you can see how far back in time we look. All right, these are some really cool images. And again, almost all of the things that we see in this image are galaxies, as opposed to stars. But part of the ultra deep field that was observed were some extraordinarily high redshift objects. So in 2011, a particular ultra distant object was seen, where its redshift was measured in a very special way, which I'll describe in just a bit. And if it is a tiny, dim, misshapen, compact galaxy just made up of blue stars, wait a second, if it's made of blue stars, why would it be red in the image? Well, okay, since it's not like a mystery game, it's red because it's been redshifted. It's been redshifted deep into the infrared. But in order for it to be seen deep in the infrared, it must be extraordinarily bright. And if it's high redshift and still visible in the infrared, then therefore it must be bright. And therefore whatever was emitting it was emitting copious amounts of blue light. So this is a time when this particular galaxy, whatever it looked like, was a mishmash of stellar activity. So let's zoom in and take a look at what this ultra deep object is. And has the highly enjoyable name of Ultra Deep Field J 395-46284. Okay, that's not very illuminating. This was done by Illingsworth at Santa Cruz and Bowens and Hubble Ultra Deep Field 2019. And so we can zoom in and see this little bitty tiny red dot, which is this ultra high redshift object. And well, you know, now we're looking at the actual pixels on board the Hubble Space Telescope itself, and that is the pixelation, that blocky appearance is the appearance of the actual object in the picture itself, and the boxes are the individual pixels on the camera for the Hubble Space Telescope. And I provide a couple of links here that show an interesting thing we're going to talk about called photometric redshift. So photometric redshift is what you can do when you have a high redshift object and a lot of filters. So the Hubble Space Telescope is outfitted with a huge number of filters that it can use to put in front of the camera. So what they'll do is they'll focus on an object, and then they'll take an image of it with one filter, then another, then another, then another. And if you steady on it and look at, now we've got this funny thing going back and forth, okay? So what we're seeing is an image of a galaxy, and if it's red shifted, it will simply disappear from the long the short wavelength, meaning the purple and blue side of this, which would be the left-hand side. And as it's getting redshifted, it will appear only on the right. So why does the light disappear and go to zero? That's because there's hydrogen gas in the way. And as the light traverses the distance of the cosmos, as it traverses it, the hydrogen gas absorbs it at a specific frequency, but it's been redshifted, so it gets absorbed at every wavelength in between. So you're going to find that there is no light left over at visible wavelengths, because as it travels, it keeps passing through hydrogen gas at different redshifts, so it can absorb at different wavelengths. That's really interesting. So we're left with, if you only see it in the longest possible wavelength band filter, and it's the only signal is in the long wavelength filters, such as the F160W that we see there, way off on the right-hand side, and it's only visible in that one. That means it's been so strongly redshifted that the only way that galaxy can be seen is if it's a redshift exceeding that of 10 or 11. All right, so an example galaxy then, the Hubble Ultra Deep Field, the Hubble Ultra Deep Field 2009, and the Extreme Hubble Deep Field, which is XDF, actually integrated all these things together and looked at all the various filters that the Hubble Space Telescope can see, stacked them together, and found that 3954628 Ultra Deep Field J object has a Z, or a redshift, of about 10, because it only appears in the Hubble H filter. It doesn't appear in BV, I, Z, Y, or J filters. And so we call this a photometric redshift, because the galaxy's light only appears at that wavelength. So we think it's a galaxy and not a foreground star, because a star will still have some emission at a little bit broader wavelengths, so it won't be only at these wavelengths. Although it could mirror that, but then you look at the shape of the object and say, oh, it's misshapen and it doesn't have a point-like source, so therefore it's probably not a star or some rogue planet in between the galaxies, because those things would be pretty dim. And so the galaxy itself can be observed, and we can posit that because it only appears in one of the filters, it must be at extraordinarily high redshift, and therefore it set a record of being a redshift of 10 when the universe was 10 times smaller, more like 11 times smaller actually. So the Hubble Ultra Deep Field was then concluded in 2012, and those observations were taken between August and September, and that included numerous observations on top of it all, and using the Wide Field Camera 3 with numbers of different filters, so they actually started adding different filters together. And the goal would be then to say, if you can add all these filters up, you can finally get photometric redshifts, and that's what's been highlighted in this image is the highest redshift objects in the entire field. And we see that there's a couple of them at high redshift 8, another one at 10. Inside this field, another tiny object at redshift 9.5, and another high redshift object at 8. At almost 9-ish, and then the highest redshift object is the one we were talking about at 11.9, which is an enormous time, which is when the universe was 1/10 of its current age, or 1/12 of its current age, and 10 times smaller. Remember, we talked about redshift indicates the size of the cosmos, so it's actually about 12 times physically smaller at that time. So the Extreme Deep Field then stacked all of these images together and made it for an amazing panorama. They took all the legacy data and all their own current data and pulled it together to make one image, so it actually had many months of time. And this is a common technique that amateur astronomers use in order to stack images together to make a very pretty picture, and it actually cleans up the image because you can actually eliminate noise by doing that. So the more data you have, the cleaner your data is, and you can say, oh, you have a pixel in this image but not in that image, and so that must be its noise. And so this allows the image to be very well cleaned, and the only thing that's left is data. So this one small image shows 5,500 galaxies at various states in evolution. And we see there's the proof, and that we have some extraordinarily distant objects, and there was one that showed a redshift, a supernova in a galaxy inside the Hubble Deep Field, which demonstrated the redshift was at a redshift of 2. So that was a very high redshift object to see. All right, but that's not all. So people kept hunting and hunting and hunting, and eventually found inside that field some objects that are worth following up on. And the Hubble Space Telescope, led by Pascal Oesch at Yale, in March of 2016, instead of just doing a photometric redshift, obtained an actual spectroscopic redshift inside of the most distant galaxy. So that is this is a much more difficult measurement. Photometric redshift has a lot of problems, but if you can make an actual spectrum of it, then you know that you're actually looking what you can actually determine the spectral characteristics and determine it's actually a galaxy and not a star. So they were able to do this and find that this was a confirmed redshift by actual spectroscopy. That when the universe, we're looking that the light has traveled to us from this little galaxy for 13.4 billion years, and only when the couple hundred million years after stars first started to form. So we're almost looking at the very baby pictures of the universe. And so this is an amazing little discovery. And so you had to really pore over this image to say, hey, there's a very red-like object. Let's take a closer look at it. And so here is the image of that. So they cleaned up the Hubble image. We saw it from the other thing what it actually looks like. And we see this squarey aspect to it, which shows we're looking at the actual pixels of the Hubble Space Telescope. And this is the shape of this misshapen, really bright galaxy. Well, it was very bright at its time, making huge amounts of blue stars. It now looks red because of the redshift. And so it probably existed, at the time it existed about 400 million years after the Big Bang. And so how they did this was they took the spectroscopic slit of the Hubble Space Telescope and laid it across the object. And that's what these lines show, is the location of how the orientation of the spectrometer was. And so they actually could get some clear space in order to actually get a view of it. And so what they had to do is they took their full spectrum of it. That's what the top image shows. And then they figured out, well, there were some bright objects in there, so they must be contaminating a little bit. So they reduced the contamination by the objects there. And after they take out the contamination due to neighbors, then they had a clean spectrum. And then they had a model of what a high redshift galaxy should look like. And then they reduced the clean spectrum by the model, and they got what looks like static. And that bottom one is the residual, which is static. And so that's the best you can do, is create static, which is random noise. And so they feel like they've actually gotten it. And so since this spectrum took 12 orbits over 3 days of focusing on just this one little object, they found that they could model the spectrum. So the upper portion is the actual spectrum of it. And then the modeling shows where the data points lied and how they could actually say, okay, it's basically noise to the left, and then they have an actual spectrum that begins with the GRISM showing it's an 11.1 redshift object. So this was it is currently the highest redshift object measured spectroscopically, which is really interesting. So it's the farthest galaxy that Hubble probably will be able to see, and it still doesn't get to when stars turned on. It's looking at extraordinarily deep objects, but Hubble's aperture is not large enough. It simply is not a large enough aperture, and it doesn't have the infrared capability, and that's going to have to wait till the James Webb Space Telescope is launched. So the previous record holder was about 700 million years after the Big Bang. Now it's something that's looking at about 400 million years after the Big Bang, just after stars started forming, only 200 million years. So we could think that if stars that are supermassive take only 5 to 10 million years to actually form, then potentially we're looking at the first 4 or 5 or 6 generations of stars being formed in that misshapen sort of weird galaxy. And hopefully the James Webb Space Telescope will be able to see things. And this diagram kind of shows us what we've been seeing, is that structure forms with time, and galaxies evolve from being small, misshapen, tiny, bright things, and they merge and collide into larger and larger and larger objects until they form either supermassive ellipticals or small ellipticals or grand spiral galaxies. So just to give you a feel for where this location is, where that tiny galaxy is, we're looking at Ursa Major, the Big Dipper in the sky, and so let's zoom in to see how tiny a patch of sky that really is that we're looking at. And we keep zooming in and falling into this tiny patch, into the Goodsfield North Survey, all the way into tiny locations, and there it is, one little bitty object seen and observed spectroscopically by Hubble. And yeah, it's right off the handle of the Big Dipper. So what we've learned by looking at these deep surveys, which we'll call pencil beam surveys, like the Hubble Deep Field, Hubble Ultra Deep Field, Extreme Deep Field, is that we're able to see galaxies in different states of evolution. And so we can think of what a spiral galaxy like our Milky Way would look like. And it would when the universe was only 2 billion years old, is what the far right-hand pictures might see. And as time progresses from, say, right to left, I wish it was the other way, but hey, we're going this way. So when the universe is only 2 billion years old on the far right, things were tiny, bright, and misshapen. And as at 5 billion years after the Big Bang, we see multiple cores and multiple interactions in some bright areas, but not uniformly bright across the object, but they're larger and there's some structure that's appearing. By 9 billion years after the Big Bang, objects have gotten much more complex and larger in scope, and by the today type time, 13.7 billion years later, we're rounding to 14 just because this was in 1994, and still, their dark energy still had not been really discovered yet, so here we go. But 14 billion years, 13.7 billion years later, I should really adjust this slide, we see spirals and giant elliptical type objects. So galaxies evolve with time. We do not see Milky Ways in the deep past, so therefore a key prediction of the Big Bang, which is stuff had a beginning, it evolved with time, and we only see very far away long ago because it takes time for light to get here from there. So therefore, since we don't see structured Milky Ways deep in the past, the universe had a birthday, and we're seeing the tiny beginnings and how things evolve with time. And that's what the important thing is, and a key prediction of the Big Bang. Now, if the universe was infinitely old and infinitely big, and maybe there's matter being created, like a steady state theory, then you should expect it to be mixed together, like young galaxies, like tiny misshapen things, right next to old ones. But that is not the case. We only see the tiny misshapen bright ones deep in the past. We only see the grand spirals nearby. We only see the giant ellipticals nearby. So galaxies do evolve with time, and that is a key prediction of the Big Bang Theory. Tonight we're going to be continuing our quest into the extragalactic domain. We've talked about the types of galaxies, how they're distributed in space, but if we go out even further and just think about what is out there's happening way out there in the cosmos, we find that some of the most violent things in the universe are happening really close next door, considering cosmological distances. So we're going to talk about active galaxies and quasars, some of the most luminous objects in the universe, and how we know that, and what the strange observations we have of them are. All right, so active galaxies were discovered first in 1943 by Carl Seifert. He identified 6 kinds of galaxies. And well, actually, he studied them most exactly. He studied galaxies that had strong, broad emission lines, and they came from the center of the galaxy, coming mostly from the center, meaning the nucleus of the galaxy, and they were bright and compact galaxies. Those are called Seifert galaxies because, the guy who discovered them was Seifert. Well, in the 50s, radio telescopes found that some of the faint galaxies there were many faint galaxies found at the location of extraordinary radio emission, and they're called radio galaxies. Okay, so kind of had names for things before we really knew what they were, but so there were Seifert galaxies with broad emission lines and radio galaxies doing a lot of extra radio emission. But the thing is that when you look at it with optical spectroscopy, we see that there's broad emission lines in their spectrum. So What he did back in actually, why did Carl Seifert actually go and look at these things? Well, back in the day, prior to the 1920s and 1930s, Vesto Slipher and Edwin Hubble looked at a specific one of the nearby galaxies, NGC 1068, which is one of the Messier objects. I believe it's Messier 77. Found it to have a really weird spectrum. And that's an odd thing. And what they did is that Seifert did do the follow-up, and this was one of his first galaxies that he looked at. And he found that it had big emission lines of hydrogen, helium, and oxygen. And this is a more modern version of its spectrum taken by Mostakis and Kennicott back in 2006. And we find, if you look closely, that there are some really, really bright hydrogen emission lines, specifically the one at 6,550 angstroms. That is hydrogen. But we also see the helium line at 5,000, and there's also some other bright oxygen lines floating around in there too. But notice it just kind of has a flat spectrum from left to right, unlike the star spectra that we saw. So this is a very different sort of spectrum. And notice the hydrogen emission is extraordinarily wide. That wouldn't look pink. That would look kind of reddish, but it wouldn't have that distinct pink that we associate with those star-forming regions like we see in the spiral arms of this particular galaxy. So look at that little inset image, and you see that there's these pink glows. Those are star-forming regions, and that's the pink stuff. Now that is also at the wavelength of 6563, but notice the intensity of the light at that one specific wavelength. Also then, compare it with the bright kind of yellowish whitish center of the nucleus. The nucleus that we see in the inset is the place where this spectrum comes from. If we were to look at just the pink clouds off to the right hand of the center, we would only see a bright pink thing. So that at that specific wavelength, and we wouldn't see much else. That's why it looks that pinkish color. But the bright center of the galaxy is enormous hydrogen emission, which is very broad, as well as emission at other wavelengths too. But that's right down in the center. So it doesn't look pink though, which is really interesting. That's because it's bright at many wavelengths. All right, so if we then zoom in and look at just that central region, just that tiny, tiny dot in the center, not the outskirts, but the really bright center of the image of that galaxy, we find and focus in specifically on the wavelength band only for hydrogen emission. You can then see just how broad the emission line is. It's not just at 6563 angstroms. It's really smeared out and much, much wider. So it's almost 100 angstroms wide, and more like 50 or 60 angstroms wide, when an emission nebula like the Herein nebula or something like that will only be about 5 or 10 angstroms wide. So this broadening is due to what we call Doppler broadening. And Doppler broadening means that there's some clouds of gas that are moving towards us and some clouds of gas that are moving away from us. And some of them are moving extraordinarily fast, up to 5,000 kilometers per second. So how does that make it broad? Well, as you can see in the inset, we've got some cloud. Now we can break it down to individual particles inside the cloud. And we see that if bulk clouds, but let's just pretend we're looking at each of these dots as one individual cloud. So if it's really moving fast, then the hydrogen, and if it's moving fast towards us, the hydrogen can absorb light that would, or emit light. This is all an emission now. The emission from a hydrogen atom moving very quickly towards us, its wavelength of light will be blue shifted. And hydrogen moving very quickly away from us will be strongly redshifted. Now it's a mix between between high redshift and low redshift, with mostly in between. So that's what the color combination is trying to show in the image. So the average is going to be kind of right on the center of it, because the average is definitely on the center, but there's some high moving parts and some low moving parts. However, when we're looking at the central region of this galaxy, it's not really that. It's whole huge clouds, such as the pink dots. But they're really, really, really tight in, and they're really compact. And so they're moving extraordinarily fast, and they're extraordinarily bright. All right, so let's see some other observations of some other Seifert-type galaxies, which are really pretty. So in the center of this image, we see NGC 4151, which is about 62 million light years away. This picture was taken by Adam Block with the Mount Lemmon Sky Center at University of Arizona, and it was taken on a 32-inch scope, the Schulman Foundation telescope. Now, in fact, this was another one of the core group that Seifert additionally used to define the term a Seifert galaxy. Now, we are going to say this a couple of times, that the nucleus might hold a black hole. I mean, they allude to that in the next lecture, but let's actually step away from that, step back from that idea, and actually just look at the nature of what we're actually seeing. So that's actually funny is that there might be binaries that they orbit really fast, but the most important thing in this is that we've got a very, very, very bright, compact region of the galaxy that has very strong emission lines and looks kind of whitish, but it's bright overall. In fact, if you look really closely at this thing, you'd guess that the central region is easily just as bright as all the rest of the galaxy combined, and you'd be right. All right, another wonderful Seifert galaxy is NGC 1097. It's an extraordinarily bright nucleus and a bar-like structure. It's about 45 million light years away. It exhibits some of this, and this picture was taken by the European Southern Observatory's VLT on a couple of nights. It just so happened that I believe the president of Spain was there during this observation down in Chile. This is another Seifert galaxy, NGC 7469. It's the one in the upper right. It's actually colliding with the one that's in the lower left. This is almost 200 million light years away. That's why it looks fuzzier than all the rest. It's farther away, so it's harder to get it clear. And this is a Hubble Space Telescope image, and that you can go check out that image with. But again, we see a very, very, very bright, compact nucleus. So let's compare and contrast a bit. So a galaxy's nucleus in normal galaxies is the exact center of a galaxy. It's pretty much the same no matter what. So you have the galaxy's nucleus as the center. If it's the spiral galaxy, then it's the exact center of rotation of the entire galaxy. And ellipticals, it's like this dynamical center around which everything seems to be orbiting. And so, and then for normal galaxies, there's always some sort of really dense star cluster in the center. Maybe there's a supermassive black hole, almost always actually. And the spectrum shows of a normal galaxy lots and lots and lots of stars and lots of absorption lines. And so there's a bunch of things happening in there. There might be gas emission and so forth, but mostly it's stars and gas and dust. And it's a composition of those things. And so you can see that. And there might be some weak nebular emission lines, like the hydrogen emission lines. However, if you're looking at an active galactic nucleus, it's very different. Roughly about 10% of all galaxies have what we call our active galaxies or active nuclei. This is a really fuzzy number. You look around at it, and this number is very fuzzy. But the most important thing is that not all galaxies are active. But in general, an active galaxy shows a bright, compact galaxy, and sometimes it's brighter than the entire rest of the galaxy. The spectrum is different too than a normal galaxy. There are those strong, broad emission lines like I showed you before, and they're coming from extraordinarily hot, very excited gas that's moving really fast around. So these AGN, or active galactic nuclei, they're also variable. So if you were to take a spectrum of them, or their brightness, they vary on extraordinarily short timescales, for about a day or so. That means that whatever's making this variation is very small, meaning it has to be smaller than 1 or 2 light days across in order for it to be coherent enough that we actually see it. So spiral galaxies tend to be the ones that we see with this kind of Seifert level activity. But when we talk about like really dominant cores, it's only about 1% of them. So the truly dominant ones are kind of rare. An interesting one that is shown that I like to show, and it's kind of one of the quintessential ones that you'll see in textbooks and online, is the Circinus galaxy. It's a spiral that's really actually kind of close. It's only about 12 million light years away. It's one of the local neighborhood sort of galaxies. But it wasn't discovered because it's basically in the plane of the Milky Way until 1977. So since you're in the middle of a star field and dust plane, the Milky Way, it can easily be mistaken for something. I think, in fact, you'll look in the literature and you'll find that it was mistaken for like a standard nebula. You'll go, wait a second, it's a Seifert galaxy. What do we mean by that? So let's go, in fact, let's just go back. This comes from Astro Cabinet. So this is Dieter Villach. Dieter Villach. That's his work. He has some amazing, amazing stuff. I'm putting his link on the website. In any event, Then there's a classic Hubble image of Seyfert galaxies, the Seyfert Circinus galaxy taken with the Wide Field Planetary Camera 2, and that's what I put in the inset there. And that inset was taken with the Hubble Space Telescope by Wilson et al. At University of Maryland, and that was part of their study. So what we see, though, is that another astronomer, Judy Schmidt, took a bunch of the Hubble observations that were taken and then rejiggered them using Photoshop and so forth, and focused in on the core and made what she considered more of a true color image, and it does look very true colorish. The rings, and you can see the rings of the hydrogen gas, and that's why it's pink. And so the rings of, and then there's some ejected gas that's being shot out at high speed in the upper right. And this is actually not a very large region. There's two kind of ringish structures. One of them is about 1,400 light years across, and the very deep inner ring is only about 200 light years across, or 300 light years across. So really, this very close-by galaxy that's exhibiting extraordinary active galaxies in its active galactic nuclei is pretty close by. So we're seeing that there's some really violent things happening in this galaxy, because pretty much for the Circinus galaxy, it's all about the core and it's almost nothing about the rest of it. So I invite you to go kind of hunt that down, and I'll post the image, the link online. So and then there's another set. So Seyferts were one kind of active galaxy. The other one I alluded to at the beginning were ones discovered with radio telescopes, and these are called radio galaxies. And so what we see is we've got a combination of a NASA, NRAO, and NSF image. So what we have is we have a specific, the radio emission is in red, and it looks like that puffy, cloudy stuff. And then we have the wide field camera for the Hubble Space Telescope, and that was done by Keel et al. At the University of Alabama. But what we see is that the visual image of the Advanced Camera for Surveys wide field camera, which is the kind of optical sort of view, and then we have the red puffy glow, and that is the radio emission from this galaxy. So we're starting to get a hint that radio emission is very different than the rest of the emission of the galaxy. And even on the right-hand side of this image, we see some strong radio emission that looks like kind of a feathery sort of jutting sort of thing in the center that seems to be bright as a dot in the center, and almost like a tadpole-y sort of fish thing shooting out. Well, it's not a fish, it's a jet. So something's happening there, because those puffy clouds on either side are actually up and down, or forward and back. And notice the lower right one has a little bit of a bright spot in the center. That might be where the jet, which looks like the fish on the right, is finally slowing down or hitting some other stuff. So let's see what we can find out about radio galaxies. Okay, so radio galaxies emit strongly in the radio part of the spectrum. So that's what we think. So electromagnetic radiation, mostly in radio, so they're very strong radio emitters. And they can have huge, huge, huge lobes of gas, which are totally invisible optically. And they go perpendicular to the plane of the galaxy, which is interesting. So you've got this, this one is called Centaurus A. And Centaurus A is one of the brightest radio sources in the sky. And well, on the left-hand side is the image that is taken by the upper images is a European Southern Observatory picture image, but the one on the right was taken with the Parkes Observatory as well as other observatories to construct a very large-scale image of the radio emission of Centaurus A. So what I did is I took the image on the left and overlaid it with the image on the right to show you how big the radio lobes are compared to the image of Centaurus A. Now, what's fascinating is on the right is that the smallest structure, the littlest, tiniest lumps, are about 200 light years across. So it's, those are big things, but yet it's pretty interesting that there is structure that's large enough to be like 200 light years across. And we see a little bar to represent that says about 160,000 light years. So that's what the bar is worth. So this thing is huge. The extent of this thing is enormous, meaning it goes over almost 1 million light years across, which is big. There's a lot, and because this is a radio image, the dots are not stars. Those are other active galactic nuclei, other radio sources from other massively distant galaxies that are being picked up by this particular telescope as it looks deep into the cosmos to make this incredible, incredible image. So Centaurus A is the pinkish glow. That's the radio structure that comes from it that we do not see in visible light. And in fact, the radio energy is so incredibly large that each of the lobes is 20 million times the energy in just the radio sources as the sun puts out. And this is only happening at one wavelength. So 20 million times the energy of the sun's radius at specifically 1.4 gigahertz. So if you integrate it across all the radio emission, it's staggering amounts of energy that are being emitted. It's billions of times the mass of the luminosity of the sun if you integrate across all radio waves. All right, just for a very interesting contrast, this was a fascinating way they did this, and so the foreground telescopes are the telescopes that were used to take the radio image with the Australia Compact Array, and this is the image was done by Ileana Fain, Tim Cornwell, and Ron Eakers, and then the northern lobe was created by Morganti at Astron, and the Parkes Observatory data is by Jonks. So Sean Amy at Cicero and CSIRO took the night sky image. So if you could see the Centaurus A galaxy in the sky, that's where it would be, and that's what it would look like if you could see in radio emission. The radio sky is extraordinarily different than the optical sky. It would be a vastly different place. And so by comparison, we see the moon there in the sky. So really interesting, fascinating appearance. Other famous radio galaxies, one of the most important ones is Cygnus A. Cygnus A is it's like 500 million light years away. And what we see is that there's a central bright core, these long jet-like structures, and then these feathery lobes at either end. And the size of the object in the sky is only 1/2 arc minutes. But remember, an arc minute is the moon is about 30 arc minutes across. So this image that you're looking at would be about the same size as one of the smaller craters on the moon, or one of the visible craters on the moon through binoculars. So if you could see radio emission in the sky, you would see this extraordinarily bright source in the sky. That you would eventually, with a large telescope, if your eyes could see in radio, with a very large telescope. Anyway, so there's a jet-like structure which seems to be collimated over extraordinary distances, and at this distance, this is almost 500,000 light years, or 500,000 light years across. So it was discovered in 1939 by Grote Reber, and in 1951 as a bright, strong radio source. Is it actually one of the strongest? And in 1951, along with Cassiopeia A and Puppis A, were defined as radio stars, as people were looking at. So people didn't know. We first point radio telescopes in the sky. You just say, "What's that?" "Oh, it's a bright point-like object. Call it a radio star." Okay, great. And so they were identified with optical sources, and so they were called radio stars. Cygnus A is a radio galaxy, and the other two, Cassiopeia and Puppis A, are nebulae, with Cassiopeia A being that supernova remnant we talked a while back about. And in 1953, just a few years later, Jennison and Dasgupta showed it to be a double source with radio emission. So everybody's saying, "Wow, this is neat. Let's go look at it with radio telescopes." And all radio galaxies, especially this one, have a huge, huge, huge active galaxy nucleus in the core. And there's a supermassive black hole about almost 2.5 billion times the mass of the sun. And that's the image in red, because with radio you have to kind of give it levels. That was taken by the Very Large Array in the NRAO, National Radio Astronomy Observatory. And on the right-hand side, what I did is I found this in the Digital Sky Survey at Space Telescope Science Institute, and made a pic and grabbed it by the 15 by 15 arc minutes to show what the region of the sky looks like in visible light. And this is the red image. But now what I'm going to do is I'm going to shrink it down and show you where it kind of appears on the sky. So that's roughly what it would look like if you could see it. I don't think the orientation's right. I think I got that wrong. But the point is that it's kind of big, it's really bright, the galaxy itself can be seen in visible light, but the lobes cannot be seen in visible light. They can only be seen in radio. And it's one of the strongest radio sources in the sky at 500 million light years away. Another extraordinarily bright one is the Hercules A radio galaxy, and it was taken. The pinkish glow was taken by the Very Large Array at 3 different bands, and they mixed it together to form a red, green, blue, and made some good images. And then the optical is from the Hubble Space Telescope Wide Field Camera 3 and UVIS. So this thing is almost 2 billion light years away, and it's centered on a supermassive elliptical galaxy. And there's a hugely bright galaxy in there. It's a 2.5 billion solar masses and much bigger than the one that's in the center of the Milky Way. And what we find is that it kind of doesn't look like much in visible light, as you can see in the lower left-hand image. But since it's the brightest radio-emitting object in the constellation Hercules, it's kind of crazy that this thing is, 2 billion light years away. And it's even at that distance, it's almost 2 million light years across from edge of lobe to edge of lobe. So something is making these jets. Something is making the jets. Something is keeping it collimated for almost a million light years, at least 500,000 light years. And then the radio emission then gets deposited out there, and then it still glows in radio light. So the question then becomes, what exactly is making that radio emission, and how does it stay in this jet-like format? And that's a big, 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 big puzzle. So there's the optical image of the visible image of Hercules A, and there is the Hubble, and then there's the VLA image overlaid on top of that. And this is a Hubble heritage image. Well, what exactly is it? So it's supposed, because it's radio light, so it has to be very low energy radio light, that there's a strong, strong, strong magnetic field. And that magnetic field is actually causing electrons to spiral around. And that's what an electron will do in a magnetic field. If it has any motion, it'll kind of start to go around the magnetic field lines. It'll form a curlicue. Now, if it's moving really, really fast, then what will happen is it'll form a helix, and it'll scoot around, and if it's traveling at almost the speed of light, it has a specific kind of spectrum. A single photon, a single electron, will make a spectrum of light in radio light, like the hump that we see in the lower right inset, which is a single contribution from a single electron traveling at nearly the speed of light in a very strong magnetic field, or at least in any magnetic field. And some of the electrons are more energetic than others, and so as they travel along the magnetic field lines, each one of those electrons each emits one of those kind of humpy sort of spectra. So if you add up all the contribution from all of those individual electrons, you get what the red arrow is pointing to, which is that dashed yellow line, which kind of looks like the merging of all of those spectra. So you get what's called a power law spectrum. And that power law spectrum looks completely different than, say, a black body spectrum like we saw coming from stars. There's no absorption lines in synchrotron radiation. It's just this flat feature. So, well, we know about synchrotron irradiation because of studies in particle colliders as well as nuclear physics studies. So this process is well understood, and it's interesting to be found in these radio galaxies. So here's another diagram to show it, and we see the electron zipping around in the magnetic field, and as it goes around and around and around, it emits light. And as it emits light, it loses energy and therefore goes a little bit slower. So we also see then the image of the sum of all of these things, and I grabbed this image from Swinburne EDU, so you can go take a look at this. This is online on their website. Now on the left-hand side, I kind of grabbed this other thing from Wikipedia to kind of try to show what I mean and why this is a special kind of spectrum. Now if the electron is spiraling slowly, meaning, kind of fast for normal people, like it'd be going faster than a person can go, but if it's kind of spinning slowly, not at nearly the speed of light, the emission that an electron would make, because it is accelerating, because it's going in a circle, as it goes in a circle in a magnetic field, it will emit light, and it will lose energy. And that light emission pattern is shown in that kind of donut-y sort of bagel thing that we see, and that's the way the light spreads out from the electron as it slowly goes around, if it's moving slowly and moving in an electric field, or in a magnetic field. But now if you take the same magnetic field and accelerate the electron up to nearly the speed of light, you get what are called relativistic beaming effects, where all of the light gets beamed in one direction. So the direction that the electron is going. So that shape of the emission as well dictates how the spectrum will look. And that's what we see, and that helps to this understanding of how it works and how the emission actually works with the light, gives us an understanding of how we might get to the upper right-hand sort of individual electron thing. But this is called relativistic beaming, and as the electron spins faster and faster around, actually it goes very fast and loses just the tiniest amount of energy because it's radio light. It's got a huge amount of energy on its own, but it emits that light and gets lower and lower energy. But as they all emit in this particular way, according to this model, you get the sum of all the contributions. And that model is also borne out by looking at nuclear physics labs. All right, so given that that's how these things kind of make their emission, let's look at some of the zoo of crazy things that we see out there. In the nearby Virgo cluster, the galaxy M87, which is an enormous supermassive giant elliptical in the Virgo cluster of galaxies, about 600,000, about 70 million light years away, roughly. And what we see is that there's these enormous, the lower left-hand image is an optical light image, but on the right-hand side is a radio image of the same galaxy. So this is a very strange thing that they're completely different. There's these puffy things around it. There's these weird shapes. I don't know exactly how they superimpose, but the structure on the right is much larger than the Milky Way. At 200,000 light years across, this thing is easily, the green puffy thing, is easily twice as large as the entire Milky Way galaxy. But yet there's really bright core compact regions, and then you see something that looks really jet-like that's pushing stuff out. You can almost imagine that there's this jet of material being thrown out in two directions. One of them towards us and one of them away from us. So now here's a VLA study, very large array by the National Radio Astronomy Observatory, done by Fraser Owen and John Batia at NRAO. And so we see that the VLA, looking at 20 centimeter radiation, shows that large jet-like structure in the center. So we see the big map. Now we zoom in with the 20 centimeter VLA, we see a very tiny jet-like feature. And the right-hand side is a jet, and the left-hand side not so much. And then we zoom in closer and tighter with the VLA at 2 centimeters, and we see that the jet has deeper resolution. It has knots and baubles and beads type of things. And then zoom in even tighter with 7 millimeter wavelength radiation at the VLA, and we can see almost the central core. Get even tighter and tighter. We can get as tight and as small as we want, and you still get smaller and smaller radiation until you get to this amazing imagery where you now have to go to the bottom two, which are VLBI, which is very large baseline interferometry, which is not just the VLA telescope, but numerous other radio telescopes across the United States and across the world, all combining their data together to get higher resolution of that interior structure. The VLA is only so big, so the resolution gets poorer as you zoom in. But if you integrate a bunch of radio telescopes together, with such as the VLBI, then you get much higher resolution. But notice as you zoom in, you still maintain a compact, tiny source. So the lower left-hand image shows something that's only a quarter of a light year across. What's a quarter? Like 2/10 of a light year. 2/10 of a light year is a couple of light months, right? Or even 1 light month. 1 light month is 30 light days. 30 light days is, wow, that's pretty, that is, remember the size that the Voyager has gone is almost a light day. So the image that you're looking at across, if you look at an individual pixel, a couple of pixels across this thing is what the Voyager has traveled since it was launched in 1977. So a few pixels on this lower left-hand image is the distance Voyager has gone from Earth. So this is a really tiny, compact, extraordinarily bright object deep down in the core of M87. Once again, there it is. We're zooming in, a VLA on the upper box and the VLBA, very long baseline array, showing the inner tenth of a light year. Remember, a tenth of a light year is on that order. So we're looking at objects or resolution of a bright compact radio source that is not that much bigger in terms of that bar. So that bar is one. It's like 1/10 of that bar is what the Voyager has traveled since its launch. So actually, if the Voyager were a super duper duper bright point-like radio source, maybe it could be resolved, but it's not. It's not that bright. In any event, this is to just try to show you the size scale that we're looking at something that can be easily measured in terms of solar system size scales. And there it is with the Hubble image showing the jet in visible light. So there's something going on in radio, there's something going on there, and we described that the radio emission comes from synchrotron radiation that's coming from the spiraling of electrons in a strong magnetic field. Now you can get visible light and you can get X-ray radiation from that as well, and that's what we're seeing here in this jet coming from the center of M87. And there we see M87 using the Hubble Space Telescope done by J. Madrid at McMaster University, showing actual changes in the visible light of that bright knot in the center of the galaxy of M87. And just for enjoyment, to get you an idea of where the heck this thing is, the lower left is M87, the giant, supergiant, massive elliptical galaxy. It's in the Virgo cluster, and we're seeing a cluster of galaxies here. And this was taken by Chris Mijos and the colleagues at the Brunel-Schmidt telescope. And this was done with the European Southern Observatory. And they took out all the foreground stars, and that's why those got those spots of bright. Because, you know, we just want to deal with the stuff that's actually the galaxies and not look at the stuff necessarily and not be distracted by things that are in the foreground in the Milky Way. All right. Another thing we can remember that with active galactic nuclei is they're really luminous, extraordinarily luminous over all wavelengths. And on the left again, we go back to our favorite, which is a Centaurus A, which is one of the most it's a favorite target for active galactic nuclei studies. And on the left, we see a visible light image taken by Sarah Tololo at the IAO in Chile, the Blanco 4 meter. But on the right-hand side was taken by the Spitzer Infrared Space Telescope, run by NASA Jet Propulsion Laboratories. And so we have emission from that, from thermal emission, we have dust and gas and thermal emission, but you can also still see dusty, gassy distortions. It's extremely bright in the center. And we also see that there's some sort of jet-like structure coming above and below. So there are extreme activity in infrared too. And if we look in ultraviolet, and this comes from the GALEX mission, and if there's some jets coming off of that, and maybe even the jets that are coming off of that indicate star formation that's happening deep in those jets as a result of collisional activity. That's one possibility, but perhaps it's just synchrotron radiation again. But this is ultraviolet light, with the bluish, whitish light being higher energy ultraviolet and the yellowish light being lower energy ultraviolet. And so ultraviolet is interesting because you get these kind of circly structures, and that's because of the nature of the detector itself, not because they're bigger objects. No, we're looking into those yellow spots typically are stars in our galaxy. All right, but you also see there's a density around them, so that indicates there's some activity happening around Centaurus A. Notice there's a cluster of those light yellow dots, so there's something happening as the two galaxies are colliding and making hot stars. Again, we can look at Centaurus A, and we see in X-ray light. This is from the Chandra X-ray Observatory from one of their earlier studies, and we can see that the jet is formed from various processes in X-rays, and we see the bubbles that are visible in radio light are also visible in X-rays. So Centaurus A has a completely different appearance in X-ray, and we see an extraordinarily luminous, hot object in the center. And the bluer the light in this image, the more energetic the X-rays we're looking at. So how do we get X-rays out of this? Well, one way is, remember that there's electrons spiraling around at nearly the speed of light, and they're emitting radio light. What can happen is the radio light is a low energy photon. The electrons are moving really fast, and so they can collide with the photons and give some of their energy to the photon and bump it up to an X-ray. So the strong magnetic fields keep the electrons flying. Something's accelerating the electrons to nearly the speed of light and keeping them entrained inside of these jets. And so we get X-ray emission from the radio light that they emit. So not only do they emit a radio light, they then billiard ball some of the light to get up to X-ray emission, and we call that inverse Compton scattering. So it kicks them up into high energy as they interact and gives them more energy. And that's where those jets appear. That's what most of this emission that you see comes from. So here's a series of images, a composite of radio imaging, X-ray imaging, and optical imaging from Chandra, VLA, and the Hubble Space Telescope, as well as others, to put it all together to show you what an active galaxy in the nearby solar neighborhood is like. Well, not solar, we're talking about 14 million light years away. So we've alluded to the idea that these things are bright at every wavelength, and the active galaxies are. So a normal galaxy seems to be usually a collection of stars and gas and dust. So the lower curve shows a typical normal galaxy, which would have a dim radio, infrared, and visible, but it's mostly an addition of a whole bunch of stars together. And we're kind of smoothing things out to make it easier to understand, but that's the basic idea. But in an active galaxy, there's enormous radio emission, there's enormous infrared emission, there's enormous visible light, and much, much greater X-ray emission than in a normal galaxy. Normal galaxies don't tend to glow in X-rays. So the radiation from these galaxies is what we call non-stellar, meaning it doesn't come from stars. Just like I described, we have electrons zipping around making radio light, and then they kick it up to X-rays. So this is not a thermal process that happens in stars. This is happening in magnetic fields as things are moving at nearly the speed of light. And something's actually accelerating these electrons and protons, or mostly electrons, seems to be the dominant model to actually make all this light is high-speed electrons. So something's happening deep in the galactic center to actually do that. So just to kind of really show a really high resolution spectrum, so we go way back to Seifert's original paper, and this is by Brown and Mistakis again, and this is from June of 2014, where they took a large number of data and made what's called a spectral energy distribution, or SED, the entire spectrum of the galaxy, from very, very deep in the ultraviolet all the way to very long infrared. And so the visible light wavelengths are only in between about, say, 4,000 and 0.4 and 0.7 on this graph, at the short end of the wavelength in microns. But then everything to the right is in infrared, and everything to the left is ultraviolet, is out into the ultraviolet. We don't go to the X-rays in this particular image. That's unfortunate. But we're seeing that this is very different than most normal galaxies because of the excess brightness in infrared, as well as the enormously bright hydrogen emission lines, which you can see in emission here. Now we're going to talk about the nature of the rapid variations. Seifert galaxies vary really rapidly, and this is kind of a schematic diagram by which what we mean. They gotta get bright and dim by 2 or 3 or 5 times over the course of a few days or a couple of years, and they can actually be measured year to year, day to day, and month to month, and sometimes even day to day that they have their time variations. So what do we mean by that? This was a study done by Arevalo et al. They published it in Monthly Notices in 2009, and this is an active galaxy, active galactic nucleus, NGC 3783. And they took 3 different sets of measurements, one in X-ray and one in Johnson B filter and Johnson V filter over a number of days. And as we can see, there are lots of variations, and this is varying, just the nucleus is varying in brightness in X-ray quite rapidly, as well as in the Johnson B, which is a visual filter, the blue end of the spectrum, and Johnson V, which is smack in the middle of the optical. So then we actually zoom in on a very short period of time when they actually when they were able to take measurements up to 3 times a day, especially for the X-ray data, and they found that there's very high variability for the B and V photometry of just the nucleus of this galaxy. So this is a relatively nearby one, or else you wouldn't be able to get B and V photometry for it of this quality. But you can see that the X-ray variability can vary up to a factor of 2 over the course of literally hours, and the amount of that can come with a B and V in terms of, well, the word flux means how much energy you're getting per second into your tiny little detector, meaning ergs is a measure of energy, erg per second per square centimeter. So if you had a square centimeter detector, you would get this many ergs per second. And an erg is a measurement of energy, just like a joule. So it's just in CGS units rather than SI. Okay, so we can see that there's extraordinary variability on the order of hours. Next, we find the brightest radio sources in the sky are called quasars, or quasi-stellar radio sources. And it wasn't enough to find radio galaxies, and they found extraordinary bright, point-like sources of radio emission. And then when they looked at the photographs, they found there was a really fuzzy, tiny, fuzzy little star-like object that seemed to be like a star. And then when you look at the actual spectrum of one of these things, you find wild, broad emission lines that nobody knew really what they were at the time. And so they said, okay, it kind of looks like a star. It's got a lot of radio, so it's a quasi-stellar radio source, or quasar, quasi-stellar radio source. So that's where the word quasar was neologisms about. And one of the first bright ones was 3C273. It's one of the nearest quasars in the sky. It's about 1 billion light years away. So to give a little history about it, 1963, Martin Schmidt then looked at 3C273 and said, well, what the heck with this? He recognized that, unlike everybody else, there was a really huge debate about this at the time, and it took a long time for people to be convinced, is that he recognized that if you simply took the normal absorption lines in quasars, or normal emission lines in quasars, and simply redshifted them all the way really deep, what do you get? Well, you get if you take normal emission lines or normal absorption lines and redshift them massively, then you get this thing that's like, oh, it fits perfectly, it's just highly redshifted. But remember, Hubble found that redshift means the greater the redshift, the more distant it is. And so the Hubble relationship by 1963 was well established. So nobody wanted to believe at 1963 that these things were that far, because if they were that far and that bright, that meant they were insanely luminous. So if they were at extraordinary distance, Martin Schmidt said they're really luminous. And he was correct, and that is true. And so here's the typical spectrum for 3C273, and we have a lab comparison by spectrum. So let's actually kind of go through what we really mean. 3C273 has bright emission lines in hydrogen, and so this is a sample wavelength thing, and I overlaid the optical spectrum on it. And know that we have the hydrogen alpha, which is that bright pink line that we see, that gives us the pretty pink of like the Herein Nebula or the Trifid Nebula or something like that. That's been pushed all the way over into the deep red at nearly 7,600 angstroms. And so it went from 6563 all the way to 7400. So that's a big shift. So how big a shift is it? Then we can then determine the redshift this way. We know it was observed at 760 nanometers, or 7,600 angstroms. But we know that if it was hydrogen, it was emitted at 6,562 angstroms, or 656 nanometers. So you just calculate the redshift, we said and the following way, and we find it's a redshift of 0.158, which is an enormous redshift, which implies an enormous recession velocity, which implies an enormous distance. So quasars are discovered. There's over 250,000 quasars that are really known. There are many, many, many quasars that are known, and most of them come from the Sloan Digital Sky Survey. And this is from the Sloan Digital Sky Survey data release 12, and we can see this particular one has a similar redshift to 3C273 of 0.1954, and the tall right emission line is hydrogen alpha. So we have all sorts of things that are emission lines in there. Now, if we then go back and look at, say, let's take a quasar spectrum and put it in the rest frame and so forth like that, what's the real emission wavelength? Not what we see it to be, but what it would be at emission. So we eliminate the redshift out of the picture, and what do we get? And this is called a composite quasar spectrum. It was done by Vanderburg in 2001. And what we see is that there's enormous, enormous ultraviolet emission at the Lyman alpha line. That's for hydrogen. That's the Lyman alpha. Then there's carbon, ionized carbon, and magnesium ionized, as well as ionized oxygen lines and hydrogen as well, is an extraordinary emission too. So we've got this amazing, strange sort of broad emission lines, especially the Lyman alpha line, which is insanely broad, much broader than anything else in the sky. And it has kind of a semi-stellar sort of appearance, because look at that shape. It's almost like a star, but there's something weird about that on the left-hand side. And here's the total wavelength spectrum across all wavelengths for 3C273. And the circles are the actual data points, and maybe there's some bars that go up and down to show you how well it's known. But on the far right-hand side are extraordinarily energetic photons, like X-rays and gamma rays, and on the far left-hand side are extraordinarily long wavelength photons, like radio. But on that, there's three kind of humps, and there's like an additional sort of hump in the middle too. But let's actually look at the three tall humps. The one that looks kind of like in the middle hump that looks roundish, that's from thermal emission, or the sum of all the stars in the galaxy surrounding 3C273. And so that's what the data points there show. On the left-hand side is emission from radio emission due to synchrotron radiation, and that's the long wavelength stuff. On the right-hand side is X-ray and gamma ray emission that comes from the inverse Compton scattering process that I described before. And so there's an enormous jet. There's three separate processes that give dominant radiation. So the idea that this kind of models the spectrum really well, actually, when you combine it together. And the top line is just kind of the best fit overlay on top of the three underneath curves. And the other one down below is another contribution, which I forget exactly what it does. I think that might be dust emission. It's probably more like dust emission, because of it kind of goes up and then drops off rather rapidly. All right. Therefore, quasars are the most luminous objects in the universe. They can have up to something that's 100 trillion times the luminosity of the sun. 100 trillion times the luminosity of the sun. Not billion, but 100 trillion. Remember, the luminosity of the sun, of the Milky Way, is about 100 billion, or 10 to the 11th solar luminosities. So this one object can have 1,000 times the luminosity of the entire Milky Way, and most of the light from this is coming from the center of the object. This thing, I mistook. Some of them can be up to about 150 billion, well, almost 12 billion light years away. This is a bit of a large thing to say 15 gigaparsecs, because multiply it by 3 and you get too far. So I made a mistake with that. It's probably a 4 or 5. Anyway, so this is 3273. It's still pretty near, but its luminosity as a point-like object all comes from the central region, just like we saw in M87's study of the VLA. If we then look at other quasars, they actually thought that they were galaxies for a while and couldn't resolve them, so it took a long time for people to actually resolve the surrounding galaxy, because quasars are pretty freaking bright. So they're extraordinarily bright objects, and finally, this one was an image that was released in 1994 using the Hubble Space Telescope. There were other images that showed some pretty good observations from ground-based things that were extraordinarily good studies of this exact thing, but then the Hubble Space Telescope confirmed what looks like a bar-like structure in the center of it all, surrounded by what look like spiral arms. So we have that there's a host galaxy with an extraordinarily bright object in the center, and this must be a colliding galaxy. And something what's happening is that the quasar object is the bright central core. Quasars also have radio lobes, and this is another one. This is a quasar 3C175 taken with the VLA at 6 centimeters, 1996. And I provide the link there so you can go hunt it down. And yeah, you can see that quasars themselves, in addition to being bright luminous sources, are also staggeringly luminous radio sources as well. All right, so to kind of sum it up, we discussed in a previous lecture the luminosity of galaxies, and we found that irregulars are kind of the little bitty guys, and then spirals are lots of places where star factories are being done, and they're more massive. So they're more massive, they have more gas and dust, so they can be more luminous. However, ellipticals tend to be the collision train wrecks where things kind of mash together, and they can be little tiny things or super massive ellipticals like M87. But quasars top them all. They are the most luminous objects in the universe, and they can be up to 10 to the 14th times the luminosity of the sun, which is 1,000 times more luminous than the Milky Way. It's as though 1,000 Milky Way galaxies are compressed inside an area that we'll find inside a volume that's smaller than the solar system. So this is really catastrophically bizarre, that something 1,000 times more luminous than the entire Milky Way seems to be coming from a little volume that could fit inside the solar system. All right, so just in rough schematics, normal galaxies just have gas and dust, and they got a nucleus and such forth, and it's kind of pretty and such forth. But then we look at this as edge-on views, of course. If it's got an active galactic nucleus, then the center is really, really bright, and it's got bright, broad emission lines. It's probably formed by something like we call a supermassive black hole, which we'll justify next time. But a quasar is so insanely bright it drowns out that thing. It's not that the disk doesn't exist. It's that the contrast is so great that you can't see the disk. It's not it doesn't exist. It's that it's too bright to see it. So it's like, hey, stare at this light. Stare at my flashlight. Oh, I can't stare at your flashlight. It's too bright. It's exactly the point. You can't see this stuff on the flashlight. So this is the kinds of activity comparisons that we see between galaxies. So we're going to look next time at exactly what drives these galaxies, what makes this active galactic nucleus, and that's a really fascinating study that we alluded to with many lectures ago. We talked about the supermassive black hole at the center of the Milky Way. Now we're going to see that effect in full focus next time when we talk about the central engines of supermassive black holes. This time we're rounding out our study of the nature of galaxies and quasars and active galaxies by seeing how active galaxies and quasars form and evolve. So what is the central engine of an active galaxy? Active galactic nuclei all have one of the same properties. They have very similar properties. One of them is that they're extraordinarily luminous objects. They emit huge amounts of non-stellar energy, meaning the energy source doesn't come from stars. The energy output is extremely variable, and that means it's very small wherever it's happening. And there are jets and other signs of some sort of explosive activity. And around the central engine of an active galaxy, we find broad emission lines with them indicating there's rapid rotation. All right, so what exactly powers an active galactic nucleus? And again, these things have to be explained. The luminosities are on the order of billions to trillions of times, which is 10 to the 9th to 10 to the 12th, solar luminosities. They emit wavelengths all the way from radio all the way to gamma rays. They're extremely compact because the visible light can vary on the order of timescales of a few days, and X-rays can vary on the timescales of hours. So this is really interesting how quickly they can vary in their sizes. So something's got to be small and really bright. So to explain what we see, we use a black hole. The energy source of active galaxies can be usually explained by having accretion of matter onto a supermassive black hole. And by supermassive, we mean 1,000,000 to 1,000,000,000 times the mass of the sun, which would equate to a Schwarzschild radius of about 1/100th of an AU, up to 10 times 10 astronomical units, meaning the most massive black holes inside of active galactic nuclei, about 1 billion solar masses, would have a diameter that's larger than the orbit of Saturn around the sun. So these would be extraordinarily huge black holes. As material falls into it, it releases gravitational energy, and that settles into an enormous accretion disk around the black hole. And when it does so, it gets hotter and hotter and hotter and emits light through friction, and eventually loses that light, and that light leaves the system, and that hot inner part glows, especially in X-rays, right as it's falling into the inner region of the black hole. So just about one or two Schwarzschild radii, it falls directly in. So that's the leading theory about what powers a galactic nucleus. is that, and also when it falls in, the accretion disk spins round and round and round, heating up as it gets closer and closer, and there's magnetic fields that probably appear as part of this disk of material, because most of it, if it's going to be hot enough to emit X-rays, will be ionized and strongly magnetized, and that magnetic field will get wrapped around and create a toroidal magnetic field that can contain material that goes out in a jet. But remember, the black hole itself is extremely small with respect to the jet. And a picture like this is a very good image of what we might see as a jet-like material. So the disk would be surrounding it as material falls in, and as it gets closer and closer, it gets hotter and hotter by friction, and that magnetic field gets stronger and stronger, and you see a jet coming out of the center of it. And so this is the typical picture we see for a supermassive black hole, because even still, something the size of 10 astronomical units is very small compared to a light year, which is very small compared to a parsec. So still, even supermassive black holes are extremely tiny objects, and this disk that we see here would be many hundreds of astronomical units or thousands of astronomical units around. So the central engine can be billions of solar masses, and material that falls in can radiate up to 20% of its mass, in a very weird way of saying. It's not like it's radiating away its mass, it's that the binding energy of the black hole, as material falls into the black hole, the energy that's released is binding energy for the black hole. And so the black hole itself has less mass than the material that falls into it, and some of that gets radiated away. If you were to take the material that's there and spread it back out, it would gain that mass. So it's a sense of saying, where do you get that energy from? And the energy happens to be as a result of falling into a gravitational field. Black holes are extremely efficient at transforming matter into energy. Up to 20% of the rest mass of the particles are converted into light. And then that means that roughly a solar mass per year of matter is needed to power the brightest of the active galaxies, and they get their fuel from surrounding gas and stars, as we saw in that previous image. So you get this rapidly spinning black hole, acts like this enormous particle accelerator, and that creates these incredibly large jets that are seen in active galactic nuclei that are very bright in radio sources. So that gives us kind of our model for active galactic nuclei. You have three different types. You have a normal galaxy with kind of a bright core that might have a supermassive black hole in the core, but it's not really doing anything. A galaxy that has an active galactic nucleus has material that's falling into the supermassive black hole. But then we've got a third thing, the quasars, which are very strong active galactic nuclei that they're so incredibly powerful that they actually overwhelm the light of the surrounding galaxy. And those are the quasars. So let's look at a little bit closer towards them and see the observational evidence for all of these things that lead us to think that there's actually a supermassive black hole down in the center. If we look at this particular one, this is taken by the Hubble Space Telescope of NGC 4261, we see a dual image. The Hubble Space Telescope is the inset on the right-hand side, but it's also inset with respect to a visual light image and a ground base, as well as the radio observation of radio lobes. So we're going to piece apart each one of these things. First of all, this is an elliptical galaxy, as you can see in the left-hand side image. This thing's about 100 million light years away, and so the diameter across this thing is approximately 88,000 light years, or about 100,000 we just call it about 100,000 light years long lobes, and it's part of part of a galaxy group. Now, this particular black hole is roughly 400 million solar masses, and there's the disk on the right-hand side in the Hubble image shows something that's about 800 light years wide. So that's what that disk is, that's material that's falling into it. The galaxy itself is only about on the left-hand side, the whitish galaxy is about 60,000 light years across. But the jets go each about 88,000 light years long, the length of each of these jets. So you've got radio emission from the jets, you've got stellar emission on the left-hand side. The radio emission is in yellow on the left-hand side. The inset is an incredibly detailed, tiny image of just the core, the inner 400 light years or so. So the disk itself is about 100 light years across. And you can see that there's some extraordinarily bright emission happening inside the center of that disk, and where that lands in there, even still that tiny dot that's there, the black hole itself would still not be visible because it's much smaller than that dot that you see in the center. However, as material falls in, it gets entrained inside of the supermassive black hole, and that is the source of the jets that you see on the left-hand side. All right, so another more local black hole, which is, this one's about 100 million light years away, but something a little bit closer, about 70 million light years away, is the supermassive elliptical galaxy M87 in the Virgo cluster. Now this is the core of M87, and if we look at this is a gaseous, so there's a huge amount of gas that's orbiting at very high speeds. And so if you take spectra of the gases that are orbiting it, you get two different versions of it. They're on the left-hand side in the image, the spectra is in red, and it shows it's receding away, therefore it's a longer wavelength. And the right-hand side shows that it's rushing towards us, or it's blue shifted. So this is hydrogen gas as it's falling into it. And the light is either blue shifted or red shifted strongly, depending on where we take our measurement of our spectrum. So and by looking at that, it tells us how fast things are. If we know the distance to M87, so we can know the size scale of this object, because we know the angular size scale, we know the distance, so we can get the physical distance between those two little circles. And that shows us by Kepler's laws that by Newton's version of Kepler's laws, that the mass of the black hole inside of there is between, say, 4 and 6 billion solar masses, which is one of the largest supermassive black holes that is known. And that rotating disk is roughly perpendicular to a known jet of material. And in order to have the lines separated out from, as we see from this Hubble Space Telescope's image with the faint object spectrograph, is that the disk itself is rotating at about 1,000 kilometers per second, and that's just under 1% the speed of light. So it spans about a third of a light year, almost a half a light year. So it's going extraordinarily fast around in this massive wind. In order to power what we see, the gas is accreting on top of the black hole at roughly 1 solar mass every 10 years, or 90 Earth masses every day. So this supermassive black hole would swallow 90 Earths a day in order to show the emission that we see here. So this is the jet that's emanating out of the M87. You can see the jet in the inset, and there's the Hubble image that we see from it. So we have an inner region and then a jet coming out of it. And that jet is the jet itself is incredibly large, and there's probably the jet is probably occurring at about 7 parsecs away. That's where we see the jet occurring. But the displacement is not really real. It has to be happening right there, but the visible portion of the jet starts happening there. So it doesn't actually start to emit light until it's far away that we can see. But the base of itself, at the base of the jet, right down near the supermassive black hole, the base has to have a diameter of about 5 times the Schwarzschild radius of the black hole, and that supermassive black hole is powering it there. You can also take a spectrum of that jet and just the jet and learn that it's polarized. And if it's polarized, then there must be a strong magnetic field. So you have relativistic, meaning things going nearly the speed of light, in a strong magnetic field in order to polarize the light. What's amazing about this particular jet is that the total energy in the electrons that must be in this jet in order to make this is approximately 10 to the 13th times the energy produced by the entire Milky Way from all the stars in the Milky Way. 10 trillion times the Milky Way's emission in order to get the amount of energy found in this jet, which is a staggering amount of energy, all coming from there. So the center of this thing is brighter than all the Milky Way, all the energy in these electrons, which looks very wispy, but it's not. The energy is extraordinary. And the jets themselves extend up to hundreds of thousands of light years. So what can we see that's doing this, that's creating the energy content of of trillions of Milky Way galaxies inside of this kind of thing? Well, we can see that there's different ways of viewing active galactic nuclei. If you look at it from down above, you see that you're going to see along the jets, and you're going to see very strong X and gamma ray emission, and that's what you see if you're looking from above down. You'll see a jet coming towards you with lots of X-rays and gamma rays. Or if you look at it from the side, you'll just see the jets and a strong infrared emission, because you're not going to be able to see the central X-ray, gamma ray emitting area. But you will see the jets, and you'll see some strong infrared because of the material that's in the disk itself. So we get broadband radiation, meaning lots and lots of different X-rays from radio all the way to X-rays. But if you only see the jets and only mostly infrared, then you're looking along the edge of it. So one engine can provide lots of different ways of seeing active galactic nuclei. And that's another way of looking at these particular objects, because some of them are radio lobes and some of them are radio cores. But if you see, looking down the radio lobe, you can see, if you see just an active galactic nucleus that's just a blob of radio emission, then you're looking straight down the lobe. Straight down the jet. But if you see it from the side, then you can see both the jets and the lobes, and that explains the appearances that we see for active galactic nuclei that we saw in the previous lecture. All right, so what does it look like close up to one of these things? Well, if you saw it, then you'd see a huge amount of material falling in, and as it fell in, the things would be taken away in the jets, and if we ride along with the jet as it goes out at many times the speed of light, we would then see some enormous emission from the side. So there's material that's falling into the supermassive black hole. A huge magnetic field creates a jet-like structure, and material comes out of that jet-like structure. And if you look down the jet, you see huge amounts of X-ray and gamma rays. And the X-rays themselves are being produced deep towards the core, and that's what we get to see as the jets from the side. All right, so if we then, here's kind of the model. Is an accretion disk around the supermassive black hole. Remember, the supermassive black hole is pretty small. It can be on the order of an astronomical unit or a few, or just like a tenth of an astronomical unit up to 10 astronomical units. So the diameter of where all the action is very small compared to the rest of the galaxy, which would be tens or hundreds of thousands of light years across. So the supermassive black hole and all the energy that's coming from it is coming from an extraordinarily small area. And if there's very small variability, then that's what explains it, because the size scales can vary on the length of a day or two, and that's roughly the size scale of roughly 10 to 40 or astronomical units. So if it's going to be coherently changing, then the entire disk must change. And if the disk is on the order of tens or so astronomical units, that's what we see. Now, the X-ray emission comes from even tighter in, which then, if it can vary on the order of a few hours, which is what we would see if it's on the order of a couple of astronomical units. So X-ray emission comes from deep in the center, and coherent changes come from the entire disk itself. And this one model then can take care of all of the known variability of all active galactic nuclei. And as an example, we can look at Centaurus A. It's one of the nearest galaxies to us. It's only about 10 or roughly 15 million light years away. It's a close radio galaxy, and it's also the fifth brightest galaxy in the sky. So there's lots of observers in the southern hemisphere that get a chance of that. So the supermassive black hole down in the center of Centaurus A is about 55 million solar masses, not as big as M87 at 70 million light years away. And those jets that are occurring out of it, those are responsible, and the supermassive black hole emits a huge amounts of relativistic jets, and they create X-rays, which you see in purple, as well as radio light, which you see kind of in the glow, in the kind of background glow. Now, you can also see if you take radio observations over a few decades or so, a decade or two, you can see that things are actually moving. And the movement inside of the material in these jets is about half the speed of light. And as they move, the jet collides with gases in the surrounding medium and creates very high energy particles, which then decay and form light. So the X-ray jets of Centaurus A are thousands of light years long, and the radio jets that are also visible in other wavelengths can be up to 1,000,000 light years long. So we're only looking at the X-ray jets, but if we could see the radio portion of this thing, it would stretch over 1,000,000 light years long. It'd be much, much, much larger than the full moon. It'd be quite interesting in the sky. So this is also thought to be, of course, a supermassive black hole down in the center with about 55 million solar masses. And here's another view of that. There's the central active galactic nucleus down in the core, and the jet which is coming out the side. These jets are going about half the speed of light, extending for tens of thousands of light years, or thousands of light years long. That's how long that jet is. And there's even the faintest hint of a counterjet. So that's kind of what we would expect in these things, is there'd be two jets, one above the disk and one below, in the center of Centaurus A. And so we see there's the galaxy emitting all of that light. And supermassive black holes and their active galactic nuclei do the trick. All right, so here's another example of an active galactic nucleus. And so this active galaxy has a supermassive black hole in the center, creating all the light. So let's see how the X-ray radiation is occurring specifically in that. So if you have a strong magnetic field, then what happens is you can then have the electrons spinning very, very, very fast inside of this magnetic field. And where the X-ray emission comes in these jets is that as the electron spins and it approaches a proton, because it's going nearly the speed of light. So as it's going nearly the speed of light, it will spin by a proton, and as it does so, feels the pull of the proton while it's moving in the magnetic field, and it loses a little bit of energy. And as it loses some energy, it loses it in the form of light, called an X-ray. So this is called breaking radiation or Bremsstrahlung radiation. And so that's where the X-ray emission comes in these jets, as the protons and electrons interact along the magnetic field, and then the X-rays then get emitted as the electron slows down as a result of getting close to the proton inside the magnetic field. And so that's where we get that, and it's called synchrotron radiation. And synchrotron radiation is a result of movement of the electron inside of a strong magnetic field. The X-rays come from the breaking radiation, but then that's a non-thermal form of radiation, as well as what you see from the radio emission. The radio emission is from synchrotron radiation, just from the electrons themselves losing a little bit of energy as they spiral around the magnetic fields. Occasionally they get close to a proton and do the breaking radiation to emit X-rays as well. So therefore, when we look at an active galactic nucleus, we should expect a lot of radio emission, a lot of X-ray emission, and not as much thermal emission. And that's what's being described by the little sketchy graph on the right, is that if it were due to thermal radiation, meaning hot something, then you'd expect kind of a bump like you see there. However, you don't see that. You see a roughly flat emission across much of the spectrum, and then you get lots of radio emission, and then and also some X-ray emission as well from synchrotron radiation. And just to highlight that, a nearby quasar, 3C273, which is about 1 billion light years away, a billion light years away or so, has three major components, and the center hump, right around 10 to the minus 6 electron volts, that's the thermal emission from the galaxy itself. And at higher energies on the right, that's X-ray emission due to Bremsstrahlung or breaking radiation I talked about. That's what that jagged pointy thing region on the right is due to, and on the left is radio emission due to synchrotron radiation. So notice that both the radio emission, which is synchrotron, and the X-ray emission, which is breaking radiation, have roughly the same kind of shapes to their curves, but they contribute differently. One contributes at high energy on the right, and that's what the dots are. Those dots are the actual measurements of the X-ray radiation. And on the left side, where that peak is on the left, that's the radio emission due to synchrotron radiation. So you have thermal emission from the stars and starlight, but the vast majority of the energy actually comes from in the form of X-rays and radio. And almost very little of it comes from visible light, which is the middle little trying to be there sort of hump that's in the middle. But the vast majority of the energy comes from those other regions. And all of that energy from either side of it comes from the supermassive black hole in the center. So we've got this massive, this jet. Things are falling in, creating huge amounts of energy, and it spirals and falls into the central black hole. The black hole heats it. The energy that it's released by getting closer and closer and closer through friction. The friction then heats the gases up to millions of degrees to form X-ray light that we see if we're looking down the top of the jet. And if we can see the jet, then the jet is giving us two different forms of light, one in X-rays as the electrons spiral in the magnetic field and interact with protons, and then there's also radio light from the synchrotron radiation as the electrons themselves just lose a little bit of energy as they go nearly the speed of light as they spiral along the magnetic fields. So they get launched from very close inside of the black hole, and then they spiral along those magnetic field lines constrained in the jet. So then how do these supermassive black holes form? Nobody really knows, but there's probably some collisions between smaller black holes, because there aren't very many middle-level black holes. There's like stellar mass black holes, there's neutron stars. We know that neutron stars are formed by the explosion of supermassive stars. We know that stellar mass black holes up to 100 or so solar masses can be formed by the collisions of either smaller black holes or directly created by massive stellar explosions. But to get a black hole between 100 solar masses and 1,000,000 solar masses, hard to know where those actually come from. So one would think that million solar mass black holes don't just appear out of nowhere, they should grow from something. But to actually not see too many of these intermediate solar mass black holes is a problem for astronomy, and it's an area of active research, is where are the intermediate solar massive black holes? Because we find stellar mass black holes, and we find supermassive black holes, but not much in between. And actually discovering smaller black holes in between is a definite area of research. So perhaps galaxy interactions, so you have colliding gases. If you have two galaxies colliding, and then they might dump material into the black hole. Or maybe the stellar bars themselves. Maybe we saw barred galaxies. Maybe that itself, the bars themselves, provide a train by which they can funnel into the gas. And maybe smaller galaxies get cannibalized by bigger galaxies. So a huge galaxy is there, and a little galaxy gets too close and falls into the core. And so you can have that, but let's see if that actually is something we can see. The NuSTAR X-ray telescope, which is the next generation X-ray telescope launched by NASA, was able to see on the left-hand side the image of in very high energy X-rays as material falls into the very inner regions of a black hole. That's what this NuSTAR is looking for. It's called a black hole telescope, because if you're looking extremely high extremely high energy X-rays, then those things must come from the inner regions of the black hole. So that's what we're seeing on the left-hand side. Optical images on the right and a combined images in the middle. So the X-ray data says that we're having an enormous, huge galaxy collision, a pair of galaxies colliding, and as they collide, they're forming another supermassive black hole. So there's the X-ray emission just from the NASA's NuSTAR, or Nuclear Spectroscopic Telescope Array, looking at ARP 299, and they weren't sure if one is going after the other, but we're looking specific. Well, there's two black holes colliding inside of this, and if we overlay that with the imagery from an optical image, we can see that the two galaxies, as they're colliding, we see that the X-ray emission comes from the center of them, which is interesting. So the black holes might be in the process of colliding and forming one big black hole. So do most galaxies have supermassive black holes? And the answer is yes. Nearly all spiral galaxies show some level of activity, even the Milky Way. And as we look closer and closer at them, the more we look at galaxies, we find that there's more and more reasons to think that that all galaxies have supermassive black holes. If it's a spiral galaxy, it has a supermassive black hole. If it's a massive elliptical, it has a supermassive black hole. In fact, there are no galaxies found yet that don't have supermassive black holes, but the active galactic nucleus element is if there's fuel. So there are lots more AGNs in the past, but fewer today, and where are all the dead quasars? And so that asks the question. Now we see that we find this is just another example of what we mean by this, the size scales of these things. We see them in distant galaxies. Again, another way to look at it is there's other spiral galaxies. When we look at the center of it in 21 centimeter radiation, which is radio light, we can get a Doppler shift and actually see the sides and see the radiation coming from the inner quarter of a parsec of the center of this galaxy, which is approximately 20 kiloparsecs across. And the whole galaxy is more like 10 kiloparsecs across. And the center 0.2 parsecs has super speeds going around, and the super speediness has massive redshift on one side and massive blue shift as material goes around the central supermassive black hole. So such studies of the centers of galaxies, amongst many of them, and then comparing them to others, show that the central mass of a black hole is correlated to the size of the galactic core. So the more massive the bulge of the galaxy, meaning the more massive the black hole. And so that's what this graph means. We can see that smaller galaxy bulges, which are represented by these little dots, have smaller supermassive black holes. Larger galactic cores or galactic bulges have larger supermassive black holes. So there's just basically more stuff to feed on, and the black hole collects more and more stuff. So even though the black hole is an incredibly tiny target, I mean, it's like having a target the size of one person across the entire city of New York City, all 5 boroughs. And so the bigger the guy at the center of Times Square, the bigger the city. So imagine that there was a correlation. The weirdness about this is that, let's say you said, well, how big is a city? And then you'd say, well, let's see, there's 10,000 people in this city, there's 100,000 people in this city, and there's 1 million people in this city. What this is saying is, go to the center of that city, and if you find a 1,000-person city, in the very center of the city, you'll find a very small person, like a tiny person. Now, he'll look like a certain thing, and he'll have like a little sign around saying, I'm the center guy in town. But if you go to a larger town, that person will be physically larger. And you'll have a sign and say, I'm the center guy in town. And if you go to a massive city, the guy in the center will be even bigger. But not like giant sized. The difference in size between them will be maybe 100 times in certain size. But the bigger the city, the bigger the person at the center of the city. And there's a direct correlation between the two of them, which is very interesting. So that tells us something about the evolution of galaxies and black holes in them. So let's see if we can figure out if there is a link between the evolution of galaxies and their active states. So if we then look at the most active of the active galactic nuclei, quasars, quasars were things that are incredibly bright active galactic nuclei. They are the brightest of the AGNs, but they're also the most distant. And therefore, since they're the most distant, they occurred the longest time ago. So therefore, they represent an early stage in galaxy development. So quasars are a long time ago, and if the universe is only 13.6 billion years old, and we're looking billions of years in the past, this is a childhood picture of supermassive black holes. So we can see that the image that we see inset is that quasars are part of galaxies, but yet they're bright supermassive cores of galaxies. Now, quasars themselves then had an epoch where they lived and when they were born and when they died. They seem to have started roughly about 12 billion years ago and seem to have had their peak about 10 billion years ago. And then they kind of petered out after that until about 2 billion years ago. So what we find is that the thing that we call quasars, or whatever is making it the brightest possible thing that the quasars are, that fuel for quasar activity happened at when the universe was only a couple of billion years old, a few billion years old, and then it faded away. And so as time went on, fewer and fewer quasars existed until today. We don't have any quasars in the local universe. It doesn't mean that the supermassive black holes have gone away. It's just that there's nothing left to feed them. So supermassive black holes grew, got fed, did their quasar thing, and then stopped. So we look at something like the 2DF Quasar Survey. They just finished this up in 2008, which is a long field survey. We can look at this thing and say, okay, these pizza slices are two different directions in the sky, a few degrees wide, high. We just compress it so it looks like a two-dimensional survey. But the center of this wedge is where we are in the Milky Way, and then we look out into the pizza wedges towards the edge of the pizza, and we find that the peak of them ends at about 10 billion years ago, at a redshift of about 2. But then we see that there are some quasars that approach to about 2 billion light years. But if you squint really hard at this thing, you can say the vast majority of the quasars were between, say, 13 billion years ago and about 10 billion years ago, and then they fade roughly away. Notice that there are fewer by number inside of the 8 billion to 2 billion area compared to the 10 to 12 billion area. There's a lot more that are seen at 10 billion light years away or 12 billion light years away than nearby. So, and there's almost none. In fact, there are none within 2 billion light years of Earth. So that's an important element of it that says that quasars are a temporary process inside of the history of galaxies, and they fade with time. That doesn't mean the supermassive black hole goes away. It doesn't disappear. It's just that the thing that makes a quasar stops after a while. And let's see how that then all adds up. So we have black holes are supermassive, and they're part of galaxy evolution. So we're going to find that galaxies start, or we have found and have seen, that little tiny galaxies long, long ago were tiny and misshapen and irregular. And then they merge together. We've seen that galaxies collide and stick together. We've seen galaxy mergers all throughout. And when they merge, they make a larger central black hole. Those then go from tiny misshapen galaxies to larger galaxies with some sort of central black hole. Then those things collide and the black holes fall together to form supermassive black holes. Now when you have two large such galaxies colliding, you then have an enormous amount of material that forms them, and that can create a radio galaxy or a blazar or a quasar across the top. And if we're looking straight down the top, there's a huge amount of material. That active galactic nucleus then can be a radio galaxy, a blazar, or a quasar, and then eventually that settles down, using up all the gas and dust and material, and it blows everything out, and it eventually settles into becoming an elliptical galaxy. However, the quasar activity occurs, and then after it does the quasar activity, it has little bitty tiny other mergers. Then you can get Seyfert level activity after the quasar is done, because quasars are a very short period of time when suns are being consumed per year, because that's what the amount of energy that it takes to make a quasar. So quasars themselves fall with, when they're done doing quasar activity, you have a normal galaxy, and if they have little tiny mergers, then you can have Seyfert level activity, which is a lot of active galactic nucleus, but you don't get the lobes or blazar activity, but just little activity, and then those things can settle down and become spirals. But if you have massive activity, it can disrupt and use up everything in the entire galaxy, blowing away the gas and dust and eliminating it, forming giant elliptical galaxies such as M87, or you can have a series of minor mergers and form spiral galaxies such as M101 or the Milky Way. And that's our summary of exactly how galaxy evolution and those things go. So supermassive black holes can explain that, and they can also explain the evolution of galaxies as they go from billions of years, as they can evolve by collisions and mergers into forming larger galaxies. All right, so we're going to go into the cosmological end of things next time. See you soon.